Hello.
Hello. Hello, ma'am.
Hey, Puspendra.
Hello, sir.
Can you hear me?
Yes, sir, I can hear you.
Okay, that's what I just wanted to check. Thank you.
Okay, sir.
Hello, Devakant.
Yeah.
Okay, so Professor Thomas Bruckel is, I think, there.
Yes, sir, he's here.
Yes.
Zupankar.
Hello, Thomas. Very nice to see
Oh,
you.
how are you doing?
Yeah, fine. Thank you so much. Very glad to see you.
I'm glad to see you. Yeah, would be nicer in person, but at the moment, that's all we have, right?
Yes, yes. So, how are you?
Oh, I'm fine. I'm fine.
Okay. Because we heard that in Germany again, the corona is spiking.
Yes, numbers are going up rapidly. That's because we had a change of government, and the old government, or we are in the process of changing government. And I think the old government is not doesn't feel really responsible. The new one, not yet, and so they didn't take serious preventive measures, and so now it goes up radically. As the scientists have predicted, I mean,
Okay.
we can calculate that.
Yeah, in India, at the moment, it is not too bad. So,
Sorry, I didn't hear.
but at
It's
least,
not too bad, right?
yes.
It has calmed down, right? Yeah, with Corona. Yeah, in Germany it's raising again, but luckily not so many very severe cases. Yeah, because a lot of people are vaccinated. So. Okay. I think you're frozen.
So Professor Vedanta Corso, can we start now or we'll wait for some more audience to join us?
Okay. So, Devakant, can you hear me?
Yeah, I can hear you.
So, okay, we can do that. You can mute there. I'm sorry, there is some internet disruption. Yeah, so we can start. I'm very happy to introduce Professor Devakant Samal. He is an associate professor in physics at Institute of Physics, Bhubaneswar. His research expertise is magnetic ferromagnetic superconductor electrostructure. So, Devakant, how are you?
All right. Welcome to this second day of this conference.
Again, there is something.
So the first talk will be given by Professor Thomas Bruckel. So Professor Thomas Bruckel, he is now presently the director of Jülich Center for Neutron Science at Trossenzentrum, Jülich, Germany. And he is very well known for his phenomenal work on neutron and synchrotron scattering. And mostly his research area covers a wide spectrum of topics, and most of them mainly limited to this magnetic nanostructures, quantum magnetism, and mainly the magnetic phenomena in solids. I think with that brief introduction, I would like to invite Professor Thomas Bruckel to deliver his talk. And before the talk starts, I would like to tell that all the speakers who are in the first session, so the talk will be for 25 minutes and 5 minutes will be for interaction or any questionnaire session. So yeah, Professor Thomas Bruckel. Please.
Yeah, thank you very much for the introduction. Good morning, good afternoon, good evening, wherever you are. And yeah, thanks a lot for the invitation. Thank you specifically to Subankar Vedanta, whom I know since he did his PhD thesis in Duisburg-Essen with Professor Kleemann, and we stayed in contact all the time. And I have to say, I'm pretty impressed with the research group that he built up at NISA. Okay, so I will try to share my screen. Let's see. This is not correct. Here, can you see
Yes.
my presentation?
Yeah, we can see it.
Okay, perfect. Okay, so yeah, the title, Addressing the Climate Crisis, How Can Magnetism Contribute? It's maybe a bit surprising because magnetism you don't immediately connect with climate, right? So I have added a second short title, Quantum Frost, and that might give some hint what to be expected in this talk. Now, this is not very long ago, the UN Climate Change Conference in Glasgow. And there were some recommendations, few decisions. I think young people are a little bit disappointed about the outcome of this conference. They will have to take the consequences of what was decided there. But coming from Jülich, you know, we are in a region which does lignite surface strip mining. You see, we have some of the biggest holes in Europe around Jülich. So there is lignite being excavated, being transported with conveyor belt directly to the power station. And this power station have a lot of CO2 emission per year. Now, it's clear that mankind is responsible for a lot of carbon emission, as you see here, since the beginning or middle of last century here, the carbon emitted in to the atmosphere increases drastically, and you can make a one-to-one correlation between the CO2 in the atmosphere to the global temperature change. So it's pretty clear that mankind is responsible for this temperature change. And the UN climate conference predicts that wants to achieve a limit of 1.5 degree in global warming, but it's very likely that it goes up to 2.4 degree with the recommendation that they have. And this doesn't seem too much, but if you remember that the ice age was just 5 degrees less temperature on Earth than we have now, you can imagine that this has a huge impact, 2.5 degrees temperature change. Now in Germany, we are in the process of an energy transition away from fossil fuels towards renewable energies. But if you look at this, everything that is gray or black here, these are fossil fuels that are being burned. These are renewable energies, and this is only the electricity generation, which is only like 20% of the total energy. Now, it's great to go to renewable energies, but if you look at the graph on the right, here you see that you only get electricity when the wind blows, when the sun shines. So the problem are these big dips between the produced electricity. So we have to find ways to store energy, like with hydrogen or something. This is a huge challenge at the moment. Now let's look at the other side of the medal, the electric energy consumption. And what might be surprising is if you look at here, cooling, refrigerators, and so on. Cooling applications amount to about 1/4 of the electric energy consumption. And this is mainly due to like cold storage, to the huge supermarkets which cool their goods and so on. So 1/4 of electric energy consumption is for cooling applications. So this is where you can save electric energies, because up to now we use the same process that was used already 200 years ago. It's essentially expansion of a liquid into vapor through a nozzle, which happens here, and then you have a cyclic process, and this is what you have in your fridge, this is what you have in air conditioning, and it's actually a very inefficient process because you have all the friction of the gas, of the liquid, and also it uses refrigerants which are very climate active again. Yeah, you know the problem of ozone depletion from chlorofluorocarbons, which are now forbidden, but still you have a lot of climate active gases in these refrigerators. Now we come to magnetism finally after this introduction. So can we do better? And yes, we can. And this is where magnetism comes into play. You can do such a cyclic cooling system with employing a magnetic system. The principle is quite simple. You apply a magnetic field to a magnetic material, you align the magnetic moments. That means you decrease the magnetic entropy. And if you do this adiabatically, that means you have to increase the lattice entropy, which is connected to heating. Now you expel this heat in a heat exchanger, and then you remove the magnetic field. The system cools down. Yeah, the magnetic entropy increases, lattice entropy decreases, the system cools down, and this you can use for cooling applications in your fridge, in air conditioning, and so on. And then you can do a cyclic process. And this process is predicted to be 30% more efficient than the vapor compression cycle, and it doesn't use hazardous gases. So we should move in this direction of caloric cooling. There's also other methods, barocaloric cooling and so on. But here we are talking about magnetism. Yeah, there are already some demonstrators. And if you see here, this is an optimistic view of a big company, General Electric, from ice harvesting via vapor compression, which is being used today, to magnetic refrigeration. You see 2020. Well, demonstrators exist, but it's not yet outrolled in a large scale, this technology. Okay, so we are doing research on material systems which can be applied for such caloric cooling. And I want to introduce the first system that we looked at. This is a manganese iron silicon 3 series. Now, this has been studied already like 20 years ago here. This is a phase diagram. You have ferromagnetic, antiferromagnetic, different antiferromagnetic phases. But if you look at this compound here with X equal 4, you see that it has a phase transition at 300 Kelvin. So at this phase transition, of course, you can, by applying a field, you can change the entropy a lot. So this is interesting for cooling applications. And this diagram here shows for the different X equals 0, 3, 4, 5 compounds, the change in magnetic entropy as a function of temperature for different applied fields. For example, here for this X equal 4 compound, you see you have a change of 2 joule per kilogram in Kelvin here in an applied field of 2 Kelvin. Now, if you compare this with other magnetocaloric material, this is not an outstanding value. It's a modestly large magnetocaloric effect, but it happens in an interesting temperature range. The material is interesting because it's a metallic material. It's relatively easy to process. And very important, it consists of abundant, cheap, and environmentally friendly constituents. So no poisonous material, no climate active gases like you have at the moment. And if we do research, of course, it's nice that we can grow large single crystals. Here's an example. Now there's another interesting compound I want to mention. This is manganese 5 silicon 3. So this is at the left side here of the phase diagram. Of course, with a phase transition of 100 Kelvin, it's not really interesting for room temperature application, but it shows a very interesting effect. And this is that it has the so-called inverse magnetocaloric effect. So if you apply a field, the material cools down, yeah, instead of warming up what you naturally would expect. So we want to understand how this happens. Okay, let's start with the manganese iron 4 silicon 3. These are magnetization measurements along different direction, 100, 001 direction. So you see the material is very anisotropic. It doesn't quite reach the magnetic moment that you would expect in a insulator. The magnetic moment per atom, it reaches up to 2 μ at large fields here, 15 Tesla. But what is very interesting is that it shows a very small hysteresis, and a very small hysteresis is important if you want to do cyclic processes. Now, how do we determine the magnetocaloric effect? And there are 2 main ways. The traditional way is an indirect measurement. So you measure many magnetization curves and you use a Maxwell relation. So you have many magnetization curves, magnetization as function of temperature and magnetic field. And with a Maxwell relation, you can relate that to a change in entropy. The total change in entropy applying a magnetic field is given as an integral. And then from the change of entropy, you can calculate the change in temperature by just using heat capacity measurements. Now, a more modern way is to do a direct measurement of the temperature change. And this is being done in pulsed magnetic fields. So you apply a pulsed magnetic field and you measure directly the change in temperature. We have done that in the high magnetic field lab in Dresden. So I want to show you the results here. We have measured many magnetization curves, and from that calculated the change in entropy as a function of temperature and field. And you see there's again a huge anisotropy. So this is along the 100 direction. This is along the 001 direction. For 1 Tesla, this is for 6 Tesla field. Of course, the change in entropy is larger. We also measured the specific heat, and you see that around phase transition, there is some interesting behavior, which indicates magnetic lattice coupling. And then if you calculate the change in temperature when applying a magnetic field, then you get such a behavior here. So 1 Tesla, 1.3 Kelvin change in a field of 1 Tesla. The other way to do it, and the more direct way for applications, is to use a pulsed field. We have done measurements up to 30 Tesla, but this is an interesting curve here. We apply a field pulse here, field pulse over 50 milliseconds. 50 milliseconds, that corresponds nicely to operation frequency of such a fridge, which will lay between 10 and 100 hertz. And you see, this is a field pulse, a black curve, and the blue curve shows the sample temperature. So we really have an adiabatic process where the sample temperature nicely follows the field pulse. And with a field of 20 Tesla here, we get a change in sample temperature of 5 Kelvin. Okay, now we want to validate these two measurements against each other. And this is the curve here, around 300 Kelvin, so room temperature application. We get nice changes in the, nice changes in the temperature, about 1.2 Kelvin for one cycle. And the calculated and the direct measurements, they coincide quite nicely. Now, what's also very important, we have done these field pulses many, many times, and we have a good cyclability. This is very important also for application, because if you have a strong magnetoelastic coupling, then you might destroy the material if you have many, many cycles. Okay, now we want to understand the basis of this magnetocaloric effect with a microscopic understanding. And the first thing you have to do, you have to determine structure, you have to determine magnetic structure, and then you go to spin dynamics. So how do you determine structure and magnetic structure? Of course, you use neutrons. Why neutrons? Well, we have iron and manganese in the system, and iron and manganese have nearly the same number of electrons, so they have no X-ray contrast. With neutrons, we have a huge contrast because manganese has a negative scattering length. That means an additional 180 degree phase shift during scattering. And we find with experiments at spallation source and at our main outstation at MLZ in Garching, we find the structure and we find partial ordering of iron and manganese in this system. So this is a crystal structure. The crystal structure consists of iron silicon octahedra here, which share triangular faces, and they form chains along the z-axis. Yeah, so this is in the AB plane. This is along the z-axis. You see, we have these chains. These are iron atoms, silicon atoms, and in between we have this distorted octahedra of iron manganese. And as you see, we have a partial ordering from plane to plane. Here more manganese, here more iron. Yeah. Okay, so this is a structure of the material. The magnetic structure can be also obtained with neutrons. So the spin lays in the AB plane. They reach a moment of 1.5 μ, so not as high as you would expect it for manganese or iron ions, according to Hund's rule. And what is interesting is that we have no refinable moment on the iron sides within the iron silicon octahedra, and this has probably to do with the distances between iron and silicon and between the different iron atoms. Okay, so we know structure and magnetic structure, but if we want to understand what happens during application of a field, we have to look at the spin dynamics. And the spin dynamics, of course, you study again with neutrons. So first step is to do spin wave dispersion, Magnon dispersion at low temperature. And you see that the dispersion here is very anisotropic, very steep along C and relatively flat along the H00 direction. We can described this quite well with a Heisenberg Hamiltonian with a very small spin wave gap. We can determine exchange parameters. Okay, so this is just to characterize the system. Strong anisotropy, which we also saw in the magnetization measurements. Now, the next step is if you want to have an effective magnetocaloric effect, you have to transfer entropy from the spin to the lattice. How does this entropy transfer function? How can we quickly transfer entropy from the spin system to the lattice system? So there we look at spin and lattice excitations. Lattice excitations are phonons. And to be sure that we only measure the phonons, we have done this at the European synchrotron radiation facility with inelastic X-ray scattering. The X-rays only see the lattice excitations. And these are these here, transversal acoustic, longitudinal acoustic, optical phonons. And the light green data here, these are the magnons. And this is particularly interesting. And the magnons are determined, of course, again, with neutrons, with polarized neutrons, to be sure we don't have contamination from phonons. Very interesting is that we have here a region with a strong overlap of magnon and phonon excitations. We discovered that here is magneto-vibrational scattering that leads to a vanishing of intensity in one of the non-spin flip channels. So this is a bit technical. But what that means is we have a very strong coupling at low energies, relatively low energies, between the magnetic and the lattice system. So this is an effective way to transport entropy between the two systems. Okay. Now, this was low temperature. This was excitation from ground state. Now we want to understand what happens close to the phase transition, because this is where we want to apply the magnetocaloric effect. And for this, we measure the dynamical susceptibility, again with neutrons. This is a temperature dependence of the dynamical susceptibility here. You see it peaks, of course, at the phase transition. That's how it should be. This here is a field dependence for energy transfer 0, so elastic measurements. Now, this is the field dependence of the dynamic susceptibility as we apply a field at 300 Kelvin. Yeah, so these are these curves, red and green. You see that we very quickly suppress all the magnetic fluctuations. Very quickly, what is the standard? Well, we can do a mean field Landau theory calculation, and there you see at 2 Tesla, sorry, we should still have very strong magnetic fluctuations, while in reality, with 1 Tesla, we have essentially suppressed magnetic fluctuation in that system. And this, of course, is important to have a large magnetocaloric effect. Yeah? We want to apply a small field and have a large change in entropy. Yeah? This is exactly what this system does. Yeah? Okay.
Yeah, Professor Thomas Brockel, you have roughly 3 minutes.
Roughly 3 minutes.
Yeah.
Well,
then
okay.
I'm reserving 5 minutes for any comments, discussion, or questions.
Okay. Thank you for warning me. I want to still say a few words about the inverse magnetocaloric effect in manganese 5 silicon 3, because this is very interesting. You would expect that if you apply a magnetic field, you decrease the magnetic entropy, you increase the lattice entropy, the system warms up. Here, it's exactly the opposite. And to understand this, we did again neutron scattering, determine magnetic structure, look at the phase transition. Here we have a phase transition from a non-collinear, non-planar magnetic structure to a collinear structure. And what is very important is that the magnetic moment at this site here vanishes in this AFM2 structure. And at the same time, if we look at the spin excitations, you see that in this in the AFM1 structure, we have spin wave excitations, sharp spin wave excitations here. And if we go at higher temperatures to the AFM2 structure, all of a sudden this whole region here in energy fills up. So we get strong magnetic fluctuations. So by increasing the temperature, we get magnetic fluctuations which correspond to paramagnetic fluctuations. Can measure this in more detail. But now the interesting thing is what happens if we apply a field. And if we apply a field, we come from this phase to the AFM2 phase. And in the AFM2 phase, we have seen we induce, here we have spin waves at low temperatures. If we go at low field, if we go at high field, we induce additional magnetic fluctuations. And this increases the magnetic entropy and explains the inverse magnetocaloric effect. Okay, I skipped this part in view of time. And I come to my summary. So having the ability to grow single crystals and use polarized neutrons, we really make a big step towards understanding of the magnetocaloric effect. This promises energy savings up to 30% compared to the vapor cycle. This material is not outstanding in terms of the magnetocaloric effect, but it's cheap, abundant, has environmentally friendly materials, good cyclability. We showed that this new method of direct measurement of the magnetocaloric effect gives the same result like the indirect measurement. We have a pronounced magnetic anisotropy, which is also important for applications because that means we have to texture polycrystalline material. We showed that for this system, manganese iron 4 silicon 3, we can suppress paramagnetic fluctuations in rather small field, which leads to a large magnetocaloric effect. This material with the inverse magnetocaloric effect there, this is due to the counterintuitive field-induced spin fluctuations. And then the conclusion is that what we understand is we have to have materials which have a moment instability in metallic materials. This leads to a pathway to high MCE effect. And indeed, we are in the process of preparing a paper where we show that this manganese 1, which has an unstable magnetic moment, has such an unstable moment due to the coupling in a frustrated triangular arrangement with the manganese 2. And this probably is important for this MCE effect and especially also for the inverse MCE effect. Okay, I hope I stayed halfway in time. Thank you very much. I have to thank many people. All these people have contributed to this work, thesis students, senior scientists, and I have to thank all the people who helped us with measurements at synchrotron radiation sources, neutron radiation sources, and so on. Thank you for your attention.
Thank you, Professor Thomas Broekel, for such a nice, excellent talk on this magnetism. And this, so now I think the talk is open for questions and comments.
Devganta, can I ask a question?
Yeah, please.
Thanks very much, Thomas. Very nice talk. I would like to know whether is there any structural phase transition in the magnetic field in this compound.
Excuse me, I didn't.
Is there a structural phase transition in this compound under the magnetic field?
There is a small structural change, and this leads to this transition from AFM1 to AFM2 in the manganese 5 silicon 3. So because the distances change, and the distances change, and that leads to an instability of the manganese 1 moment.
So both are coupled. The induced
So
fluctuation.
there's no strong spin lattice coupling, because if you have a strong spin lattice coupling, you can get a strong MCE effect, because you get additional change in the lattice entropy. But these materials, most of these materials are unstable if you cycle. You have to see for continuous cooling applications, you have to cycle that millions of times, the material. And if you have a strong coupling to the lattice and you have a phase transition in the lattice, you can get a large effect, but eventually your material will amorphize.
Okay, thanks very much.
All right. Is there any other questions?
Sir, hello, sir. Can I ask a question?
Yeah, please.
Professor, thank you for the talk. So in the real-time magnetic refrigerator, what form of magnetic caloric materials are used? Like single crystals or polycrystals, ribbons, wires, which is the advantageous form?
There are polycrystals. There is one hydrogen containing compound, which is at the moment hot. I don't know the formula at the moment precisely, but it's polycrystalline material, of course, because for commercial purposes, you cannot use single crystals. That would be too much challenge. And the idea is to have permanent magnets which deliver a magnetic field of say 1.5 Tesla, and you have a plate where you rotate your magnetocaloric material through that field. With that, you can make field pulses, and then you have to have cooling liquid running through this material that goes to the heat exchanger. So yeah, there are already commercial systems available, but at the moment, as I say, it's not rolled out a lot for a lot of applications. But
All
it's
right.
coming.
Okay, so
Thank you.
I think I will take one last question that is from chat message. This is so the question is the following. Regarding this power consumption, you also need to, you require electromagnets. So for that
No,
to
no,
make
no,
it,
no electromagnets. I mean, these are permanent magnets, and you just rotate your magnetocaloric effect material through these magnets. That's
okay.
So you just need a motor, electric motor, to rotate it. So
Yeah.
it's.
I think that was one of the questions from the audience. I think that answers his question.
If you use electromagnets, you don't win. You don't gain in efficiency.
All right, because the paucity of time, there are some other questions I see in the chat box, but let us not extend it further. So let us give a big applause for.
Can you hear me?
Yeah.
So there is a memento.
Yeah. So
Thomas, please stop sharing your screen. Thank you very much for your nice talk. So.
How do I stop? Okay.
Yes.
Okay.
Devakant, I request you to present this digital memento to Thomas.
yeah. So let me read it out. Symposium on Magnetism and Spintronics, Niger, Bhubaneswar, India, takes immense pleasure in presenting the plaque to Professor Thomas Bruckel, Zurich Center for Neutron Science, Germany, in appreciation for being a valuable speaker to give a lecture on addressing the climate crisis. How can magnetism contribute? Thank you very much, Professor Thomas Bruckel, for illuminating us on your research work. Thank you
Thank you
very
so
much.
much, Thomas.
Thank you.
Thank you very much. Abhishek, you can stop sharing your screen.
Okay, so yeah, Professor Tanushree Sahadas Gupta, she's around, I think.
Yes, I'm around.
Okay. So now we have Professor Tanushree Sahadas Gupta. So let me give a brief introduction about her. She is a senior professor and director of Asian Bose National Center, Calcutta. She is very well known for her work mainly based on the first principles electronic structure calculation and study of magnetic, optical, and electronic properties of complex materials, and to provide a realistic theory of strongly correlated electron system. And she is very well known, I mean, not in India, also across the world, to the scientific community in her community. And she has many accolades from national and international level. And I don't want to list those, but just to tell that she is a fellow of American Physical Society, and she is also a fellow of all science academies in India. And she is also a awardee of Sunna Jayanti Fellowship and as well as Bhatnagar Award. So she will be talking today an interesting topic, designing 2D ferromagnetism. So now I would like to request Professor Dasgupta to please.
Thank you very much for the kind introduction. Just one correction concerning the awards. I am not a Bhatnagar awardee, so I stand corrected there. Okay. And thanks the organizer for giving me the opportunity for sharing some of the work we have done in this forum. So the title of I hope my screen is visible.
It's half visible. Yeah, now it is visible.
Yeah. So the title of my talk, as announced, is Designing Two-Dimensional Ferromagnetism. The previous talk was on importance of magnetism on climate. And as I will try to show, of course, the magnetism is important for other things as well. And I belong to the Department of Condensed Matter Physics and Material Science, as well as part of the thematic unit on computational material science at Asian Bose National Center for Basic Sciences. For those who are especially from out of India, it is this institute was formed in memory of Professor Satyendranath Bose, in whose name half of the fundamental particles of this world, namely the bosons, are. The collaborators in this talk that I'm going to present is Dr. Dhani Nabde, who is my former PhD student. Now she is doing her postdoc in KPCTP in South Korea. Dr. Dipan Sen, the postdoc with me. And we have been greatly benefited by collaborating with the group of Professor Purujena from Virginia Commonwealth University and Dr. Anamitra Mukherjee from NICER, the organizing institute of this conference. And the funding came from Nanomission Department of Science and Technology and also Jessie Bose Fellowship of SERB. So we are all quite conversant with the world of two-dimensional materials since graphene was kind of exfoliated from graphite in the form of a monolayer carbon. Due to its extraordinary property, there have been a lot of interest in the 2D materials in general, and many of them have been synthesized. I showed only a few examples like silicon, borophene, MOS2, in general transition metal dichalcogenide, the hydrogen decorated graphene, and etc. And they have shown a variety of property, which starts with the metallicity with unprecedented mobility in case of the graphene, to many of the newer properties like topological properties, charge density wave, superconductivity, and Mott insulating property in very recent time in bilayer twisted graphene. Now, missing from this portfolio until recently is that of an intrinsic magnetic order. So what I mean by intrinsic is not like what can be induced by adding add atom or by creating vacancy and defects in graphene that was attempted. Because in this case, since it is externally induced, controlling of that magnetism becomes difficult. Now, the magnetism, as you are all aware of, is quite dependent on the dimensionality of the material. In case of a 3-dimension, the magnetic phase transition can always occur at finite temperature. In 1 dimension, there is no long-range ordering. In 2 dimension, the issue of magnetic long-range ordering is complex, as I will elaborate in my talk. It depends on several factors. However, such kind of a 2-dimensional magnetism can be potentially important in view of the low power, ultra compact Spintronics application that is one of the focus of this conference. And as is basically, it was a title of one of the article in Nature Nanotechnology, which says that the 2D magnetism gets hot. And the demonstration of room temperature ferromagnetism in atomically thin layer broadens the prospect for device application of 2-dimensional van der Waals materials. 2D magnetism actually is an old story, but in recent time it has got more and more focus because of its possibility with the device application. It started as back as 1944, when basically it was Onsager who proved this long-range order in 2-dimensional Ising model. And it took about 20 years to prove that instead of an Ising model, if you have a Heisenberg model, then there is no long-range order in 2 dimension, which is known as the famous Marmon-Wignaud theorem. Around the same time, 1968, quasi 2-dimensional long-range order was discovered in such kind of a layered material, namely K2NiF4. And in 1976, another 10 years down the line, monolayer thick magnetic films on substrate was discovered. And after that, several years have passed. And in 2004, we had the proof of this freestanding graphene. And then came the recent discovery is in 2017, which actually there are papers that showed the existence of 2D ferromagnetism, which will be the topic of today's talk. Now, the 2D magnetism, as I said, it's kind of tricky, it being in between the 1D and 3D, the presence of long-range magnetic order is kind of tricky. And that also depends on whether you are talking about a metallic system or an insulating system. In a metallic system, of course, it is the itinerant magnetism that we are talking about, and the magnetism being guided by what is known as Stoner's criteria, and which basically depends on the shape of the density of state at the Fermi level. In case of insulating system, which was actually what I showed when I was showing the history, I had in mind the insulating system, is the Marmon-Wignaud theorem, which says that finite temperature, spontaneous symmetry breaking is absent in a 2-dimensional isotropic Heisenberg model. All of these are very important, 2D isotropic Heisenberg model. So this is the precise statement taken from Marmon-Wignaud paper, which says at any non-zero temperature, a 1 or 2-dimensional isotropic spin Heisenberg model with finite range exchange interaction can be neither ferromagnetic nor antiferromagnetic. By isotropic, what it means that your spin can point to any direction. So therefore, you have a rotational invariance or a continuous symmetry because spin can point in any direction, which in a formal way and a technical sense will be called a distinct 2 symmetry. So this is the form of this Heisenberg model, as you are all aware of, but the spin here can point in any direction. Now, the proof of it is kind of, this is shown in the slide in a sketchy manner. You have the magnetization at finite temperature. You have a assumed long range order at T equal to 0, and then you have the temperature driven fluctuation of that magnetization. Now, the question is, can the thermal fluctuation destroy the magnetic order? That is the point. And that will be given by the magnitude of this delta M, which is written here. And that crucially depends on the density or state of the magnetic excitation. And that depends very much on the dimensionality. And you can show that if this dimensionality is 2, and if you have a short range magnetic interaction, basically this delta M, this quantity, actually has a logarithmic divergence at any finite temperature. So that means any small amount of thermal fluctuation will basically kill the magnetic ordering. So in other words, the magnetic transition temperature is a 0 Kelvin transition temperature. Of course, the whole thing is based on the thermal fluctuation. So the long range order at T equal to 0 is not strictly ruled out by Marvin-Wegner theorem, as very, very critically said in their statement at the non-zero temperature. However, the quantum fluctuation can have a similar role, but which was not covered within the Marvin-Wegner theorem. An assumption of short range interaction, later it has been shown it is not a necessary really condition, but this is applied to localized spin, where I can really have put the spins specific to a specific site, not to an itinerant magnetism. Most important probably is the assumption of isotropic interaction. Even an arbitrarily small anisotropy is sufficient to stabilize the magnetic ordering, and therefore resulting in a gapped excitation. That means where the magnetic excitation will have a gap, and therefore there will be a transition temperature to overcome this gap. So from an Heisenberg model, an isotropic Heisenberg model, you can now write a second term, which basically is the single line anisotropy. And as you can see that if this parameter A goes to infinity, this Heisenberg model basically reduces to Ising model, where the spins are basically pointed to one specific direction instead of having any possible direction. Now, the source of this anisotropy, as was the form shown a slide before, is primarily the single line anisotropy, and its origin is the relativistic origin, namely the spin-orbit coupling. And you can write it's a kind of a tensor, but you can choose the principal axes and have it in a form of this two parameter like E and T. One can in principle also have an exchange anisotropy, where whether the magnetic exchange between two parallel spin but pointing in the x direction is going to be different from the magnetic exchange of the two parallel spin but pointing instead of x direction, let's say along the z direction. That's known as exchange anisotropy, and we are really not going to talk about the exchange anisotropy here, but in many of the compounds which are in discussion in recent time, like chromium triiodide, exchange anisotropy plays a very big role. So there were two back-to-back papers in Nature in the year 2017, which actually spoke about and demonstrated the discovery of intrinsic ferromagnetism in such kind of two-dimensional crystal. The first compound was chromium germanium tellurium compound, and going up to the bilayer limit by using a small amount of field, which is shown here, that they could find that although the magnetic transition temperature is suppressed from the bulk limit, but still the value is as high as 30 Kelvin. In the experiment, they could not go beyond bilayer, but this same paper also has some kind of theoretical calculation, which shows that even in the monolayer limit, the transition temperature is well above 15 Kelvin. In the next paper, the second paper of this two back-to-back paper, the ferromagnetism was demonstrated for chromium triiodide down to the monolayer limit, and where they found even the monolayer shows this magnetic ordering stable up to 45 Kelvin. Then came this report on vanadium diselenide, which actually reported on a single layer the room temperature ferromagnetism, and which, unlike the two other examples, is metallic, and there is occurrence of magnetism due to specific monolayer band structure guided by the Stoner criteria, as I have already talked about. So therefore, there is an urgent need to expand the list of candidate material that would provide a better understanding of 2D magnetism in a diverse class of compound. And as has been mentioned, that the expertise is on first principles calculation. So we thought of using first principles calculation to basically predict new 2D ferromagnets. The first example that I'm going to talk about is boronated holy graphene. And we all know what is a graphene. In case of a holy graphene, you basically have some holes which are basically patterned in an ordered manner. So therefore, you have a graphene with some ordered patterning of the holes, and that opens up a gap, the band gap value being dependent on the size of the hole and also the shape of the hole. Then what was achieved is, like in this holy graphene structure, the nitrogenation was done so that you have such a kind of a hexagonal pattern around this hole, where two of the benzene ring is connected by a ring containing nitrogen. So this has been made, and the samples and etc. are shown. Now, what we thought as a computational person, what will be the effect of boronation? Because this nitrogenated holy graphene was found to be semiconducting and non-magnetic. Can we, instead of a nitrogen, put boron? And our past experience shows that boron can do wonder, and we worked out in the context of a two-dimensional material called as Maxine, where we showed that by putting boron in place of carbon, actually you can have a 40% decrease in the two-dimensional stiffness of this two-dimensional compound. Also, in the context of fullerene, we found that the activation energy of the Stonewall's defect can be strongly suppressed if you basically substitute boron in place of carbon at the active site. So motivated by that, we, instead of putting nitrogen, where in this nitrogenated holy graphene structure, you have nitrogen here, instead of nitrogen, we put boron. And of course, it is now our responsibility to show that this computer predicted or computer imagined structure is quite stable. So we calculated the cohesive energy and the formation energy, and all of them showed this material to be stable. We also showed their dynamical stability by calculating the phonon dispersion, as well as through finite temperature molecular dynamics, we proved their thermal stability. So what we found, this is basically the band structure of nitrogenated holy graphene and the band structure of the boronated holy graphene. The zero of the energy is all set at the Fermi level. So as you can immediately see, while nitrogenated holy graphene is semiconducting, this compound is metallic. So why it is metallic? That is rather simple to understand. If you remember that boron has 2 electrons less compared to that of the nitrogen, and I have a 2-dimensional structure. So therefore, the chemical bonding is of sp2 type with a pz or p pi orbital that is basically sticking out of the plane. So these would be the occupation of the electrons in case of nitrogen, where I have these 2 sp2 which are occupied by one single electron that gets bonded to this carbon, neighboring carbon, and I have one electron occupying in this pz or the pi bond, and there is one dangling sp2 because of the presence of this hole, which is completely filled with 2 electrons. Compared to that, in boron, there is no electron in this p pi. And on the other hand, the dangling sp2 now gets filled with only one electron instead of two electrons. So that is actually the source of magnetism, while absence of any electron in this p pi orbital leads to hole doping in this pi star network of this holy graphene, making it metallic. And that is exactly what we found just by doing the calculation and applying the Stoner's criteria, which actually tells the Stoner parameter I times the density of state at the Fermi level should be larger than 1 for the material for this metallic system to be magnetic, and we indeed find it to be larger than, much larger than 1. Doing a spin polarized calculation, we find most of the moment are actually coming from the boron site, as it should be, with this dangling sp2 bond filled with only one electron. The second example that I like to talk about is the layered inorganic organic hybrid perovskite, and searching for two-dimensional ferromagnetism in these materials. And as opposed to the previous example, these materials are insulating. So we all know what is a perovskite. The general formula of perovskite is AbX3. So if you take a cube and at all corners you put the A atom, and at the center you put the B atom, and at the all face you put the X, and that's your cubic perovskite structure. But you can, from there, you can make some kind of a layered perovskite structure. For example, you extend this along the Z direction or the A direction, let's say, and then make a cut from there and take two such cut and make them separated. So therefore, you have like a layered structure, and that is known as the famous Rudolfson proper series that you can make depending on how many basically perovskite layers are in a given thickness. So depending on that, the N changes, that's the general formula. In case of hybrid perovskite, so it's a hybrid between an organic part and an inorganic part. So the inorganic part is basically drawn from such a perovskite structure, but in between these kind of two layers, you put some layers of organic molecules. So this is the structure of this organic inorganic hybrid perovskite, which are layered. So you have the layer of this inorganic octahedral that are connected to each other, and in between you put some organic layer because you are now not restricted by the space, and there can be different possible organic molecules you can put inside. So the advantage of putting such organic molecules is now these layers becomes weakly coupled, and as I will show, they can be easily clipped and made in a two-dimensional form. So these compounds have been all synthesized basically in the University of Groningen, which was copper based. So in the inorganic part, they have the copper transition metal, which were basically octahedrally coordinated by either chlorine or bromine. Also counterpart was also studied, and then in between these, there were these organic ligands where they were connected to the inorganic layer through hydrogen bonding, and there were two layers of these organic molecules. So the two layers of this organic molecule, they are connected through van der Waals interaction, and these organic molecules, they have basically some protonated amine group and then a long tail, and depending on how long is the tail, increases the separation between these layers. And there are also examples of such chromium-based compound, which I show in this slide. So the first thing we try to calculate is the cleavage energy, how easy it is to cleave this layered material and generate a kind of a strictly two-dimensional structure. And we found that the calculated cleavage energy is 2 to 2.5 times smaller than that of the graphene. So that gives us a really promising situation that these materials can be really cleaved to a two-dimensional layer. And this is not only our calculation, a related material where instead of transition metal like copper or chromium, lead has been put. And this is a paper from Science where atomically thin two-dimensional organic inorganic hybrid perovskite has been made, which were lead-based. And this is the plot of the magnetization density shown for this copper-based compound. And what we find that in the inorganic layer, they are completely red, which means the spins and the magnetization density are all ferromagnetically aligned in the inorganic layer. In between the layer, of course, in some cases, it changes from red to blue, but that interaction is actually very, very weak magnetic interaction, as I will show. So what causes this ferromagnetism? So these are basically because of the antiferrodistortive arrangement. This copper 2+ here is Ian-Taylor active. So therefore, it has 2 extremely long bonds and 4 short bonds. And the neighboring copper octahedra has its long bond, which is connected to the short bond of the neighboring copper octahedra. As a result, the magnetic orbital of this octahedra has a kind of a 90-degree orientation to the magnetic orbital in the next octahedra, leading to a ferromagnetism that is completely driven by antiferrodistortive arrangement.
Yeah, Professor
These are
Dasgupta,
calculated.
you have maybe 2 minutes more.
Yes, I will finish in 2 minutes.
Okay.
So these are the calculated magnetic exchange and also calculated magnetic anisotropy. As I mentioned, that magnetic anisotropy is the most important thing for stabilization of true long-range order in the 2 dimensions. And this magnetic anisotropy comes because of some unquenched orbital moment at the copper site due to very large copper chlorine covalence. In case of the chromium compound, the value of the spin is increased because of its D4 occupancy. In case of copper, it was D12. This one is in case of copper, this was S12. In case of chromium, this is S2. So the value of the spin increases. The magnetic exchange is somewhat decreased compared to copper. But as we will see that the calculated transition temperature will be much larger for the chromium compound. And we did the spin wave analysis of this Hamiltonian, which is the Heisenberg Hamiltonian, but with a generalized form of the single ion anisotropy. And we use the Langshaw's method to calculate the spin wave spectrum. And as you can see, by introduction of finite anisotropy basically opens up a gap in this structure factor. You can see in the S of omega. In absence of this anisotropy, there were no such gap, but with introduction of this anisotropy, the gap opens up. And with the TC, estimated TC, very small, 2 to 3 Kelvin in case of the copper. But as soon as we switch to the chromium compound, we find remarkable increase in the TC. In particular, if we apply a slightly small magnetic field, the TC can be shoot up to about 50 Kelvin, which is in the same ballpark as the chromium iodide compound that I showed. So I think I got a warning from the chairman. So my conclusion or summary slide is very simple. 2D magnetism is just the tip of the iceberg because there are many compounds to be discovered and many new phenomena to be discovered. Thank you very much for your attention, and I'll be happy to answer any question that you may have.
Yeah, thank you very much, Professor Tanushree Dasgupta. Excellent talk on 2D ferromagnetism. I think the session is open for now questions. Yeah, I can see Professor Mohendrian has raised his hand, so you can please go ahead with the question.
Well, Shubhankar is in front of me. It's
he's the organizer, so we can take him later.
Okay. So what is Tanushree? What is the maximum Curie temperature for the copper complex?
Yeah, that was very small. According to our calculation, it's only 2 to 3 Kelvin.
Okay.
But for the
we have the
chromium
results where the TC is about 15, 17 Kelvin.
For the copper compound?
Yes. Well, I cannot tell what
Okay.
is the name of the compound, but I'm collaborating with a chemistry group here where we found the TCs varying from 10 to
So
17
maybe
Kelvin.
maybe the change of that organic group really helps,
Possibly,
because-
yeah. I do not know the
Yeah.
details of the compound. Okay, yeah. I was also surprised.
But that
because
is,
the first time I was working on
I'm very
organic
happy
compound.
to know that. Yeah, but for the, as I said, for the chromium compound, if they can really work on the chromium compound, the TC can be even as high as 40.
The sample was not stable compared to copper
For the
complex.
chromium one?
Yeah,
No,
that's
but
what
the
they told
chromium
me.
compound no, the chromium compound has been made. Whether they can be made in the two-dimensional form or not, that is the thing. Because the bulk chromium compound, the TC is more like 60.
Yes, that I understand. I think I'm not sure about two-dimensional compound. Yeah, okay.
Okay, I
Yes.
think
Thanks very much.
Subankar.
Yeah, very nice talk, actually. I have just a quick question. You said, or you showed rather, that the fullerene molecule, if you boronize it on few sites, you said that it shows 2D magnetism. So what is the underneath mechanism for that?
No, I think you misunderstood. The fullerene example, maybe I was too fast. The fullerene example I showed to impress on you that boronization helps. But for the fullerene with the boronization, what happens, there are these Stonewall's defect, which is basically rotation of one carbon-carbon bond by 90 degrees. And that Stonewall's defect is very important if you want to fuse, for example, two fullerene. So they really, but that comes with some activation energy. So the whole idea is how you can reduce this activation energy so that this fusing process becomes very fast. And what we found by putting boron instead of carbon at this specific site, which actually rotates, you can reduce this activation time substantially from several days to only a few seconds.
Okay,
All right.
Thank you so much.
So I think if there is no question, let me ask a quick question before we move to the next session. So I think in all your, two materials, or two kind of materials that you described, you basically considered of introducing a single ion anisotropy or magnet crystalline anisotropy. But can we think of a problem if you have anisotropic exchange interaction? So is there any literature in this direction where they're talking about also introducing magnetism?
Yes, as I mentioned, the chromium triiodide, the original Nature paper, they thought of single ion anisotropy, but later on it has been proved very categorically because of the iodine and the spin-orbit interaction of iodine. What is the anisotropy present there is not single ion, rather it is more exchange anisotropy. So there are concrete examples of that. And we are currently working on some material, basically relying on this idea or making use of this exchange anisotropy.
Okay, thank you.
There are chromium triiodide is the most prominent example.
So I think, we are, Subankar is there. Yeah, so we have come to the, so now let us, so there is a memento here, online memento. So first of all, we should
Receive the memento. This is the first time an online memento.
I would request this Subankar, at least he has lots of budget. He should make it a physical one and send to all the speakers. So anyway, so a nice talk on 2D ferromagnetism. Now let me read out what this memento tells. So Symposium on Magnetism and Spintronics, Niger, Bhubaneswar, takes immense pleasure in presenting the plaque to Professor Tanushree Saha Dasgupta, SN Bose National Center of Basic Sciences, India, in appreciation for being a valuable speaker to give a lecture on designing 2D ferromagnetism. Thank you, Professor Saha Dasgupta. Thank you very much.
Thank you so much.
Thank you.
So I request all the speakers to kindly log into the frame platform in case there are more questions, at least for 30-40 minutes. And we have already allocated some zones for you. I think for Professor Tanushree Saha Dasgupta, it is zone 2 of room 1. and for Professor Thomas Bruckel, it is Zone 1, Room 1. You can directly click the email which we have sent today. You can directly click, or in the chat box also I have put. Okay, thank you so much.
Thank you. Thank you. Hi, Carlo.
Hi,
Hi.
nice to see you.
Same here, same here.
Hello. Yeah. So I can now, yeah. So Professor Maith has already started it. Hello, good afternoon.
Yeah, good afternoon.
Okay.
So you can see my.
Yeah, it is now well visible.
Okay.
Okay. So let us start this third talk now of this session. So we have Professor Maiti from TIFR, Tata Institute of Fundamental Research. He is a senior professor there, particularly in physics department, and currently is the Dean of Natural Science. And his research is basically focused on this photoemission spectroscopy. He is well known for experiments on photoemission spectroscopy. And he has got many awards and recognition. So he's a fellow for all this academies in India. He's also awarded for Santi Swarup Bhatnagar and Shonna Jayanti. And there are many other awards which are not necessary to be listed here. And his present research activities include topological materials, also superconductivity and correlated electron system. Also, he looks at the surfaces and interfaces by this photoemission spectroscopy. So I think with this brief introduction, I will invite Professor Maiti to please deliver his talk. Professor Maiti.
Thank you, Devkanta, for your kind words. And also, I like to thank Shubhankar and all the organizers for giving me a chance to speak in this interesting meeting. There are many interesting talks which are happening. So anyway, since I have half an hour, so I'll try to finish it in time. Okay, so today I'll be talking about our work on samarium bismuthate. So before I get into the topic, I would like to acknowledge, so the results that I'll be presenting today, these are basically or primarily led by one of my postdoc, Dr. Anup Shakya. So he at present, he's in US now doing his second postdoc. So he basically prepared the sample, studied the bulk properties, data analysis, and so on. And all the RPA studies is done by, again, Anup and Shiv Kumar at Hiroshima in the Shimada lab. So most of the credit goes to these two. And of course, the others are there, like Arindam and Ram, they have helped in data analysis and so on. Samples are prepared with the help of Tamijavel's group in TIFR. Magnetism study was done with the help of Paulos. And at the RPS facility, IK and Kenya was also very, very helpful. So I acknowledge all of them. And this is a RPS facility, which you can say probably one of the best that one could think of at the present time. The energy resolution is 0.26 milli-electron volt, which probably the best achieved anywhere. So this is a laser RPS, which is done with 0.05 degree angle resolution. And we also have studied RPS with standard synchrotron source, where the resolution is of this kind. So I'll try to show both of these results, as well as the bulk studies, which is done here at TIFR. And I acknowledge Yogendra, who helped during the sample preparation at RPS facility, and Hiroshima Synchrotron Radiation Center, HISA, for all the experimental supports, and DAE and VRNS for financial support. Before I get into the topic, I'll try to give a brief introduction about the Kondo lattice systems and their properties, which probably will help to the non-experts to get into the topic. As you know, that impure metals have been really the mysteries for the physicists for many, many decades. So what we mean by simple metal is that you have the lattice well ordered, there are very little defects and so on. So if you have a highly itinerant electrons or conduction electrons that can move freely, the only impedance can come because of the lattice vibrations and so on. So that way, the resistivity primarily driven by the thermal vibrations of the lattice sites.
So if you reduce temperature, the resistivity of course will reduce, and a typical metallic behavior is shown here. Now, if you have an impurity, then the complexity comes, which is often found in most of the materials. And if the impurity again is magnetic, then the problem becomes much more severe. So for example, I talk about a magnetic impurity here in a good metal. So if you have an electron of upspin and impurity is downspin, then when it crosses through this side, there is a spin flip scattering. Of course, if there is no spin-spin interaction, then the effect will not be so significant. But if there is a spin flip scattering, then what happens is that the resistivity or impedance will change. So this is called actually Kondo scattering. This kind of scattering, the intensity would depend on the how this local moment is coupled with the conduction electron state. So this basically they are supposed to be talking to each other, then only they will influence each other. If you reduce temperature, this kind of coupling becomes stronger, and at certain temperature, what happens is that this conduction electron, which were actually getting scattered randomly, will actually form a singlet kind of states with the local moment, which is called a Kondo cloud, which has a effective extension, which can go up to micron order depending on the materials. But anyway, the moment you have formed this Kondo cloud, you can see that the conduction electrons will no longer see this kind of magnetic impurity. So the scattering will be minimized, and the resistivity, which was actually going up at low temperature because of the Kondo scattering, will get saturated, and you see that the resistivity flattens out. So the specific characteristic of a Kondo material is that you have a metallic behavior at higher temperature. The moment you reduce temperature, there is a coupling between the conduction electron and the local moment, which becomes stronger and stronger, and at low temperature, when the vibrations are less important compared to the scattering, so you get a resistivity minima and the resistivity goes up. And the moment you have a Kondo singlet formation, then you see that there is a flattening of resistivity. Okay. Now, if you have, say, this magnetic moment at each and every side, what happens is that these Kondo singlets, they can form a coherent states. So once they are formed, they formed a coherent states, then what happens, the resistivity can go further down. So the temperature below which this coherence happens is called coherence temperature. There are many phase diagrams which are there. I'll show you one of them, which is essentially shown as a function of temperature and the Kondo coupling strength. So at a lower coupling strength, the magnetic moment survives, and you see a typical from paramagnetic to antiferromagnetic transition, like you see in a typical magnetic material. Above a critical coupling constant, what happens is that there is a Kondo singlet formation. So the magnetic moments are actually get compensated completely, and you get a typical Fermi liquid kind of behavior. This critical coupling is called the quantum critical point. And the more the coupling is there, the Kondo temperature goes up. Okay. So, so if you look at from the electronic structure point of view, you can see that there are local moments which gives you magnetism, and there are conduction electrons which forms the Fermi surface. The moment there is a Kondo singlet formation and there is a Kondo coherence, then what happens is that the local moments, since they are hybridized with the conduction electron, they also start contributing in the Fermi surface. So the size of the Fermi surface becomes big. So if you go across this quantum critical point, it is expected that the Fermi surface will expand. Okay. Now, now you can have a different scenario where this Kondo temperature at the critical point is non-zero. Okay. So this means that even if you have reached to this regime where there is a local moment is there is a compensation due to Kondo effect, but the magnetic moment may not have been completely compensated. So there you have this kind of a scenario which is like itinerant magnetism, where you get spin density wave kind of states and so on. So this kind of criticality is, that's the reason defined as spin density wave quantum criticality. The cases where the Kondo temperature is zero at the critical point is called local criticality. If you look at from the electronic structure point of view, so if there is no magnetic impurity or there is no impurity, the typical metal which has this energy and the density of states, and there is a Fermi level which is the highest occupied level, and you get a metallicity. Now, if you are at a pretty high temperature, much higher than the Kondo temperature, even if you have a magnetic impurity, you do get density of states and there is some scattering, so that gives you some additional contribution maybe, but that's not really so strong. But if you go to a very low temperature where the coupling is very, very strong, so then there is a strong hybridization of this local moment with the conduction electrons. So because of that, you see this bonding, anti-bonding kind of scenario that you see in chemical kind of materials. So where you see a sharp feature because of the F character actually growing up at the Fermi level. So if you reduce temperature, this intensity goes up. Now you can immediately see that the number of electrons or carriers at the Fermi level is much larger compared to this. So that's actually is called expansion of the Fermi surface. Unfortunately, there are a lot of experiments have been done by spectroscopy, and this Fermi surface expansion has not been observed. If you see a big Fermi surface like this, it continues to be there even if you are going to a very high temperature, much above the Kondo temperature. If you see a small Fermi surface like this, I'm not going to the details here because the today's topic is somewhat different. So, but anyway, it continues to survive like this. So people have started actually talking about different kind of scenario which can take care of this Kondo kind of minima, and the Kondo physics is not really operative. So, I mean, there are different alternative suggestions are there. Let's look at the scenario once again in a different way. So you have this conduction band and the local moment which is there. So if you are thinking of, don't worry about this terminologies which are used. I'm not really going to use any equations or anything. So one can actually define this state as F1 state because you have one electron in the F band like cerium for example, in a simplest model, and you have this conduction electron. Now, if this F state is hybridized with the conduction electronic states, so you can have a scenario where the conduction band is populated by this F electron, means that the F electron has hopped to the conduction band, and you get a scenario like this. The other scenario which can happen is that one of the conduction electron or conduction electronic state actually is entangled with the F electronic state, which can be expressed notionally like this. So this is essentially a Kondo singlet state. So if you have this heavy fermion systems, you can have all the kind of contributions in the ground state. So all these three possibilities are there, and the ground state can be actually expressed like this. So all the physics that we talk about, like heavy fermion physics or Kondo physics, it's essentially involved how the F electronic states or F level is hybridized with the conduction band. Okay, so the hybridization is the most important thing. So if you are doing experiment or if you are doing theory, most of the time what you try to do is that you try to study the hybridization of F states with the conduction band and see how it evolves with temperature or various other experimental parameters. Okay, so let's look at this hybridization physics a bit more. So assume that this is your conduction band, okay? And this one is the band structure, this is energy, this is the K, and this can be D states, or like if you are cerium or any rare earth kind of systems, you have 5d 6s electrons, they form the conduction band. If you have intermetallics and so on, they are also, you'll have D or E-like states which contribute in the conduction band. And the local moment comes because of the F states, which are actually localized because their behavior is more like a core kind of, or shallow core level kind of, because their radial extension is pretty small. Now, if they're hybridized, what will happen? So you expect that at the crossing, a gap will open up. This is like, this kind of gap will depend on the hybridization strength between F and conduction electrons. This is similar like a nearly free electron description in solid state physics, if you look at it. So now if your electronic structure is such that one of the band is completely filled and other is completely empty and the Fermi level is lying in between, then this gives you insulating behavior. These are called Kondo insulators. These materials actually have drawn a lot of attention recently because of this fact you know, the hybridization gap here in various Kondo material that goes of the order of say 10 milli-electron volt. Many systems which are shown, so 2, 3, 4 milli-electron volt or so. Kondo temperature is not really very high in most of these systems, like say 35 to 100 Kelvin or so. Now the spin orbit coupling is very, very strong for the F electrons because they are highly local. So that can be of the order of say half a electron volt. So if you compare with the gap, hybridization gap, the spin orbit coupling is infinitely large for this. Now you see that carefully look at the crossing. The F level, which has the orbital angular momentum is 3. So if you look at the parity, it has a odd parity. And for the D states, which forms the conduction electrons, they can be even parity. Of course, you have P states which can have odd parity and so on. Let's talk about the even parity. So if you have a crossing, so or the hybridization, what happens is that you are going from a even parity to the odd parity and so on. So there is a easy way of having band inversion in this system. So this Z2 index that we talk about in topological materials, so that can be realized in these materials very easily because a band crossing means you are essentially changing the parity. So that's the reason these Kondo materials have been looked at very extensively for the topological properties. Now, what is the advantage compared to the typical topological materials like Di2, Se3 and so on? So those are simple insulators and the surface states are protected by inversion symmetry and time reversal symmetry that gives you topological protection. In the Kondo systems, they are highly correlated and the hybridization of the F states with the D states actually derives the material properties. Now at higher temperature, they are simple metals. So you don't have a gap, you don't have topological property, and you cool down at low temperature when there is a gap opening up, you see this topological behavior. So you can actually realize interesting physics just by changing the temperature from a normal kind of scenario to exotic ground state. Okay. There are many Kondo insulators have been known for many years, like SMB6, samarium sulfide, YB12, and so on. So there are Kondo semi-metals are there. I'm not getting into that. The most extensively studied material is samarium hexaboride, because this one is known for, I think, since 1970, that it's a Kondo insulator. There are controversies in terms of properties of samarium hexaboride. It has been studied extensively by ARPES, and of course, it's not really known whether you have a topologically trivial ground state or topologically non-trivial ground state. Without getting into that, today I'll be talking about a material which is samarium based, because we feel that samarium is a good material to realize a Kondo kind of scenario. At the same time, you also can realize topological properties. So samarium bismuthate, it forms in rock salt structure. It's extremely good crystal that Anu prepared. You can see from the Laue kind of dispersions. So if you look at the magnetization data, this is magnetic susceptibility as a function of temperature. At higher temperature, it's more like a typical paramagnet. But if you go more and more towards lower temperature, you can see that it deviates from this Curie kind of behavior, and you see some kind of a hump, probably due to this Kondo kind of compensation. And there is an antiferromagnetic transition. There are two antiferromagnetic transitions at 9 and 7 Kelvin. If you look at the resistivity, you see that normally at higher temperature, they're metallic, and you do see a resistivity minima that I have shown earlier in the schematic, like a typical Kondo kind of system that exhibits. Now, of course, you can have a minima and rise in resistivity due to similar scattering by impurity and so on. So you need to look at this temperature dependence of this curve, and that has been similar fitted, and we see that it follows this log T kind of temperature dependence that is typical for a Kondo system. Now you also see a peak at 9 Kelvin due to antiferromagnetic ordering. At low temperature, they are much more complex. But the most interesting thing is that these materials show quantum oscillations even at a very, very small field. Like, for example, if you are doing at 1.8 Kelvin, even 1.1 Tesla gives you quantum oscillation. So which is really very, very interesting and shows that this material has a small damping. So the material quality is very, very good. So we have studied this DHDA kind of oscillations as a function of temperature. You can subtract the magnetic background from this and extract the oscillations. So they look like this. and you see that they are strongly temperature dependent. The most interesting thing is that all these oscillations are actually within the antiferromagnetic phase. And you go to 8 Kelvin or so, they all dies down and there is nothing that could be seen. So the different parameters that we have obtained from the first Fourier transform of this. So you see that our data, which is collected up to say 7 Tesla, that shows signature of 3 Fermi surfaces. The field is applied along the C direction. So basically, as you know, that this DHBA kind of oscillations happens because of the Landau level formation at high magnetic fields. And the Fermi surface that contribute in these kind of things are having a finite cross section perpendicular to the magnetic field direction. So here, these 3 Fermi surfaces that you see, they are of the size like this. The area can be of this order, and there are different parameters that we have estimated. So this effective mass is pretty small, which is from close to 0.3 in these kind of materials. Now we can actually, to understand this, we can compare this with the band structure results. I'm a little bit rushing fast because I have to go to the RPS data, and I think 20 minutes is done. Okay, so if you look at the band structure around gamma point, you see that there are 2 hole pockets. Why we call hole pocket? Because you know the contour it enclosed the Fermi pocket are actually filled by unoccupied levels. You see they are all above the Fermi level. So that's the definition of a hole pocket. Now, if you have a contour which forms the Fermi pocket and encloses K points which are occupied, that's called an electron pocket. So we have 2 hole pockets from the band structure calculation. They are shown here. One is star-shaped, this is pink one, and there is a green one which is spherical inside the star-shaped Fermi surface. And there is an electron pocket which is at the zone boundary, which is formed by this band. Okay. Now it turns out that, I mean, it may seem that, okay, fine, these are the 3 pockets might be seen in the experiment of DHBA. But if you compare the numbers, like the cross-section of the Fermi surface and the corresponding values, you see that the electron pocket, which is about 372 Tesla, matches with one of the Fermi surfaces that we have detected from DHBA, and the effective mass also is matching pretty well. So what we see that this electron pocket contributing to the DHBA kind of oscillations are essentially this. This is the one which is this F gamma, and the other 2, which has a much smaller size or pocket size, are probably because of the surface electronic structure. Now, the 2 hole pockets that you see at the gamma point requires much higher field to capture in the DHBA kind of scene. So we have not really seen them because of that probably. Now, if you can calculate the Berry phase for various Fermi pockets that you have seen, that the F beta shows a Berry phase pi equal to pi. So it shows that it's a non-trivial kind of Berry phase. So this clearly, it suggests that there could be a topological kind of states, surface states in this material. Okay. If you look at the band structure a little bit more carefully, so these are the different band characters are plotted. I'm not going into the details of that, but you look at this band crossing here. You see that this is the bismuth 6p states, which is coming like this. And these are the D states, samarium 5D states. And actually, although in this plot, they're looking like they're crossing, but there is a gap between them. And you see that the character of these bands, so this goes from samarium D to, so this red is samarium D and this one is bismuth P. So you can see the band inversion kind of scenario that we expect are visible pretty clearly in this. Okay. So even the band structure shows that these are expected to be a non-trivial kind of topological material. Now let's look at the RPS data. So this is the Fermi surface plot, and you see that at the gamma point, you have this star-shaped kind of Fermi pocket, which is expected, the pink one, and there is a spherical one here, which is the one which is inside this, I have not shown here. And this Fermi pocket, which corresponds to the ellipsoidal the electron pocket, which is seen. So this more or less matches with the DFT calculation results. You see that the K points that we have shown here, this is the surface Brillouin zone, and this is the bulk Brillouin zone. The X point, which is this diamond or the square surface center, is defined as M bar on the surface. So the surface Brillouin zone high symmetry points are denoted by bar, and the bar is not there for the bulk Brillouin zones. Similarly, gamma is gamma bar here, and X bar is basically the middle of the edge. Okay, and the Kx, Ky is defined that way. So it's shown here. Now, if you do the same Fermi surface plot with a lower photon energy, these are all synchrotron data. You see that the star-shaped one is seen, the electron pocket is also seen here, and this Fermi surface is also seen here, whatever is seen here. There is an additional pocket which would not be captured in the DFT bulk band calculations. So this could be the surface band, which I'll show you the signature later. So that actually is the surface band. Now, if you look at the band structure along gamma M bar, which is this gamma and M bar, so this direct K vector, and we have collected this band structure at a different photon energy. So you see that you have these two bands which are seen here, which are also seen in these two bands around gamma. Okay, these two bands which are seen here, so we can see these two bands. This kind of band inversion that I have talked about, this is also clearly visible here. So the DFT results seem to match well, and you change the photon energy, of course, you see the signature. Of course, their K values will shift because they have a dependence along the K. So if you change the photon energy, if you go to higher photon energy, the Kz will increase from, you can calculate it from RPS. So that way, the K will of course change because of the three-dimensionality of the electronic structure. In addition, what we see that there is a Dirac cone kind of feature at gamma point. M point is not so clear here, but if you look at higher photon energies, so you can see that I have put it some circles. So you see that Dirac cone is there at M bar, Dirac cone is there at gamma bar. Okay, so there is a clear Dirac cone observed at these high symmetry points, gamma bar and M bar. This is shown very clearly in the energy distribution curves. So this is the band inversion. You have the bulk bands, all of them, which is seen here. In addition, you have a surface band showing the Dirac cone. This is done at 35 eV photon energy. At 90 eV, you can see the same thing. If I show in terms of lines, you see that clear Dirac cone is there with a Dirac point. Now, what we have done is that we have plotted the density of states at different photon energy at the M bar point. And this peak shows the Dirac point, and we see that at different photon energy, the Dirac point is not shifting. So this shows that actually this Dirac point is independent of Kz, means that they are surface states. So if you have the bulk states, there is the dispersion as a function of Kx, Ky, and Kz, but when you go to the surface, you have this translation and symmetry breaking along the surface normal, and you see that the Kz dependence is vanished. Okay, this is clearly seen here that here I have plotted as a function of Kz. Let's not go into the details. Here I have plotted the same bands close to the gamma point with much more clarity along gamma X bar. So we have seen in this plot that there is a Dirac point, and it is two-dimensional like the surface states that you expect at M bar point. And but now let's look at the gamma point much more carefully. Okay, so there is,
you are kind of done with the time slot. So
yeah, this 28 minutes I can see. Yeah, I'll finish in another 1 or 2 minutes. Yeah. So there is a clear Dirac cone you can see at gamma bar point also, and this is visible at low temperature. So this is the reason we wanted to look at much more carefully using extremely high, ultra high resolution photoemission spectroscopy by laser RPS. So here the energy resolution and angle resolution is the highest that could be achieved so far, which is about 0.26 milli electron volt. And you see clearly there are 3 Fermi surfaces are observed at 15 Kelvin. The outside one is of course the bulk Fermi surface, and there are 2 Fermi surfaces due to the surface. So this DHBA oscillation that showed these 2 Fermi surfaces due to the surface probably link to these two. Now, interestingly, if you go across the antiferromagnetic transition, which is at 9 Kelvin, you see that one of the Fermi surface somehow as if vanished. So normally, if you have an antiferromagnetic order, so there is a destruction of Fermi surface. Now, if you look at the bands, you see that there is a clear Dirac cone is seen. So these are the surface bands. So this is surface band, and they form a Dirac cone. So you have a Dirac cone like this at one point below the Fermi surface, below the Fermi level, and above, and they are crossing. So there are something like that. So this kind of scenario is seen. The most interesting thing which people have, I could say, smoking gun kind of result, which people have not seen, the influence of antiferromagnetic order in the Dirac states. Okay, so you look at 6 Kelvin data. You see here along cut 1 in this direction. At 15 Kelvin, there is no magnetic order, and you see these surface bands are crossing nicely. But if you go to say low temperature below antiferromagnetic order, you see that there is a bending. So as if that there might be a gap opening up at this crossing, so at finite momentum. But at gamma point, there may not be much change. So this we have looked at very, very carefully. Now I'll show you here. So this momentum distribution plot shows clearly there are 3 Fermi surfaces, 1, 2, 3 peak. One of them vanishes if you go to antiferromagnetic order. So probably the destruction of Fermi surface. The most interesting thing is that the Dirac cone that you see actually is gapped. So this is the energy distribution or spectrum along the gamma point, and you see there is 2 peaks separated by some energy. Now, if you go to lowest temperature, so this line is the lowest temperature, the peak shifts slightly by 11 milli-electron volt to higher energy. But if you shift them back and overlap with the higher temperature data, they match almost identically. So it looks like that the behavior of Dirac fermion survives within the antiferromagnetic order, but there is a opening of gap at the crossing of the 2 lines, surface bands, which are at finite momentum. So this is very interesting, I think, and probably exotic, and I'm not sure, I mean, it has been observed earlier like the antiferromagnetic order in this kind of topological materials. So the real conclusion is that SMBI is a Kondo metal or Kondo lattice system which exhibits 2 antiferromagnetic order at 9 and 7 Kelvin. The 7 Kelvin and 9 Kelvin, of course, this has to be understood much better by neutron diffraction and so on. But what we see that this is a material which shows 2 types of coexistence of 2 types of Dirac fermions. One is that where the Dirac cone is not gapped, which is at the M bar, and there is another Dirac cone which is at gamma, which is gapped, like the heavy Dirac fermions that people often talk about. And if you have antiferromagnetic order, it appears that the behavior of the Dirac fermions survives within the antiferromagnetic level. Of course, there is a gap opening up at the crossing of the linear bands, which is not at the Dirac point, but away from the Dirac point. Thank you very much for your kind attention.
Thank you very much, Professor Maiti, for a nice, exciting talk on this topological material, magnetism, coexistence of magnetism, and this topological materials. So now the session is open for questions and comments. There is a question from Anamitra. Please go ahead.
Hello, Professor Maitri, very interesting talk. I just had a quick question. So in materials like samarium hexaboride, I mean, there are these theories of spin-on Fermi surfaces and gapped charge excitations.
Yes.
So I'm just wondering, I mean, what is the status of the theory from the experimental side? In the sense, are these theories still holding, or is there a way to tell apart?
Okay, I would say that I don't really believe those. You see, the thing is that when you have certain experimental observations, like SMD6 is supposed to be insulating, Kondo insulator, but you see that there are signature of metallic kind of behavior is seen, like you have specific heat contributions, then these quantum oscillations and so on. So that way there has been several theories, and one of them is this spin-on charge excitations, different excitations. But if you look at very, very carefully, that actually it seems the band structure itself, I mean, if you, which we have also published a paper where Anup is the first author. So where we see that actually this is a very weak kind of metallic material. If you look at even the DFT calculations, Fermi energy is very, very small. So if you have small amount of disorder, you can get this kind of temperature dependence that people have observed experimentally. So as far as I am concerned, I would not say that those separate spin and charge excitation theory is valid in this or required. I don't say that it's valid. I would say that it's probably not required to explain the samarium hexaboride.
I see. Sure, thank you. Thanks.
Yeah, so there is a question from NH and AN. Please go ahead.
Sorry, thank you for this. This is Ashish actually from NICER again. Sorry, and it's a very good talk, Kaloda. And so the question is regarding that you have two Dirac cone at the gamma point and M point. So is it a weak topological insulator? And this gap is this Dirac cones are in the same energy gap is coming, or two different bands is coming? So whether it's a strong topological.
No. This is, you see, this is a metal, first of all. I mean, you can call it a, because these are not insulating. So the M point, the Dirac fermions, they are different from the ones that you see at gamma point. Now, okay, I mean, the gamma point Dirac fermions, they are gapped. So there's, I mean, effective mass could be somewhat larger. So that's the reason they are called heavy Dirac fermions. And the surface states that form the Dirac cone at M bar point they are different and they are ungapped. I would say that way. Now, if you,
so is it related like one is bulk Dirac cone and another is surface one?
No. Both are surface. Both are surface.
Okay, both surface. Okay.
Both are surface states because you know in the bulk band structure you don't see them. So they are both surface states, but there are two kinds of Dirac states that is found. Now, this may not be very much special to this correlation effects of samarium bismutate, because if you look at LABI, they also show a similar Dirac cone at M bar point and gamma point. The advantage of SMBI, why I'm excited, is that, okay, in LABI also you see a gapped Dirac cone at gamma point and at M bar point ungapped one. And so that way it's clear that the surface states that forms the Dirac cone are actually coming from the conduction electronic states at the surface. The advantage of SMBI is that it helps you to look at the influence of antiferromagnetic order on the Dirac states.
Okay. Yeah.
So that was very, very special to us.
Okay, this is a question from.
Thank you.
Yeah, there is a question from Su. Su. Could you kindly go ahead with your question?
Yeah, please.
Okay. Yeah, thank you. Very interesting talk. Very clear explanation for the quantum physics. I really enjoyed to hear your talk. I have a question. Since I'm a neutron scatter, okay? A curious question is because, you know, for the whole scenario you are proposing or argue for is about the presence of antiferromagnetic ordering. Is there any evidence come from the, let's say, neutron scattering that I know, of course, samarium is a extremely toxic element to do neutron scattering because of its strong neutron absorption. But there is a way, for instance, you could do isotope. Okay, instead of normal, you could do isotope enriched samarium. So that might pave the way for some neutron, because that would be very interesting. Okay, I see.
Absolutely,
you know.
absolutely. Yeah, I agree with you. As far as I know that, I mean, there is no neutron data. Maybe I have to look at it more carefully. But I completely agree with you that, I mean, one can find a way out and look at the magnetic phase more carefully. That will help us much better. Absolutely. I agree with you.
All right. So before ending this session or this particular talk, let me ask you a quick question. This which you pointed as smoking gun evidence, this proximity of antiferromagnetism to, but you are not seeing any opening of a tiny gap in your electron spectra. But there are many, hybrid systems where people are interfacing an antiferromagnet to a topological metal, either in thin film or other thing. So what do you think? Why is it that the magnetic antiferromagnetic, that exchange interaction is too small, which is not affecting, or what is the kind of idea why it's not opening up a gap?
Okay, I mean, the question is that, thanks for the nice question. So the antiferromagnetic order influencing the electrons which are forming the linear bands, we have seen a gap, but at a finite momentum. But at Dirac point, there is no effect that we observe. Correct.
Yeah, that is more exciting.
Yeah. So at Dirac point, there is no effect that we observe. I think we have to look at, I cannot say exactly what could be the microscopic origin for that. You see that maybe we can discuss more.
Yeah, I think that's a very interesting
experimental observation for us. We have to actually study much more what happens because of the antiferromagnetic water on this. But in the heterostructure, of course, I understand the proximity of magnetic moment. So on the topological states, surface states or interface states, there what happens is that until this magnetic ordering actually breaks the time reversal symmetry or crystal symmetry that protects the topological order, okay, so you will have the surviving Dirac fermions. So the moment you have this time reversal symmetry, like plus k minus k, the energy actually is same. So the moment you break that, then you will not get the Dirac fermions. So it all depends on the magnetic interaction of the magnetic moment with the Dirac fermionic states. So as you already noticed, mentioned that probably the interaction is not strong enough to break the time reversal symmetry and inversion symmetry that protects the Dirac fermionic states.
Yeah, I think that's very exciting.
Yeah.
So thank you very much, Professor Maiti, for a nice talk on this coexistence of magnetism, Dirac electron spectra, Kondo system. So thank you very much. Now I think I will give this to Subhankar. I think he need to flash something.
Yeah, I think, Abhishek, can you please share the digital plaque?
Yeah, so we have the pleasure in giving you this online memento on behalf of the organization. So let me just read it out. So Symposium on Magnetism and Spintronics, Niger, Bhubaneswar, takes immense pleasure in presenting the plaque to Professor Kolavaran Maiti, Tata Institute of Fundamental Research, in appreciation for being a valuable speaker to give a lecture on antiferromagnetism in a topological Kondo system, SMBI. Thank you very much for this nice presentation.
Thank you so much. Excellent talk, Karoda.
Thank you. Thanks a lot.
Yes.
So I think we will switch on.
I think I just have to mention that I see more hands. Maybe after Professor Sampath Kumaran's talk, there is a poster session and a break. During that time, if the invited speakers are still around, I request you to log into the frame, and probably that time people can discuss. I tried doing discussion together with Zoom in the same computer. It's actually cumbersome. So maybe we need to go out of Zoom and discuss there. So that time I request you, Kaloda, if it is possible. I think there are more people who want to discuss with you. Okay, Kalpataru, please start.
Okay.
Thank you, Kaloda. Thank you.
Yeah, so let us go to the next talk, which will be given by Kalpataru Pradhan. So Kalpataru Pradhan is a faculty member at Saha Institute of Nuclear Physics, Kolkata. And his research expertise or research interests mostly focus on physics at the interface of ferromagnetism and insulating layers in transition metal oxides, and also digital-induced magnetism in graphene. So I would request Pradhan to please present his talk. You can probably make full screen.
Yeah, so can you hear me now?
Yeah.
Yeah, thank you, Professor Samuel, for the kind introduction. And I would like to, before I start, I would like to thank the organizers, especially Professor Subhankar Vedanta, for inviting me to this nice conference. Okay, so let me start. So the title of my topic is Inverted Hysteresis and the Exchange Bias in Ferromagnetic Heterostructures. This is so I don't know, it's moving automatically. Okay. Okay, sorry. And so mostly in our group we study about the interface between ferromagnet, between ferromagnet and ferromagnet, between ferromagnet and antiferromagnetic. And recently we have started studying about the insulator interface also. So this ferromagnet and antiferromagnetic interface are basically interesting because of the spintronic application. Also, we are mostly interested because of the basic physics, and so physics are the interface. And the physics at the interface is complicated because of the charge, lattice, orbital, and the spin degrees of freedom. And these degrees of freedom, because give rise to this delicate magnetic and electronic phases. And this, because of this electronic and because of this, so we find electronic and magnetic reconstruction at the interface. So these complicated things should be studied with rigorous level study, microscopic level. So mostly today I will discuss about the LSMO and the SRO interface. So LSMO is a ferromagnetic metal, and the SRO is also a ferromagnetic metal. And for this study, the ferromagnetic heterostructure study, so we'll use the model Hamiltonian calculation. Basically, we use spin fermion Monte Carlo calculation, which are the kinetic energy, coupling, super exchange, electron phonon coupling, and sometimes the Hubbard repulsion, and importantly the disorder. But in our group, we also study different kind of magnetic materials, 2D materials, and clusters, and we use sometimes DFT, mostly use VAS. But so we use both DFT and model Hamiltonian calculation for the magnetic calculations. And so we also value our experimental collaborations. So mostly we have in-house experimental collaboration at SINP, and we also have collaboration at NICER and different IITs. So to start with, before I go into the main topic, so I thought I will give a glimpse of what we do in the 2D materials and clusters. So recently what we did is that we took a HBN 2D surface, and we doped this HBN with 4 carbon rings. You can see these carbon rings here. So we have doped the HBN with 4 carbon rings. So 1, 2, 3, 4 carbon rings are there. And we studied this system heterostructure. This is one kind of heterostructure, I can say that HBN and carbon heterostructures. And we studied the band gap with different doping concentration. This is 4 carbon ring. If this is a clear HBN, so the band gap is 4.5 eV. And if it's a 4 ring structure, it's 2.2 eV. And if it's a 9 ring structure, the band gap decreases to 1.22 eV. And if it's 16 ring, it decreases further 0.7 eV. And so then our main important study was to manganese dimer on this complicated heterostructure. So we studied the manganese 2 on the different ring doped HBN. And because of this band gap changes, we want to see how the charge transfer. So there will be some, there is definitely binding energy between the manganese 2 supported on this HBN cluster, and the binding energy is good enough. And we see that the charge transfer, we studied the charge transfer, from the manganese to this heterostructure, manganese to this HBN, carbon doped HBN. And the charge transfer for zero electric field without any application of electric field is largest for this 16 ring structure. So and the band gap is smaller here. And if you keep on doping, this will be a graphene, but we doped up to 16 ring only. And this is 8x8 cluster done calculation, DFT calculation. And we see that at electric field, zero electric field, so this 16 ring is there is a large charge transfer, and if you apply negative electric field, the charge transfer increases, and if you apply a positive electric field, the charge transfer decreases. And what this has some consequence on the magnetism on the manganese 2 supported on this 2D surface. We see that if there is a large charge transfer from the manganese to the 2D surface, it becomes ferromagnet. And if there is hardly any charge transfer, of the charge transfer is very small, it remains antiferromagnetic. And let me tell you that manganese 2 as a dimer, it's antiferromagnetic. So if there is a charge transfer from the manganese to this HBN surface, it becomes ferromagnet. And if the charge transfer is very small, it remains antiferromagnetic. So at zero electric field, some of the clusters remain antiferromagnetic, and if you apply magnetic electric field, it becomes ferromagnet. So one can apply electric field to control the magnetism, and this is basically depend upon the charge transfer. So the means the magnetism is controlled by the charge transfer. So this is a glimpse of the 2D material and clusters we do in our group. So I'll go to the plan of the talk of the today's, this is the main plan. So we'll start with LSMO and the PCMO like material, which is a ferromagnet and antiferromagnet. Then we'll go to the what is exchange bias. Then we'll come to the LSMO and the SRO structure. So we'll start with ferromagnetic and the antiferromagnetic oxide heterostructures. And theoretically, what we studied is that antiferromagnetic insulators sandwiched between ferromagnetic and ferromagnetic material. And what we see that there is charge transfer from the ferromagnetic material to the antiferromagnetic insulator. So you can see that if the initial electron density was 0.5, so at the interface, there is charge transfer from the ferromagnetic material to the antiferromagnetic insulator. And because of this charge transfer, what we see that there is a magnetic del layer kind of thing at the ferromagnetic interface. So the ferromagnetic interface, the magnetism at the interface decreases, and we somehow loosely call it a magnetic del layer. And because of this magnetic del layer, the spintronic device, tunnel magnetic junctions, which are expected to be ferromagnet with an insulator, there are some magnetic del layers present in the actual reality. And in 2007, this paper, what they did in experimental wise, what they did is that there's a ferromagnet, two types of ferromagnet, LSMO and LSMO, and they sandwich the PCMO in between. And they see that the magnetism in the PCMO increases non-monotonically. So first, in the width of the PCMO increases, the magnetism increases in PCMO. This is the magnetism in the PCMO, the antiferromagnetic insulator layer. So the magnetism increases, then it decreases. So this is non-monotonic. So in our theory calculation, we also, this is a 2D calculation. So we're doing the 3D calculation presently, and we can see that because of this, the magnetism in the antiferromagnetic insulating layer, 24 by 24 lattice, the magnetism in the insulating layer increases and then decreases. And then we see that because of this increase in the magnetization in the antiferromagnetic layer, we see that the del layer, the magnetism at the interface of the ferromagnet increases and then decreases. So we call it for W equal to 2, there is no del layer. For W equal to 1, 3, 4 kind of thing, W is the width of this antiferromagnetic insulating layer. For W equal to 2, there is no magnetic del layer. For W equal to 1, 3, 4, and all others, there is a magnetic del layer. So now we'll come to the exchange bias in the oxide heterostructure. So this is like a glimpse of what is exchange bias and what we are actually studying. And let's say there is a ferromagnetic material and there is antiferromagnetic material, and there is strong ferromagnetic coupling at the interface. So because of this strong ferromagnetic coupling at the interface, we'll get a negative exchange bias. And this is the cartoon from this microscope. And this is the exchange bias, which is negative, and the coupling between the ferromagnet and antiferromagnet is ferromagnetic. And recently, from Rana group, which is in Bhopal, so we see that so they are coupling between iron and SM cobalt. This is a ferromagnet and this is the antiferromagnetic bilayers, and this was done in way back 1956. And because of we get a negative exchange bias, but this is very old, 1956, but recently, maybe 10-15 years back, so the positive exchange bias was discovered, and this is between iron and Fe2. This is a ferromagnet, this is antiferromagnet, and recently in 2004, so the positive exchange bias was discovered in LSMO and SRO, and both are ferromagnet. So it started with ferromagnet, antiferromagnetic layer, negative exchange bias, then in 96, ferromagnet, antiferromagnetic, positive exchange bias, then LSMO, SRO, ferromagnet, positive exchange bias. The main point to see is that here the ferromagnetic, antiferromagnetic bilayers, the interaction between the layers, ferromagnetic and antiferromagnetic, is ferromagnetic. But here, the interaction between the ferromagnetic layer or the next layer is antiferromagnetic. Because of ferromagnetic interaction, we get a negative exchange bias. Because of the antiferromagnetic interaction, we get a positive exchange bias. Then we come the actual system we are studying, LSMO and SRO heterostructures. And so Devakanta, can you hear me?
We can hear you, no problem.
Yeah. So this is the LSMO and SRO heterostructure. And so it was chosen that LSMO, which is a soft ferromagnet, that transition temperature is 300 Kelvin, and SRO, which is a hard ferromagnet, and you can see this is hard ferromagnet, and this is LSMO is a soft ferromagnet, and the TC of SRO is 150 Kelvin. So there are two types of ferromagnets. So if you join them, basically we give, because of the antiferromagnetic interaction between LSMO and SRO, at the interface, we get a positive exchange bias, and this is reported in APL 2004. And why LSMO SRO heterostructure? Because of the good quality heterostructures one can prepare between LSMO and SRO. And main property of LSMO, it is half metallic, and SRO as a material is very complicated, and we need some complications also. So what are the properties? Properties are like AFM interaction at the interface, as I told you. So the interaction between the LSMO and the SRO at the interface is antiferromagnetic. What I mean, so at high temperature, both LSMO, L is LSMO and S is SRO are paramagnetic. At the temperature like 300 Kelvin, the LSMO is ferromagnetic, but SRO remains paramagnetic kind of thing. But at 50 Kelvin, 150 Kelvin or so, both are ferromagnetic. LSMO is ferromagnetic, SRO is ferromagnetic, but they are aligned antiferromagnetically. And what is inverted hysteresis and double flipping? And for this, let me show you a cartoon. So if you apply very large magnetic field, the LSMO and SRO are ferromagnetic. But if you decrease the magnetic field, the soft ferromagnet LSMO switches fast. So it becomes antiferromagnetic before the magnetic field hits 0. And if you decrease the magnetic field further, both the ferromagnet aligned in the magnetic field direction, and so it goes from up, down, and down. So there's and you can see inverted hysteresis loop here. So the magnetization is antiferromagnetic before the magnetic field goes to 0. And what is the double flipping? Double flipping, here I tell you that the soft ferromagnet LSMO switches first, but here you can see that cartoon picture. So if you apply a very large magnetic field, both are ferromagnet. But if you decrease the magnetic field, the SRO, which is the hard ferromagnet, switches first, and then again the magnetic field decreases below 0. Both the LSMO and the SRO flips each side. So this up goes to down, and this down goes to up, and again if you decrease it further, both goes to down. So this is like a double flipping kind of scenario, and this happens at 100 Kelvin. The only difference between these two experiments, one is done at 10 Kelvin and another is done at 100 Kelvin. And this is inverted hysteresis, and this is what we call double flipping. And this is the main thing we want to explain or understand in our theoretical calculations. And what else? So there's an insulating behavior for the metallic bilayer. So both SRO is a metal and the LSMO is also metal, but if you join them, LSMO and SRO, they behave insulating. So this is because the manganese and the ruthenium, which are the transition metal elements, and you can see that there's electron can hop from one atom to other atom like a double exchange scenario if both are antiferromagnetic. If they are ferromagnetic, this hopping is not possible, and that's why if you both have LSMO and SiO are ferromagnetic, the conductivity is small. If they're antiferromagnetic, conductivity is large. This is inspired from this experiment. So what is finally that if they're antiferromagnetic, it's metallic. If they're ferromagnetic, the system is insulating. It's relatively insulating. And the model Hamiltonian calculation for LSMO and SiO2 structures. So this is manganese 4 and manganese 3 plus, manganese 4 plus 3D3 and Mn3 plus is 3D4. I won't go into detail. So we construct a double exchange model out of this one, and there is Hund's coupling between the classical with this T2G as a classical spin and this EG electron, the itinerant electrons. There is Hund's coupling between classical spin and the itinerant electrons, and we include the super exchange interaction. These are localized spins. And we also, there's a double exchange interaction between because of these itinerant electrons. And this itinerant electrons can hop from one side to other side and gain kinetic energy T square. And because of the SRO, because we know from this paper 2015, the carrier mediated ferromagnetism in SRO. So these are the energy diagram with thickness of the SRO. So either it's all are localized or there are some delocalized spins, although T2G, but they are delocalized. So depend upon the thickness, one can get different magnetism in SRO. And this is the phase diagram, whether this is metallic or insulating, that depend upon the thickness of the SRO. So in our model calculation, what we did is that we took Mn3 plus T2G electron and EG electron, and ruthenium 4 plus are the T2G and T2G. So there is some overlapping between EG electron and T2G electrons. And we have done a model Hamiltonian. We have kinetic energy, Hund's coupling, and super exchange interaction. There is a magnetic field, there is anisotropy. And the main part is the anisotropy. So we choose two parameter range. One is ferromagnet 1, which is LSMO like. Another is ferromagnetic 2, which is SiO like. The ferromagnet 1 is soft ferromagnet, other is hard ferromagnet. The TC of the soft ferromagnetic should be large. The TC of the soft SiO like material should be small, and the anisotropy should be 0 almost in the LSMO, and there should be finite anisotropy in SiO material. And we do a classical Monte Carlo calculation, which is you can see this is a Monte Carlo simulation of classical spin. If you do a IG model kind of thing, because of the itinerant electrons, we have to diagonalize the system. That's we call spin fermion Monte Carlo calculations, and we do a system size 6 by 6 into 8. This is SRO, this is LSMO, and we 6 by 6 lattice at the interface is necessary to study the properties at the interface. So we'll come to the results from the model Hamiltonian calculation. So this is the model Hamiltonian, as I explained to you. And the electron density we choose according to the experiment. The electron density of LSMO is 0.7, electron density of the SiO is 0.4. And first thing is that LSMO TC should be larger than the TC of SRO. That we choose a parameter range for which this TC of LSMO is larger than the SRO. And then what we do, for the same parameter range, we show that the cohesive field of LSMO is smaller than the cohesive field of SRO. So these two means what are the necessary conditions to choose the parameters are satisfied here, LSMO and SRO. And when do a calculation, means LSMO and SRO, we can see that if you go, means when we pull down our system, doing Monte Carlo system, we see that the LSMO side, there is a magnetization. This is the ferromagnetic structure factor. So we can see that there is a magnetization in the LSMO side, but SRO side still the magnetization, there is no magnetization, it's still random. But after some time, at temperature a little below, we can see that the SRO is also ferromagnet, but both of them are aligned antiferromagnetically. And because of that, the total magnetization goes to 0.5. This is a 4x4 system. So half of them are LSMO and half of them are SRO. No, sorry, this is 4x4 system. This is 5x3 system. You can see because 4x4 system means both have half and half. LSMO is 4 layers and SRO is 4 layers. So because of the antiferromagnetic interaction, the total magnetization goes to 0 at the low temperature. And we show the positive exchange bias in LSMO. So for that, what we did is that we pinned the SRO layer, which is has large cohesive field. So we pin the SRO layer. The magnetization we freeze it to be ferromagnet. Then we play with the magnetism of LSMO, and we see that because of the 89 electrons in LSMO, and we get the positive exchange bias, which is more or less similar to the experiment. And this is at very low temperature. For 5+3 superlattice, we get positive exchange bias. For 4+4 superlattice, we get positive exchange bias. So we apply a magnetic field. Both we fix the S layer, which is SRO, to be up. Then if I apply large magnetic field, the LSMO layers goes up. And if you apply a decrease the magnetic field slowly. So before the magnetic field goes to 0, we see that the LSMO layer flips its sign, the magnetization goes to down, and it becomes antiferromagnet. This is because the antiferromagnetic coupling between the SRO layer and LSMO layer. If you decrease the antiferromagnetic interaction in our calculation, this exchange bias vanishes. So this is mainly because of the antiferromagnetic exchange interaction. And what about the inverted hysteresis? And so this is the inverted hysteresis from the experiment, and we can see that there's a inverted hysteresis. So if I apply large magnetic field, both are ferromagnet, then there's antiferromagnetic interaction between them, and they're antiferromagnetic aligned. Then they have a ferromagnetic aligned, but in opposite direction. In theory calculation for 5+3 layers, also we can see this what we call inverted hysteresis. This part is the inverted hysteresis part. You can see, so similar to the experiment. And this is mostly because of the antiferromagnetic exchange interaction between the LSMO and SRO, and because of the anisotropy, interplay of anisotropy and exchange interaction. Similarly, this is the double flip in the experiment, and similar to this, what we get is that coincidentally, qualitatively, this matches very well. So if I apply very large magnetic field, both LSMO and SRO are ferromagnet. If you decrease the magnetic field, then LSMO remains ferromagnet in same direction. SRO flips to opposite direction. If you decrease the magnetization a little further, both of them flip the sign. That's why I call double flip. And if you decrease further, then both of them are in down direction. This is the calculation from our spin fermion Monte Carlo calculations. And the conductivity wise, as I explained to you, if they are antiferromagnet, the conductivity is large. If they are ferromagnet, conductivity is small. And if you calculate the conductivity, we calculate it from Dudet model. And you can see that when they are ferromagnet, the conductivity is very small, means relatively smaller. But if the antiferromagnetic, conductivity increases. So this is the antiferromagnetic layers, means region where the conductivity is large. And so this is all about the LSMO and the SRO. And we have a more or less a simple model to explain and qualitatively reproduce the experimental vectors. And more heterostructures, means if I have time, so how many minutes?
Yeah, Kalpo, sorry, I did not warn you. You are kind of almost, you finished 25 minutes.
Okay, 25 minutes. So maybe another.
So you have consumed all your time.
Yeah, another 2 minutes. Okay. So okay, maybe. So we are also studying different kind of other heterostructures like LSMO, STO kind of. This is ferromagnet. This is insulating. There is charge transfer from LSMO to STO, and there is magnetic moments at this STO. And So most of the system we are studying at this moment because of the charge transfer across the interface, of the oxygen deficiency, of the interlayer ferromagnetic, antiferromagnetic couplings, and recently we are also studying LMO, LNO systems where the LMO is antiferromagnetic, LNO is paramagnetic, and so there's charge transfer from LMO to LNO, and there's magnetic moments in LNO. So, and we are studying with the, maybe I'll not go into detail, but what we are studying is that because of the at some layers, because of the antiferromagnetic interaction, we are taking U to be the Hubbard interaction to be finite, and some layers U to be 0, and depend upon the interlayers spacing, either this 2M system, you can see that either 2 plus 1, the induced magnetic moment in the one layer, which is non-magnetic, is large. And if you do a calculation for 2 plus 2 layer with the means the interface spacing increases, the insulating layer, the U equal to 0, which is paramagnetic, the induced moment decreases. And so maybe I'll just show this slide as my conclusion. This is the experimental paper which shows inverted hysteresis, spin fermion Monte Carlo calculation shows also comparatively the qualitative results. And thank you for your attention. And this work is done by mostly by my student Sandeep for my side. Thank you.
Thank you, Kalpa, very much for a nice talk on this carrier-induced exchange bias phenomena at ferromagnetic antiferromagnetic interface. I think now the session is open for questions and comments. So I can see there is a question from Professor Mohendrian. Please go ahead with the question.
I think there was someone in front of me, Anamitra.
Anamitras, I think it was last time. I think he had not.
Yeah, please go ahead. I'll ask at the end. No,
Okay.
This time, but please go ahead, Professor.
Thanks for the interesting talk. So you showed mostly the magnetization data. Do you have the evidence from the resistivity data that it's an antiferromagnetic metal, the LSMO SRO combination?
So we calculate the conductivity, and because because of this what do you call we don't have a direct evidence that this is antiferromagnetic conductivity data, but when we measure the conductivity, the conductivity is larger for the antiferromagnetic scenario, and the conductivity is smaller for the ferromagnetic scenario.
But that is what is unusual. So I'm just wondering, is there any evidence for that experimental evidence where the antiferromagnetic state has a lower resistivity or higher conductivity?
This is because you can see, let me go down a little bit from this model Hamiltonian calculation. You can see that from this T2G and EG, this electron and this T2G is down. This is up, T2G is up, and this is down. And this is T2G is up, and this EG is up. So one can qualitatively explain from this the way we model the system.
And I understand this model, but I'm asking the experimental evidence from the papers you have cited.
Okay.
But what you present is mostly the magnetization data.
Yeah, mostly
because the decrease in the magnetization at low temperature can come from the change in the magnetic anisotropy direction, as somebody was trying to mention.
Yes, but conductivity and T effective, which is the kinetic energy, can also be, the conductivity can be explained from the effective kinetic energy. So that can be explained from this energy diagram also.
To explain, of course, you don't have the experimental data to.
We don't have the but this is the experimental data, no? Sorry, but
the experimental data is mostly magnetism.
No, they have their conductivity data also.
I see, they have, okay.
Not that same paper, but let me, where is the data? This is the data from this Takahashi 2003 PIB. They have conductivity data also. They delta R by delta R. So this is the resistivity data.
Okay, thanks very much. Thanks, that clarifies.
All right, and Anamitra, there was a question from Anamitra.
Hi, Kalpa. Nice talk. Just a quick question. So when you have interface, one thing was in the LSMO side, at least if you go deeper into the bulk region, does this sort of electron phonon coupling become an issue? Because in your model, I notice you are using double exchange.
So we have not included that part here in this model at least.
And related thing, towards the end, you said some, I mean, of course, you went through it fast. Is this, you're looking at this nickel and manganese interface, right?
Not exactly that system, but I'm trying to find out some experimental evidence what we did. So
I see. No, my question was, I mean, in all of this, at some point you have to worry about the Madelung energy. So, is there any Madelung calculation that you do?
In this calculation, we have not included, but we implement.
No, in principle, we want to put a Madelung and stabilize the densities, of course.
But we got to include the long range Coulomb interaction. Yeah.
Okay, you do. Oh, there is this thing. Then okay.
We take the long range Coulomb interaction
at a mean field level. You mean the second
at mean field level.
Okay, fine. Thank you.
Here also in LSMO, SRO, we took the long range Coulomb interaction.
Okay, sure. Thanks.
Devakant, there is a question in the chat box.
Okay, let me see how. Yeah. So, so there is a question, Kalpo, from chat box by Satyaprakash Pati. Maybe he's from Niger. So the question is the following: usually LSMA should possess twofold or fourfold anisotropy in the in-plane direction. I wonder what is the direction of a magnetic field during image curve measurement of LSMO SRO bilayer. Probably it was measured along hard axis of LSMO. Bit experimental question, but see.
Yeah, it was measured in the hard axis of LSMO. And we have not included this in-plane anisotropy of LSMO. But if we include it, our result won't change much. But at some point of time, we'll include it. But we have not included it because that's very small. As compared to SIO, that is very small.
All right. Kalpa, I have a question, very general question.
Before Devakant.
Yeah, quickly, I'm asking, I will be switch off within 30 seconds. Okay. Generally, the people tell that if you get an inverted hysteresis, that generally defy the second law of thermodynamics. But I see many papers, they are reporting the inverted hysteresis. From thermodynamics point of view, what I know from energy work done, it kind of defies the second rule of thermodynamics. So how that discussion is going on in this kind of hysteresis?
Okay, so yeah, I'm also part of that discussion, but so we can discuss about that.
Okay, fine. That's good.
Yeah.
Okay, then I think.
Just a small correction. Satyaprakash Pati, I think he's a scientist working at University of Nagoya in Japan. He's not from NICER.
Okay, I'm sorry.
Yeah, it's fine. I think let's present the memento, and Professor Sampath Kumaran had some video issue. He called me. He's joining in, so you can present the memento, and then we continue. Yeah. Thank you, Kalpataru, for your nice talk.
Yeah.
Okay, Kalpa, many thanks for such a nice work on the interface physics.
Kalpa, we don't see your video. Please turn on your video.
Okay, during talk, maybe I feel uncomfortable. That's why I always switch off it.
Okay, so that is a memento for you.
Okay, thank you.
From on behalf of the this conference. So let me read out. Symposium on Magnetism and Spintronics, Niger, Bhubaneswar. Takes immense pleasure in presenting the plaque to Professor Kalpataru Pradhana, Saha Institute of Nuclear Physics, in appreciation for being a valuable speaker to give a lecture on carrier-mediated inverted hysteresis and exchange bias in ferromagnetic heterostructures. Thank you very much.
Yeah, thank you.
Thank you. I think Professor Sampath Kumaran is here.
Yes, I joined. Yes.
Yes.
Thank you.
Abhishek, please make Professor Sampath Kumaran a co-host.
Can you share my screen?
I think he's making you a co-host. We see your video, so it is working. That's good. So thank you so much, Professor Sampath Kumaran.
Okay, thank you.
Nice to see you.
Nice to see you. Okay. Can I share video? On my screen?
Yeah.
I think now you can.
Okay, where is that share screen? I don't find it. Here it is. Okay, fine. Can you see it?
Yeah, it has come.
Okay, can you see it?
Yes, it is there.
Yes. Okay, fine. Okay.
So before we start the last talk of this session, so let me put before the audience a brief introduction. Professor Sampath Kumar is an emeritus professor at Department of Condensed Physics and Material Science, Tata Institute of Fundamental Research. And his work basically involves, he has a very illustrious career. So his work basically involves around magnetism, superconductivity, physics of D and F electron systems, Kondo lattices, as well as geometrical frustrated systems, and low dimensional magnetism, multiferroics, and nanomagnetism. And he has received numerous awards and recognition, particularly in his illustrious long span career. But I do not want to get into that. So we are looking forward really, sir, to hear from you about your talk, which is the unexpected Kondo-like anomalies and topological Hall effect features reported for heavy rare earth systems since 1990. Thank you very much, sir. So we are really looking forward to hear your talk.
Thank you very much, Vedanta, for inviting me to an exciting conference. And I must congratulate you for putting together a very excellent program. I know it's not easy to organize a conference of this type during pandemic period. And I would like to thank you and your team for this wonderful effort. So I would like to thank you again for inviting me to this meeting. Okay, as the chairman has already read the title of my talk, but actually I wanted to give a different title, which is more general: Untasted Old Wine and New Taste. So normally you heard of the saying, the old wine, new bottle. It is not old wine, new bottle. It's a old wine, untasted, but there's new taste to it. And of course, you know what exactly I mean. There's a old result, and now it attracts a lot of attention. So that's what I would bring out in my talk. But of course, I don't take wine or alcohol. I don't know how wine tastes, how alcohol tastes. But at least this particular part, I know how it tastes. So let me present that. Okay, in my talk, what I plan to do is that I want to bring out some very exciting anomalies which we found in those rarer systems where you don't expect those anomalies, both in the paramagnetic state, also in the magnetically ordered state, and which are attracting attention. Now, I mean, the features which he reported violates all the fundamental knowledge of magnetism in the literature, and it was left unexplained because we could not explain. That is attractive. That's what I want to bring out in my talk. And the point here is that I have been pursuing this particular activity, one of the activities, ever since I observed 1990s, and we have been constantly looking at various, discovering various materials with those anomalies, and we did find that such anomalies not less abundant, they are actually more abundant, except that they have not been noted. People just assume that making certain assumptions and carrying on the interpretations on the so-called normal system, which is strictly not correct. So I want to bring out. If you see me, really initial work was way back 1991 or 92 with Indranil Das on some material, who is now the chairman of the department SINP. And subsequently, we really the first experimental result, direct experimental result, what I'm going to tell you now. Roop Malik, who turned out to be now with a very well-known biologist, he was in TIFR, now he has moved to IIT Bombay. And of course, Paulos, Karthik, and Sumam, you will see Sumam Majumdar also joined later during his PhD. And I'm sure that you all seen today as a chairman session today. And Niharika Mahapatra, who is an IIT Bhubaneswar, Sudhindra Rai Prol for Neutron, and Surya Narayana Jamala Madaka, the IIT Hyderabad faculty, Kaushik Sengupta, Kaushik Mukherjee, Tatamai Basu, Ramkumar. You could see I have a good number of postdoc students right from 1919 who were actually involved as a part of their work to discover such materials. They were indeed very, very successful. And if you really want to see initial work, I would request to you the first initial work in Europe's letters in 1998. I give the reference here. And that is another paper in physical review B. These are the two results. I will mainly focus for the first 15 minutes. And I made a summary of what exactly I want to say in one of my very recent review articles in Journal of Magnetism and Magnetic Material. It's an invited article. I made a complete summary of the main anomaly which I want to discuss today. And I also would like to say that I've done very extensive, other measurements to augment the conclusion over a period of time, but I'm not thanking all the people here. And for a collaborator Maiti photoelectron spectroscopy, which I'm not going to present, Clemens Lofstad and Adurajascope neutron, Clemens Lofstad photomission. So I'm not going to present any of those results. And therefore, what I present today is essentially a gist of the important discovery which we have made in 1990s and the follow-up work. Okay, so let me start from the very basic introduction, which Kalabaran Maiti has done very wonderful introduction, but let me, for the sake of completion, for the sake of some students, let me say, you know, all of you know the rarest by definition or for elements starting from lanthanum to lutetium with 57, atomic number 71. And it was generally assumed 3-4 decades ago that 4f orbital, which is responsible for magnetism, is essentially well localized, therefore it cannot participate in bonding. And therefore people for all practical purposes ignored 4f orbital 4 decades ago. But this idea got changed around 1960s, 1970s. And it was realized that when you come to see the beginning of rarer series, a middle, maybe europium, also at the end, the 4f orbital is not as strictly localized as what you are shown here. And the radial extent really extends somewhere near the bonding region here. Therefore, you find you have a lot of localization, delocalization phenomena, which that is what currently the field of people working in the field of strongly correlated electron systems are studying. So therefore, this assumption is strictly valid that 4f orbital really well localized, well within the ionic core. Even now it is believed it is valid in the middle of the series like gadolinium, terbium, dysprosium, holmium. One would therefore expect that such rarest are supposed to be normal. You don't expect any great localized anomaly, delocalized anomaly. Of course, some magnetism angle, there could be something interesting like magnetocaloric effect. But from the exotic physics point of view, you don't expect anything great to happen when it comes to intermetallic compounds or even oxides or inorganic compounds of the compounds containing this particular series. With this assumption, a lot of storing is built around the compounds of for the cerium or praseodymium and also to some extent also for terbium. So I would say this assumption is strictly not correct. This is basically the main message I'm driving in my talk. Okay, so therefore when you come to the middle of the rarer series like gadolinium to erbium, or even for that matter neodymium, what is expected? For example, you look at electrical resistivity as a function of temperature. What is believed in the literature is the following thing: that you have some contribution into resistivity due to defects, and then a phonon contribution, which is decreasing temperature, and then you have a spin disorder contribution in the paramagnetic state. When you add up these three, you will find the measured resistivity will follow this particular curve in the paramagnetic state. And therefore, at the magnetic transition temperature, when you come to gadolinium to erbium, you will lose this particular part. You are losing a spin disorder contribution. This is the typical behavior which you expect when you come to this middle of the series. This is what has been, even now it is believed in the current literature. But therefore, if you look at this number of spin disorder contribution, really scales what is called de Jones factor. In order, if you know the number for gadolinium, you can predict what the number should be for other members of the series. So if you take such a normal rarest material, if you apply a magnetic field, one would expect a very insignificant influence on magnetic field on the resistivity. Therefore, magnetic resistance should be essentially negligible, barring the influence of a magnetic field on the Lorentz motion of the conduction electrons. For simple antiferromagnets or simple ferromagnets, this is also true. The magnetism is supposed to be very, very small when it comes to rare intermetallics. And of course, you can have other complications in the Fermi surface. Let's not go to the detail at this moment. So this is for a very strictly localized for a case when it comes to gadolinium erbium. And for this, I'm showing here as function of temperature, as function of magnetic field room temperature. If you take some of the material like gadolinium containing material or europium containing material, you will find magnetic resistance will practically zero till they measured till the field which you can access in the laboratory. Okay, so now, however, when you come to light rarers, for those 4f systems where you have some degree of delocalized 4f electrons, like those containing cerium, okay, to some extent now we considered for neodymium or a little bit of europium for ytterbium, where the 4f electrons are really pinned to the Fermi level or close to the Fermi level, or not strictly localized. And Kalabaran Maiti has a very beautiful introduction already, therefore I will not spend much time on that. You have another interaction called the Kondo effect, in which the conduction electron will try to couple anti-parallel to the local moment. And then you have in the paramagnetic state, you have spin split scattering at very low temperature. When you have T less than what is called Kondo temperature, as Kalabaran Maiti already explained, you have a formation of singlet ground state. Therefore, though you have magnetism at high temperature or magnetic moment that is quenched at a low temperature, this is due to the formation of the Kondo singlet state. This is possible only if 4 of electrons are not strictly localized, as in the case of cerium. Okay, so such interaction strength Tk is supposed to be exponentially with the exchange interaction strength. Okay, so however, you also, when you come to this true dilute limit, when you come to compounds, you have the periodicity of the magnetic ions of cerium. Then you have another interaction competing with the local Kondo effect already discussed. You have interside interaction due to the Orkiv interaction, cosmic interaction. Then you have magnetic ordering. Therefore, the Kondo interaction strength and the Orkiv interaction will compete each other. So depending upon the strength of one over the other, I mean, either this will dominate or this will dominate. Sometimes if you have extreme non-magnetism, you have extreme magnetism for intermediate values or comparable values. You see the features of both. Okay, therefore, if you measure electricity for such a system, as Colabron already has shown, in the single layer limit, you have a lattice contribution, and there is electrical resistivity minimum, and then it increases, and you form what's called fermi-liquid behavior. However, when you come to concentrated limit or any compound where you have periodic arrangement of magnetic ions, you have what is called a coherent Kondo contribution, which will decrease. And as I already mentioned, can also order magnetically. In that case, this drop also can come from magnetic ordering. So this is a typical feature to expect for a Kondo effect. Therefore, in the rare earth literature, anybody sees this minimum, and they always try to attribute it to Kondo effect and build the story. Okay, under the assumption that when you come to gadolinium or terbium or dysprosium or holmium or erbium, you do not see that feature. Okay, this is basically the point. When you also measure heat capacity, you will find there's a large enhancement of electronic contribution to resistivity as you decrease the temperature. So these are the two classic features of the Kondo effect. Now, what I want to show here, the first breakdown of this rule, that you will not see such features in gadolinium compounds or heavy rare earth compound, localized moment system. That rule was broken down by us in 1998 on gadolinium palladium silicon 3, and this compound is now attracting a lot of attention. And I want to mention right in the beginning, we are the first one to point out right at that moment, this has some very unusual Hall features, which I'm going to show, also unusual transport features. The first breakdown of Kondo-like anomalies in a compound where you really don't expect, where the 4 of electron really strictly localized. And it has anomalies not only in the paramagnetic state, also in the magnetically ordered state. Therefore, I'm going to highlight this particular point. Anyway, so more time I'll spend on this particular compound, mainly because I'm a Tokarov's group, and many other groups are following our original work. Of course, first work cited our work, and now the current work, people don't even cite those works. Therefore, I thought I should inform this august audience. Please take note of the old work, where we already shown all this anomaly, except name we could not coin because the concept did not exist those days. Concept was known on like photopological effect late 2005 to 2010 on manganese silicon, iron, chromium silicon, things like that. So the features are already shown. It was pointed out there is some anomaly here. This basically aluminum boron 2 structure, the same structure as Mgb2, and you could see layered structure here of palladium silicon here, and then you have a rare earth layer here. And we have published about 50 papers in this family right from 1990 with all the authors I already mentioned earlier. People can see all the physical review letters. We have plenty of papers in this family bringing out various anomalies of various compounds. And these are all basically honeycomb-like structure. If you look at it, there's a triangular lattice here. This is the rarest made up of triangles. And therefore, you have an intrinsic frustration because many of them are antiferromagnet. There is an intrinsic frustration due to the antiferromagnetic interaction between these rare earth ions in this lattice. Please remember, there is a potential frustration here. Now, this is the data we published for the first time. You could see here, this is the parent compound of Gd2Si3. You could see this is the paramagnetic state here. I'm not showing all the magnetization data or photoemission data, everything. I'm suppressing all the data because shortage of time. I'm showing only the transport data mainly. You could see there's a minimum, very well-defined minimum here, and this temperature corresponds to magnetic ordering temperature. Neil temperature, we also measured gadolinium Mossbar, were conclusively established by Mossbaugh, that this is the point where the magnetic ordering really is setting in. Okay, and instead of the downturn here, you could see the resistivity shows an upturn here. This again itself an anomaly here. I will come back to this, the magnetic order, the magnetic order state. Let me right now focus on the paramagnetic state. Sorry, this thing is not moving. Paramagnetic is a very clear-cut minimum. The interesting aspect, this minimum persists even if you dilute gadolinium by yttrium. Even the dilute limit, of course, you know the dilute test, dilute limit of 0.2, you could see the upturn still increases. Magnetic ordering temperature is pushed down. Okay, now if you look at applying magnetic field to this, the magnetic field suppresses the minimum. You could see normal metallic behavior which you expect here. Therefore, the magnetic resistance is quite large here in this paramagnetic region, larger than what you expect for a paramagnetic normal paramagnetic material. So this, this is exactly the feature what you expect for condo systems of cerium or ytterbium. So the identical to, there is no difference between that qualitatively. Also, if you look at heat capacity, you see below magnetic ordering, there is a peak here, and magnetic contribution heat capacity shows a peak, and then you put a long tail here. This tail persists even the dilute limit. This again, this typical feature of fermion compounds, magnetic ordering fermion compounds. In other words, if you show this compound to somebody and show the data, ask him what is this compound, suppose, can you tell me? He will not agree this is a gadolinium compound. He will say it's some cerium compound. So therefore, whatever you can see is a cerium compound where 4 electrons are delocalized. You are seeing in a system where the 4 electrons are strictly localized. And we have done photo emission experiments long ago. We published all these things. Also, the angle photo emission measurements are performed on single crystals by Dresden group. All these conclusively establish that 4 electrons are 2 or 3 electrons or below the Fermi level. There is no scope this compound can really exhibit quantum effect. Okay, so okay, now this is the data on single crystal. Initially, we tried to publish the data, referee rejected in PRL, finally published in the EPL. EPL editor wrote back to us saying, EPL referee, look, the report came after 3 months. I saw it's going to be rejected. The referee responded back saying that we repeated the experimental and we found the experimental results are correct. I'm very surprised the referee repeats the experimental data and I mean, it supports the data which we sent it for reviewing. So we are very pleased. Subsequently, we measured on single crystal. Tokyo University prepared a single crystal. We are able to reproduce whatever you see in the polycrystalline sample, a clear minimum, which could be suppressed by some magnetic field. Also, in magnetic ordered state, you don't see a suppression of the drop here. You don't see the drop in the resistivity. Okay, this is the main point which I want to send paramagnetic state. And subsequently, we have seen such a larger number of compounds. I show you, for example, these are work with Subham Majumdar. You could see this compound, the same crystal structure. You find a minimum here. This is magnetic ordering temperature. P2T silicon theory, there is a minimum here. They are not very, not as much as what is gadolinium palladium, but you definitely see a minimum before the system orders magnetically. And then you could see a large number of compounds belonging to different crystal structures. I don't think that it's restricted in one crystal structure. You see different crystal structure compounds. I don't have a data to show all. I show you some more here. People can see the article cited in the reference Journal of Magnetic Material 2021, where you see a huge number of compounds. And one paper published in Physical Review Letters is the rare earth copper arsenic 2. And you could see a neodymium compound shows a minimum. The vertical arrow shows the magnetic ordering temperature. Samarium also shows a minimum. Gadolinium compound also, gadolinium copper arsenic 2. By the way, even before arsenic became attractive, we were working on arsenic 122 as well as 112. We have quite a good number of papers on arsenic even those days. Of course, we did not look for superconductivity. Now, terbium, again, it shows a minimum above this arrow. You could see here everywhere you find, but however, where you expect minimum, you don't find minimum. You see the Kondo coherence effect or the magnetic ordering effect. When you come to yttrium, you see a normal effect, yttrium compound where you don't have magnetism. Therefore, the whatever minimum which you see here, it is just magnetism related. This paper got published, and then we tried to interpret whatever ideas were known at that time that we cannot explain the data in terms of any well-known ideas at that time. Now, I show you some more compounds, much more exact, rarer summoned ODM3, hexagonal structure. You could see the entire paramagnetic state, the temperature coefficient resistivity is negative. See here, this is ordering temperature, then upturn here, not a downturn. This is negative temperature coefficient, terbium, gadolinium, erbium, everywhere. Whereas come to cerium, you don't find it exactly opposite what you expect. Cerium compound, you don't find the minimum. And neodymium compound, you don't find minimum. Prisonum, you don't find any. Come heavy errors, you do find upturn as though there is a minimum at high temperatures. Of course, we don't have data at high temperatures. Okay. These are very exotic compound. We had a lot of measurement. Let me pick up one example, GD7 rhodium-3. You could find that when you apply magnetic field, this is ordering temperature here. Apply this could be really suppress the minimum. It tries to be the temperature for the resistor tries to become positive here. Now, why it is called magnetic? How do you know the magnetic in origin? Whatever transport anomaly which you get in the paramagnetic state. Reason is if you plot magnetoresistance as a function of magnetization, you could find all temperatures. The curve is you get a single curve. There's a universal curve here, almost universal curve. Therefore, magnetoresistance tracks magnetization. It is not due to any gap effect. Okay, it is just the magnetic scattering effect. There are very unusual magnetic scattering happening in paramagnetic state. So it's a very clearly magnetism. Magnetism plays a role here. Another common TB5SI3, you could see this compound orders at this temperature. There are much more exotic anomalies here. I'm not going to talk about it. In the paramagnetic state, you see the temperature equivalent is negative right up to room temperature. And applying magnetic field, this is getting suppressed. You could see, you see a very wide temperature range where you see the negative temperature coefficient. And recently, some compound published by Ram Kumar, Journal of Applied Physics, 2019, another new compound, you could see there's a minimum here. In these ordering temperature, and you could see minimum well above the magnetic ordering temperature. And then when you apply magnetic field, you can do all kinds of anomalies. You ignore that. Now, when you have one compound, you don't, this is zero field data, you do not find minimum in zero field. When you apply magnetic field, you start finding a minimum. This is very surprising. What is the paramagnetic state of heavy errors? You have certain occasion where they be in a very funny way, which we really don't understand. That is different from other compounds. Okay, what is the basic message as far as paramagnetic state concerned is that in some normal, so-called normal is called normal. I'm using the word normal because either 4 of electrons are strictly localized. They're not near the Fermi level. Even in those cases, there is an additional T-dependent contribution to resistivity in the paramagnetic state as the magnetic ordering is approached. Okay, these are like Kondo-like minimum, sometimes leading to a Kondo-like minimum, either to unrecognized in the literature. These basic points which I want to convey. Now, this was completely unexplained, and there are very famous irritation by Christian Batista. He has picked up this work. Our result, he happened to see our paper. I'm very surprised. He theoretician looked at the paper. He published the paper in PR in 2016. He came out with a model, and of course, you see a number of papers which are cited. He clearly says this is based on our experimental results. I mean, he has cited here. You could see here that this is a very unexplained feature in magnetism. And one has to explain he tries to propose a model saying that in the event you have a frustration, a tendency for frustration, the frustration can compete in the presence of archival interaction that can give rise to a minimum. This is a very new idea. Like Kondo effect can give rise to a minimum. There's another concept which can give rise to electrical resistivity minimum in metals. This is truly a new concept which has come out from our work, and that is theoretical advance by this group. He's a very well-known theoretician. I worked on maybe a lot of phenomenon this work, and he found that he also dilute. You can also dilute limit. You can see resistivity minimum, diluted metallic magnets. Again, he talks about our material G2PD-SI3 and all the materials. You could see here all the examples you could have picked up from our paper, from our work here. So this for the first time you have a theory to explain that electrical resistivity, like a Kondo effect theory was produced by Kondo, but here is a theory which just talks about a theory which can give rise to a minimum in the paramagnetic state, even if you don't have Kondo effect. This is completely new development in condensed matter physics. I thought I should bring out the attention of this knowledge of the audience. Now we go to magnetically ordered state. The same compound which I described just now. I mean, as a result, we found many exotic anomalies. Anybody interested can go through our papers on 213 family. We published about 50. There are many exotic anomalies are found in this family. And this compound here again, let me go to magnetical ordered state. In the magnetical ordered state, as I told you, there's antiferrometric ordering. Here, this single crystal work. There are two metamagnetic transitions here, M versus H. I'm showing a low temperature here, magnetically ordered state. And you are showing a magnetic phase diagram. There are two metamagnetic transitions field here. Now, in the other direction, you don't find, you essentially find only one. Now, the most exotic finding, which you pointed out at that time, was you mentioned Hall resistivity. is that Hall resistivity shows an upturn at one field here and then downturn at another field with a broad maximum for intermediate fields. Such a thing was never known in the past literature. The magnitude, people working on Hall effect will know the magnitude is quite large, 2 microohm centimeter here. Very large, such a broad maximum. The interesting aspect here is that you know the Hall resistivity consists of 2 components. One is a normal component, other one is skew scattering. If you add up these two, if you plot the resistivity multiplied by magnetic field versus magnetic field, this curve should look like exactly this curve. In contrast, you find exactly completely different behavior at the metamagnetic transition field. On this basis, observation of these fields, we have proposed that there is something funny in the magnetism of this compound. People can read those papers, and there could be some very interesting Fermi surface effects in these compounds. And I mean, therefore, there's a need to understand this compound, this feature better. We are first time point out. We also pointed out that some Fermi surface topology may play a role in this material. Subsequently, this work was picked out by resident group. They measured angular resolved photoemission, and they do find that in this material, low temperature, there is a very strong Fermi nesting, very unusual Fermi nesting, and they also endorsed our view that the magnetism of this compound could be complex. I'm saying this 1999, 2000. Okay, and we left it at that stage. Please remember this graph. We reported in 2000, that is experimental data was obtained in 1999, a broad maximum in Hall coefficient for intermediate field range. Please remember that. Remember, this was for the first time proposed as experimental signature of magnetic fermions in manganese, silicon, and iron, chromium, silicon, many systems after 2005. This we are able to see as early as 1999, 2000. This is the point which I want to make. Okay, so therefore, in this, if you look at Hall resistivity, your additional contribution, which now we known as topological effect contribution, which adds up to that, as a result of which the conventional knowledge of a Hall coefficient, Hall effect breaks down. That was pointed out even earlier, that was not known earlier. Now it turns out to be interesting mainly because of the fact that the potential applications, Spintronics, next generation information storage in the materials. Now I just want to bring it to the knowledge of the audience that following our work, the Kurmaji group, Tokaras group published a very nice paper in Science very recently, and following our GTP, you could say GTP SI3 here, and of course they measured repeated of Hall effect measurements, and now now it's called topological Hall effect. And you could see the features are exactly the same what we have reported here. Same broad page except the measured exert temperature. So whatever they are seeing now, we reported 20 years ago, 25 years ago, long ago, except that they also measured X-ray resonance scattering measurement, and they do find evidence for the presence of magnetic fermion. Therefore, whatever you see here is due to the magnetic fermions. We are very pleased. The Tokaras group followed our work and brought it out, established the validity of our results, also bring out the magnetic fermions are responsible for that. And I written up a note into science paper following that these things were already known in GDP SI3 as a follow-up of this Tokaras paper. Anybody interested can see that. I also found my article. So basically, the point here is that there is also a theory by Hayami and Motome, and they have come out with theoretical concepts that you can have certain situations also by Batista, that now they come out with new theories based on our original finding. In fact, our gadolinium compound which we reported, our data considered to be a triggering point as far as I'm concerned to come out with such new theories. They come out with new theories that how the Italian electrons, what are circumstances under which the Italian electron in metals can give rise to such features, and they find that archic interaction can be frustrated. You don't have frustration due to geometrical frustration. You don't have frustration due to disorder. Even archic interaction can really frustrate, and many states can compete in the ground state. As a result, you will see the complex magnetic ground state. This is basically the message of the paper. So this is different from conventional geometrically frustrated magnetism because this is short range. Conventional geometrically frustrated magnetism is short range, where archic interaction is supposed to be long range interaction. There's a conceptual difference. So here the difference is also band structure plays a role. That is what was found in GUTPD SI3 in the year 2000. There is a Fermi surface nesting. Therefore, we got enough experimental results in late 1990s to suggest that there is extremely complex magnetic state that is appearing here, and which one has to understand. Our today now results are coming out in favor of our earlier thing. And also you could see the drop in resistivity is absent in this material, which already pointed out in our papers that is also due to the complex nexting of Fermi surface. We have a complex nexting, you have a gap developing at the Fermi level, then the resistivity tries to goes up instead of other coming down. So this was actually pointed out at that time. And recently we have published a paper 2020 comparing the features to the same family of Gerdon silicon 3. You could see we point out that we also have metamer transition here, 2 metamer transition here. We propose that these are some of the examples which you can further explore to augment the conclusions on other magnetic fermion. Those interested can read this paper. Okay, therefore, the main point is that following our original experiments on gadolinium-based intermetallics about 2 decades ago, recent theoretical approaches by Batista, Hayami, Motomi, they emphasize the roles of within the electron, arcane metallic system on the magnetic and transport anomaly, not only in the paramagnetic state, but also in the magnetical ordered state. And it's very, I would request members to read those papers, those theory papers as well. And there are further theories based on GDP. You could see here at the conclusion, they are referring to GDP SI3 of our paper of 1999 or 2000. This is a beginning point. They come out with more theory physical review letters by Batista's group, how the fermion crystal can be formed from arcane interaction mediated by 2D. There are basically 2D system, 2D electron gas. And this example turned out to probably, in my opinion, a prototype, because they reported 1990. A prototype, as far as VR opinion is concerned, going to be example for the theoretical prediction according to them as well. And we have another example, GD3 aluminum 4Al2.
So we are, can I interrupt? So we are kind of running out of time.
Okay, the last transparency here. Basically, the take-home message is that even for those materials, gadolinium, terbium, etc., now other wearers, which are traditionally considered uninteresting from the magnetism point of view, can exhibit novel properties, not only in the magnetical ordered state, but also in the paramagnetic state. Kondo, second point, Kondo-like upturn in metals, not necessarily due to Kondo effect. A new theory for triangular lattices emerged, but may not be universal explanation. There could be more than one theory, may be required. And I would say that so generally I try to be modest. Let me not be modest. Kindly permit me not to be modest, because we are very proud that we have seen something 20 years, 30 years ago, what people are talking about today. Except that we didn't coin the name. We could not, because the concept did not exist. I would say we have done pioneering work in this direction, leading to new concepts and novel magnetic states in the current literature. And we reported Hall anomalies even 2 decades ago, which are now termed topology Hall effect in the literature after 2009. Thank you very much for your attention.
Thank you, Professor Sampath Kumaran. Such a nice, fantastic talk. Now, because we are running out of time, we may take maximum 1 or 2 questions. So Anamitra has a question. Okay. Professor Mohandiran has a question. Yeah.
Okay. Well, it's not a question. Thanks very much, Professor Sampath Kumar. It's a very interesting talk, of course, very original work. But of course, now this is been shown as a new work by Tokura's group. I'm wondering that what new now can be done. Of course, you have the material.
Yeah.
What is the direction you want to give to the Indian researchers to work on this material? The new experiment?
Well, as I told you that we already shown the large number of material we brought it out. Recently, also paper PRB last year, I already given one reference. We have brought out the review I've written up. I already clearly mentioned in my review of 10 pages review in order of Professor Krishnan. They appeared in Journal of Magnetism. We have brought out various ideas that can be pursued. A lot of work can be done. The new materials we already have, only the one has study them in detail. That's all. And look at the systematics. Various systematics emerging.
Okay, sorry, I didn't read that.
Yeah, you see,
Thanks very much.
Written by Ram Kumar and myself. There's an invited article in the special issue in honor of Professor Kannan Krishnan.
Okay, thanks very much.
Yeah.
All right. I think there is one more question. I think this is the last question we'll take. This is why Su? Yeah.
Yes.
Thank you for this very nice talk. I really read your comment paper on archive about this gadolinium system. Congratulations. I fully agree with your talk. Okay, you are really the pioneers for the discovery, because I often read this Takura's group's paper. Okay,
Yeah.
I have a question about because for gadolinium system, this is a triangular lattice. Okay, of course, your argument is that there is a strong anti-ferromagnetic coupling. Okay, that's why the fluctuation comes. But what about for other rare earth systems if the coupling is ferromagnetic? Because in this case, you would get rid of frustration. Would the resistivity behave differently? This is my just one question.
Repeat your question. I didn't get your question. Sorry.
My question is, okay, for gadolinium, you assume this is anti-ferromagnetic coupling based on the new theory.
Not assume.
But my question is, if there are some other rare earth system, you have a ferromagnetic coupling, okay? For this years labor triangular. In this case, there is no more frustration, okay?
Correct, yes.
In this case, I just say, is there any such kind of the system exists based on your study?
No,
for instance, indicate.
Yes, you are talking about paramagnetic state or magnetic launders.
Exactly. Because in this case, you have no more frustration, then the system would become more like a conventional way, okay?
Yes. Okay, let me, okay, the very good question. I think I don't have the list. There are gadolinium nickel. You look at gadolinium nickel is ferromagnetic. We have published from 1994. Even gadolinium nickel we are finding in the paramagnetic state. Resistivity, extra resistivity. Now, therefore, frustration, that's why I concluded and lost my frustration could be one mechanism. There could be more than one mechanism, which is yet to be explored to explain the ferromagnetic systems also. Your question is 100% valid. I endorse the question.
Okay.
We have seen in the list which you have shown in the 1 hour transparency, there are some ferromagnetic systems also.
Right. Thank you. This is very interesting because it's not published yet. We are working on some. We are working on some theorem-based triangular system. We have actually seen similar. This resistivity has a minimum, then goes up. Of course, the ideal is this is a quantum effect. Okay, but now we would have to think about that really carefully.
Exactly. I would I request you to see my review in Journal of Magnetism Magnetic Material.
Yes.
Recently. You had thoroughly reviewed that.
Okay. I think, the discussion can continue. Thank you so much, Professor Sampath Kumaran. Devakant will read the memento, but before that, I just like to mention that you are requested to go to the room 2, zone 1. And then interested people who want to discuss with Professor Sampath Kumaran can go there. And the other speakers, Professor Brukel, Professor Sadas Gupta, Professor Maiti, and Professor Pradhan. If you are still around, you can go to room 1. We have also volunteers there. In case you face any difficulty, they will assist you. And people who want to discuss with you can discuss. At least be there for 15-20 minutes. And it's up to you. And we have very active poster session now about 35-40 wonderful posters are there. I encourage you to visit there. Okay, I raise my case. Devakant, please continue.
Yeah, so Professor Sampath Kumaran, it was a nice talk, very excellent. The old work which now they say other groups are taking up. So very wonderful. And in this occasion, we would like to now offer you a kind of memento, online memento. So let me read that what the message tells. Symposium on Magnetism and Spintronics, Niger, Bhubaneswar, takes immense pleasure in presenting the plaque to Professor E.V. Sampath Kumaran, Tata Institute of Fundamental Research, India, in appreciation for being a valuable speaker to give a lecture on unexpected condo-like anomalies and topological Hall effect features reported for heavy rare earth systems since 1990. Thank you very much.
Thank you very much. I thoroughly enjoy meeting you all, and let us hope that we are able to meet personally at soon.
Yes.
All of us in our meeting.
Thank you so much, Professor Sampath Kumaran. I really appreciate your presence. Thank you all. We will resume the session here in Zoom at 6 o'clock with the same link. So it's up to you to log out or log in again. But now we can go to the friend platform. Thank you. Thank you so much, Devakant. I'd like to present a small memento to you for doing a wonderful job with the session chairing. So the Symposium on Magnetism and Spintronics takes immense pleasure in presenting this plaque to Professor Devakant Samal from Institute of Physics, Bhubaneswar, in appreciation for chairing the session 4. Thank you so much, Devakant. Thank you. So let's meet at 6, and now let's go into the frame platform. Thank you. See you.
Thank you.
Żeby sprawdzić to. Chyba, że nie wyłączy. Weź Wojtka szybciutko. Znaczy zaraz.
Wszystko słychać.
Słucham?
Mikrofon włączony jest.
Co jest?
Mikrofon macie włączony.
Dobra, to jest.
Hello, Subhankar.
Okay, good afternoon.
Hi, how are you?
Yeah, good. Good to see you. Thank you.
How was the poster session?
It was this virtual platform is not so good. If you don't play video games, then it is killing.
Right.
So I realize now I have to learn video games.
So poster was also on virtual or it was offline?
No, it was virtually.
Oh, I could not attend.
No, you can tomorrow also there. So you really feel like a conference hall. You have to work. Your avatar will go to the poster. It's nice.
Okay.
Okay. I think Professor Anjay Majiski is here. Hello, Anjay.
Yes.
Hello. I could not switch on my camera.
Why that? One second, maybe.
Okay.
Just a second. We will make you a co-host.
Okay, now it works.
Okay.
Okay.
Yeah.
Okay. Znaczy to może usiąść troszeczkę tam.
And I request my team to make Professor Majiski a co-host. And also Professor Subhankar Chakrabarti a co-host. I think people are busy in the poster session. Please give me a minute. They're just in the next.
Sure. Hi.
Hello.
Hi, Professor Majiski. My name is
Nice
Dr.
to meet
Subhankar
you.
Chakrabarti. Yeah.
Okay. So is it possible to check how it works?
Yes. Do you want to share the screen?
Yes.
Yeah, please.
Yes, not it. Just a second, because my team, they were also presenting posters. And
Right.
now they're coming back to the Zoom computer, they will first need to make you a co-host, and then you can share your screen. I think Subhankar is now a co-host. And so Anjay, how are you? After a long
Fine.
time I'm seeing you.
Okay. We are following your research now.
Thank
connected
you.
with super ferromagnetism.
Okay, thank you so much. So just to tell you, Professor Kleeman is in the audience.
Yes.
So he is looking forward to a lecture.
Okay. So regards to him.
Yeah, Anjay, you can now share your screen. You are a co-host.
Yes.
Yeah,
Oh,
hello.
hello, Wolfgang. Nice to see you.
Wolfgang, we cannot hear you. Something is wrong. I think your maybe the plugs are plugged in a different socket. You are on mute. No, we are not able to hear you.
So I think this is a problem with the microphone.
Yesterday. No, Wolfgang, I'm sorry, we cannot hear you. Maybe you fix it. At the end of the lecture, we can exchange few words.
Yeah, the slides are shared.
Yeah. Okay. No, Wolfgang, we cannot hear you. Wolfgang, we cannot hear you. I think we cannot hear you.
I think he also can't hear us.
No.
Okay, a teraz.
Okay, Wolfgang, I think we cannot hear you, so I would request you to mute your microphone in any case. Yeah, it's really pity something again happened. But maybe you fix your microphone issues, and at the end we can have few words. We can exchange few words. So okay, Subhankar, I request you to. We share the same first name, friends. But he is Professor Subhankar Chakrabarty. He is an associate professor at the Institute for Nanoscience and Technology at Mohali in Chandigarh in India. And he expertise on many things, heterostructures, two-dimensional electron gas, where he looks both for transport and microtransport. And I request him to chair this session. So Subhankar, it is all yours.
Yeah,
kindly note that all lectures will be 25 minutes plus 5 minutes discussion. So
right.
you
but
may
I am supposed to say this.
Yeah, you may kindly say that after 20 minutes you will give some reminder. Now I leave it to you. Thank you.
Yes. Thank you, Shubhankar, for inviting me to this fascinating conference and also for giving me the opportunity to chair this exciting session. This session is basically consists of 3 talks by eminent scientists. Each talk will be for 25 minutes. And as Shubhankar said, we will try to keep this time very as strictly as possible, followed by a discussion of 5 minutes. I will give a ring, try to give a ring or kind of alarm for the speaker at 20 minutes. So you'll have another 5 minutes to talk about your things. So the first talk of this session is by Professor Majewski. He is a very senior faculty member in the physics department of University of Białystok in the Department of Physics of Magnetism. He is not only involved in the scientific activities, but he's also involved in many kind of administrative duties. He is a member of Committee of Physics of Polish Academy of Science. He held many positions that include Scientific Secretary of Polish Academy of Science, Ministry of Science, Higher Education and Technology, Ministry of Education of he also received the Polish President Golden Cross in 2001. His prime interests are investigation of static and dynamics of magnetic domain structures and magnetic phase transition, then development of magnetic topological magnetometers supported by digital image processing techniques and ion bombardment, and looking into the light irradiated influence of magnetic materials. And then magnetization, excitation and spin wave propagation in pattern films. The title of his today's talk is Engineering of Magnetic Ordering and Magneto-Optical Properties in Ultra-Thin Films. So please, Professor Majewski.
Thank you very much for invitation to participate in this very special conference. We met 3 years ago at another conditions. I hope that in the future we can continue our direct contact. Thank you for your introduction, Chairman, for introduction, and I would like now to start my presentation. As the first slide, you can see our new campus in physics is part of nature and science campus, chemistry, biology, and mathematics. My talk will be focused on maybe focused on 4 different topics. I will discuss some selected data connected from our recent research, especially connected with ion bombardments. And the main part, I will compare it with light irradiation. I will show some result connected with reversible changes of magnetic isotropy by small temperature annealing, and some results connected with modeling of magnetic ordering. Okay, so as introduction, it is very well known that it is possible to engineer different properties in the ultra-thin regime, and it is possible to apply for different applications. It is rather well known, for example, recording and other purposes. And as introduction, it is necessary to consider exchange interaction, uniaxial isotropy. It is main isotropic which will be discussed in our case. Działszyński-Moria interaction, it is a new topic in ultra-thin films regime, and room temperature, magnetic field, Zeeman energy, and demagnetization connected with charges on the surfaces. In the case of ultra-thin film, for example, to focus our attention for cobalt ultra-thin film, magnetic isotropy contains different contributions: as volume isotropy, demagnetization, and also surface isotropy connected with different surfaces, is 1/d. And changing thickness using, for example, wedge type of sample, it is possible to obtain spin orientation for about 2 nanometers in the case of cobalt. Sometimes instead of effective isotropy, it is usually used quality factor. It is relation between uniaxial isotropy energy and demagnetization. And changing thickness, it is possible to obtain spin orientation when effective isotropy change sign, or when quality factor decreases below 1. It is a case of cobalt and gold, but it is a very common situation for iron and another. And if one has such kind of If one apply magnetic field, it is possible to have magnetization rotation in the thicker part and movement of the domain wall in the range which is white. Here we have out of plane magnetization. It is image magneto-optical image obtained from Kerr effect. There are hysteresis loops, and here we have rotational type of magnetization and analyzing of magnetization curve from saturation field. It is possible to determine effective anisotropy value, which is important for analysis. Approaching this phase transition, one can find very strong change of domain dimension sizes. This pioneer work from Germany, Speckmann and Open, where it is possible to find very fast decrease of domain size, and it is possible to recalculate and estimate and find that domain size is in sub-micrometer range. We made a similar analysis using LFM for different thicknesses of cobalt, and a critical period of domain at the spin orientation point. It is possible to describe by simple formula. It is a relation between exchange length over D. And from this, it does not depend on anisotropy, and it is of the range of sub-micrometer. Okay, and now let's go to modification by ion. Let's consider such kind of structure, this cobalt and ceramic of platinum. And if we have ion, I will discuss ion of gallium and argon ions. It is possible to obtain locally increase of temperature, changes of position of cobalt and platinum ions, creation of some alloys, some phases, and some sputtering effect. We started such kind of research with cobalt and platinum surrounding. Using magnetoptics, it is possible to analyze two-dimensional changes. So we study it as a function of cobalt thickness and as a function of radiation. It is along x-axis cobalt thickness, and along y-axis this different influence of gallium from 10 to 13 to 10 to 16, a series of this work. And analyzing locally magnet loop, one can obtain decrease of coercivity and transition to superparamagnetic state. It is classical results obtained at the different works, decrease of coercivity. But there is another effect when one increase thickness of cobalt. Starting from in-plane magnetization, it is rotational type of loop. It is 3 nanometer of cobalt, so above spin orientation, one can find the creation of out-of-plane state even 2 times. So we found 2 out-of-plane branches after this transition to supermagnetic case. It is possible to characterize loops, saturation field, remanence, rotation remanence, and coercivity. And after this, it is possible to construct maps of different parameters. Let's discuss, for example, 2-dimensional map as a function of cobalt thickness, influence of coercivity and effective anisotropy, and one can find creation of branches of out-of-plane state. Here it is in-plane magnetization, and here there are 2 branches of out-of-plane magnetization. And here it is superwagoneric or spattering of material. In the remanence, it looks very similar. It is relation between remanence curve rotation to maximal value, and it is possible also to find strong changes of magneto-optical curve effect, increase of this curve effect. Okay, and we recently we did some systematic studies of influence of irradiation, gallium irradiation for cobalt at different surroundings. It is, one can say, reference cobalt with platinum, and also cobalt with platinum and gold, gold, platinum, and gold, platinum gold. It is possible to have hysteresis loops and analyze, and we made this irradiation also double wedge, cobalt thickness, cobalt, and influence on the y-axis, and one can find following maps, this initial map which we discussed below in saturation, and one can find that for gold surrounding, these changes are very small. And magneto-optical changes, so also in the platinum surrounding increase of curve rotation is the strongest. From synchrotron radiation analysis, we found that first branch is connected with some stresses, and second is connected with creation of some cobalt clusters. After this, we decided to make analysis for selected cobalt thicknesses and for different fluences, and it is a set of samples in the following range. Cobalt 3 nanometers, so cobalt is in initial in plane configuration, and different influences, stacks, and it is magneto-optical image, and we have the possibility to obtain these two out of plane branches. In the immediate state is here, and there are hysteresis loops showing these results. Here it is analysis of different parameters, magneto-optical, and also anisotropy and coercivity. And one can find that for cobalt in surrounding platinum, especially having gold, it is possible to have out of positive effective anisotropy, so it is possible to create out of plane state. It is possible to study also domain structure in these agents with out of plane state. It is selected points A, B, C, and for these points we made MFM imaging, and one can find small domains structure. This domain structure is not defined by magnetic. In Prague, magneto-optical spectroscopy studies well performed for these samples, and for selected traces spectra, and strong rotation.
I'm sorry, Anjay. Hello.
Yes, yes.
Hello. Your voice is not clear, and then there is some strange sound is coming from your side.
Okay, so maybe I can be closer to microphone. Yes.
Yes, yes. Now it is better. Yes.
Okay.
Thank you.
Okay, so so from this magneto-optical spectroscopy, one can find also strong increase in ultraviolet range. Here it is the spectral dependence of polar carrier effect. It is energy from 1 to 4 electronvolts, and here it is rotation. It is rotation and ellipticity. So one can find strong increase. And this data were analyzed considering different alloying of the system. So it is possible to find distribution for this 3 selected, so reference sample and for 2 branches. And after this, it is possible to reconstruct distribution of cobalt. It is depth, it is surface of cobalt, and there are different curves showing cobalt profile from 3D simulations. It is black curve. From magneto-optical spectroscopy, it is visible here. And also from the X-ray reflectivity, which was done for homogeneously irradiated samples for defined thicknesses. Okay, here it is visible, mouse. Okay, and now we selected, focused our attention for this sample, because in this sample there are asymmetric interfaces, so one can expect Działszyński-Moria interaction in such kind of system. To study this effect, we used Brilliant light scattering setup, and measurements were done as a function of inclination angle, so it was possible to change K vector, and results are visible here. There are stocks and anti-stocks spectra, and one can see asymmetry in frequency stocks, anti-stocks, and in this asymmetry, this asymmetry is connected to Działszyński-Moria interaction. We made measurement as a function of the K vector and also as a function for different orientation of the field, and one can fit this curve, and it is possible to estimate effective Działszyński-Moria interaction constant. It was done also as a function of fluence, and for fluences above 10 to 15, it is we found that Działszyński-Moria interaction is vanished or strongly reduced. It is possible to combine it with isotropy measurements, and from this one can find that here there is out of plane isotropy and in plane, and Działszyński there is no. It was done not only for gallium but also for argon, which is more commonly used ion. And for this ion, it was possible, using this same energy, it was possible to obtain also similar effect, 2 branches of out of plane state. Measurement were done also as a function of argon energy. And from this, one can find that decreasing energy, this first branch goes to second, and we have very close to sputtered surface, we have out of plane Max-Jesel state. It was systematically studied using another technique, but we have no time for precise discussion. Using light, it is possible to obtain similar effects. Changing thickness of cobalt, here it is spin orientation, and for low power, one can find reversible effects, but for higher power, it was possible to obtain also 2 branches of out-of-plane state, and after this it is possible to have ablation of sample. It is similar as we found for irradiation by gallium. And here I would like to show results of modification of platinum, cobalt platinum sample with in-plane magnetization, and it is laser spot, and one can find rings, white rings, which are connected with creation of out-of-plane state with small domains just close to surrounding. It is very similar as was observed previously on cobalt wedge.
However, you have 5 more minutes. I'm sorry for
okay,
this.
so I
Yeah.
try to finalize. So it is, but here we have 4 phase transitions. Okay, and now it is. I would like to show some results connected with influence nickel oxide. In the sample with cobalt gold surrounding, we have spin orientation for about 1 nanometer, but having the deposition by nickel oxide, it is much higher. One can try to compare it with antiferromagnetic state in cobalt, which depends on the composition between cobalt and nickel. So close to room, slightly above room temperature, one can obtain transition above null temperature. And here there are results connected with characterization of the samples using field. And after annealing, it is possible to have transition to in plane, and domain structure which was obtained during such kind of magnetization was very small in comparison to these domains. It is reversible effect. And so after saturation, one can obtain the same situation. It is similar as transition driven by in-plane field. Here it is also possible to have different domain sizes. And the last part is connected with modeling of magnetic anisotropy. We made it as a function of Q parameter, this transition from in-plane to the perpendicular state. And here there is the DMI. And so increasing DMI from in-plane is possible to obtain spin spiral. And after this, it is possible to construct diagram of magnetic state. It is here in plane. Here it is out of plane state with different spin spiral domains. And this annealing effect, which we discussed, it is connected with the transition along this axis. This critical period is defined in this point. It is possible to derive on this space not only by temperature, but also, for example, by electric field. And conclusions. It is possible to make creation of ion by light, 2 branches of out-of-plane states. It is visible for light. These 2 branches could be changed by cover of a layer and ion energy. It is this case of argon irradiation. Small temperature annealing induces spin orientation and creation of small domains, submicrometer domains. Domain existence, DMI existence, namely deposited by platinum cobalt gold layer, could be reduced by ion irradiation. And phase diagram of magnetic state is constructed is here. I would like to thank different co-workers from Poland. We started this research with people from Orsay, from Professor Jacques Ferret team. Synchrotron radiation study was done in France, in Grenoble and in Tsukuba. Irradiation was done in Rosendorf. some magneto-optical study was done here. I would like to mention that during our last meeting in Budenswar, some very fruitful for us discussion was done with Stanisław Rochar. So thanks, Stanisław. So thank you very much for your attendance. So maybe I am in time.
Thank you, Professor Majewski, for this fascinating talk. So the session is now open for discussion. So we have 5 minutes. Yeah. Any question you can ask directly, or you may raise your hand, and then I can.
Can I ask Subhankar one question?
Yeah, please, definitely.
Yeah. So very nice talk, Anjay. I really enjoyed. I wonder if you go to the previous slide where you show these domain structures from platinum.
One minute. Okay.
Can you hear us?
Yes, I hear. So I made. You can see all and what domains you are talking about.
If you go to slide number 28.
Yes. Okay.
Thank you. So, you know, the standard platinum cobalt domains, they are this bubble domain with very sharp boundaries. Now here you see like this kind of flower-like domains, or what do you say? So what is the reason behind this kind of petals-like domains?
You are not right. In the case of platinum, cobalt, platinum, it is possible to have very different type of domains. It is possible to have sharp domains, but in many cases it is possible to have, depending on technology, it is possible to have fractal type of domain wall. I could give you some references concerning this, and we study such kind of effect, and it is possible to describe it considering spread of coercivity field at different points, and it gives such kind of structure which is not defined by magnetostatics.
So it is kind of magnetic inhomogeneity.
Local, yes. For high anisotrope material, high coercivity material, it is the case. This situation is another when we are approaching spin orientation. Approaching spin orientation, it is possible to have a smaller roughness of domains, not fractal type, but distribution defined by magnetostatics.
Okay.
And I think that it is clear visible here because it is not cobalt and platinum, but we have rough domains, but is close to phase transition system is sensitive for magnetostatics. It is the reason that we have nice domains.
Okay.
And very dense state.
Yeah. All right. Thank you so much.
There is a question from Srinivasan S. If you wish, you can ask directly, or I can read it out what you have written. Srinivasan.
Okay.
Yeah, I'm reading on behalf of him. He's writing weight shape layer is play a role rather than the planar shape. So he's talking about some kind of shape anisotropy. If it is weight shaped or planar shaped, how it matters.
I do not understand. You are talking about the magnetization. It is.
I am also not sure. I'm just reading what he has written.
Here?
Srinivasan, if you are around, I request you to kindly unmute.
I increase it. Letters.
Yeah.
So you have this demagnetization, which is leading contribution.
Okay.
And we have contribution from volume, and we have safest anisotropic contribution.
Yeah, I think his question is probably like is the wedge shape is playing a role, or is the planar shape? I think the wedge shape is just to vary the thickness. I think the wedge is not really playing any role, I think.
No. If, we use it wedge because it is possible to study for different thicknesses and for wide different thicknesses.
Yeah,
and in many cases, these effects are very thickness dependent. So it is better to use wedge instead of many hundreds flat samples.
Okay.
Yes. Okay, Subhankar, I think you can wrap up.
Yeah, thank you very much, Professor Majewski. It was a fascinating talk, and people can directly contact him and discuss with him later if they wish.
Yes, Anjay, you can stop sharing.
Yeah, he has stopped sharing already.
Yes, and you can, Subhankar, you kindly read it for present this memento to him.
Okay, so thank you very much.
Okay. There is a virtual memento for you, Majewski. This is the National Symposium on Magnetism and Spintronics, SMS 2021, National Institute of Science Education and Research, NIACR, Bhubaneswar, India. Takes immense pleasure to present this plaque to you. Thank you very much once again. This is I'm presenting on behalf of Dr. Shubhankar Vedanta. Thank you.
Thank you so much, Anjay, for all your support. Thank you.
Thank you very much.
Okay. So the second talk of this session is by Professor Rohat from CRNS, University Paris Saclay, I think, if I pronounce correctly. He is interested in the physical properties of magnetic textures and their application in spintronics. He has pioneered the research on chiral magnet texture, showing that the combination of Zajcenski-Moiria interaction with spin orbit torque could lead to more efficient texture motion, which lead to a renewed approach to this field. He has been working on magnetic skyrmion for last 10 years, both in theoretical and experimental aspects. Today, he is going to talk about time response and maximum velocity of skyrmion in antiferromagnet. So, Professor Rohat, it's all yours. Please start. As you know that it will be for 25 minutes, and I will give an alarm 5 minutes before. Okay.
Okay. Hello, and thank you for the introduction. Do you see well my screen?
Yes,
screen?
yes.
Okay, fine. So I will present you our theoretical work on skyrmion dynamics in antiferromagnetic situation. I will show you why people are interested in that. So this work has been done by my PhD students, Sujit Panigrahi, and my former postdoc, Sugata Malik, that were both from NICER, Bhubaneswar, and also from Edward Als, another PhD student. Okay, so skyrmions, you may all know that they are very interesting texture, very exciting for maybe for future applications. They are topological in the sense that if you map all the spin texture on a unit sphere, you will cover exactly once. So if you wish to do some mathematics, you can use this matrix of the unit sphere, and you will find plus or minus one depending on the magnetic core orientation. So topology nowadays in physics is very fancy. It's very nice, but it has some drawbacks for skyrmions. If we look to the magnetic dynamics, if we push a skyrmion in a, let's say, for example, this is a magnetic track, it's a simulation. We push the skyrmion in this direction with the current, and the skyrmion is going to be deflected. And this is due to the topology and also the magnetization of the sample. Another drawback of the magnetization of the sample is that due to the dipolar coupling, so the coupling between the skyrmion surrounding here in blue and its core here in red, we have larger skyrmion, and we would like for application to have super small skyrmions. So this is why people are very interested in antiferromagnetic situations. When I speak about antiferromagnetic situation, it's not only real antiferromagnets that are very difficult to work with, but kind of equivalents that are either artificial or synthetic antiferromagnets, two magnetic layers that are coupled by RKKY coupling through some spacer, or also ferrimagnets. There are these very nice rare earth transition metal amorphous alloy that are naturally antiferromagnetically coupled and that mimics the dynamics of antiferromagnets. So in this situation, of course, the magnetization is killed or almost killed. So we can have very small skimons, as it was demonstrated in this paper in 2018, with very small skimons down to 10 nanometer, or we can say a few tenths of nanometer. It has been shown also by some colleagues here in Paris-Saclay in synthetic antiferromagnets. And also very interesting, and I will insist a lot in this talk today, is that during the dynamics, because two skimons are coupled with opposite topology, they have opposite skimon core polarity, we may expect that the gyrotropic deflection that can be seen in this simulation can be cancelled. And so some experiments have now shown that it can be reduced when there is a bit of residual magnetization in the sample, at least. If we wish to describe the magnetic dynamics of a skimon or a texture in some sample, we can use what is called the Thiele equation. So this Thiele equation is very simple. We just take the local dynamics, so the Landau-Lifshitz-Gilbert equation. We integrate over the space, supposing that we have a stationary motion, that the texture do not evolve during time, and then we end up with this equation. In this equation, we have some forces. Here is a force that is due to the spin current in the sample, so in the form of the spin orbit torque, and it is of this form. Then there is some dissipation, which is related to the magnetic damping. So we have alpha, the magnetic damping, and D, some parameter, which is related to the shape of the skimion. And this force, which is specific to the topology. So G is what is called the gyro vector. It's perpendicular to the magnetic plane, cross the velocity of the sample. So you see that this force is orthogonal to the velocity vector, and then it is at the origin of the skimion deflection. These three forces, they are parameterized by three purely geometrical factors, N, D, and F. We have the angular momentum in the sample, which is more relevant than the magnetization of the sample. So if we solve this equation, we find it's very easy to solve. We can see that the velocity is mostly proportional to the ratio between the current force, induced force, and the dissipation. And this velocity looks to be inversely proportional to the angular momentum. And the deflection, so the Vy over Vx ratio, is simply proportional to the ratio between the norm of the gyro vector and the dissipation. And it looks to be independent on the angular momentum. So we arrive to a paradox, because we have said that in antiferromagnetic situation, because we cancel the angular momentum, we will have no gyrotropic deflection. And here we cannot reproduce this situation. So to deal with this problem, we have to deal with two equations rather than one, and explicitly describe the coupling between the two skimons. So here we have two antiferromagnetically coupled skimons. And in addition to the forces that I have described before, I had these two green forces, F2/1 and F1/2, that are the coupling force. So these two forces, they are just opposite in direction. So just by action-reaction principle. And we can just sum up these two equations to remove this force and end up with an effective Thiele equation. So this effective Thiele equation now involves an effective gyro vector, which is proportional to the difference between the angular momentum in the two layers. So we have now explicitly the total angular momentum of our sample. And the dissipation instead, it is the sum of the dissipation in the two layers. So this indicates that the dissipation now is not proportional to the angular momentum of the system, contrary to the previous example with just one equation. And we can see that the dissipation is always positive. It never diverges or be cancelled. And the dissipated power is okay. It's a viscous force, so it is proportional to the square of the velocity and proportional to this angular momentum L alpha, which is basically the sum of the two dissipation in the system. And then the force of the current is simply the sum of the two current forces. So if we solve this this effective Thiele equation, we find that the velocity is no more inversely proportional to the angular momentum, but inversely proportional to the dissipation angular momentum. So it looks not to be affected by the magnetic compensation. Instead, the deflection, so Vy over Vx, now is proportional to the angular momentum. And if we go to, I mean the total angular momentum. And now if we go to an antiferromagnetic situation where the angular momentum is exactly zero, we expect no gyrotropic deflection. So I will illustrate this in some simulation further. So if we look to the consequence of the small Skimen size, which is one of the specific aspect for the antiferromagnetic situation, is that the magnetization is zero or close to zero. So we have three geometrical parameters, n, which is related to the topology. So because it is topology, it's not dependent on the Skimen size. But we have the dissipation related parameter d. So it looks like an exchange interaction. And we can exactly show that if the Skimen is very large, so the radius is large as compared to the micromagnetic domain wall width parameter, this d parameter is proportional to the ratio between the radius and the delta, the domain wall width parameter. However, this parameter cannot go to zero. It is a limit that has been shown by Belavin and Polyakov for exchange interaction. And actually, this parameter goes to n, the topology of the Skimen. So we can interpolate this d parameter, sorry, f should be d here, and that's a mistake. And we can interpolate with this formula that reproduce nicely the two limits, large Skimens and very small Skimens. And for the f parameter, which is related to the current induced force, we have this interval which looks to some Białości-Skimen area interaction. So f involves both the Skimen radius and the chirality. So the spin orbit torque force, and it is a general parameter. It is true also for domain walls, something that we have shown about 10 years ago in this group. This force is proportional to the chirality c and the radius of the Skimen. And if now we look to the consequences of this variation, I've shown that the velocity is mostly related to the ratio between the spin orbit torque force and the dissipation. And for large Skimen, it is constant. It doesn't depend on the Skimen size. But for small Skimens, it goes to zero. So it shows that small Skimens are expected to move much slower than larger Skimens. And for the dissipation, so rho is related to the deflection of the Skimen. The deflection of Skimen is supposed to be inversely proportional to the radius of the Skimens, but should not diverge close to zero due to the Belavin and Polyakov limit. Now I will show you some micromagnetic simulation where we consider a cobalt gadolinium alloy. So this is a transition metal rare earth alloy where the two lattices are antiferromagnetically coupled. So here you have some parameters of this system. We have explicitly a finite exchange coupling between the two lattices. We have a slightly different damping parameter. And very important is that the temperature, the composition variation of the magnetization of the two lattices. So they vary with the concentration. So we have, so in red, it is the variation of the magnetization in the rare earth system, and in black in the transition metal system. And we have a specific point where these two magnetizations are equal. This is called the magnetic compensation, and the total magnetization of the system now is zero. Due to the difference in G factor between these two chemical species, the angular momentum compensation do not occur at the same point as the magnetic compensation, but at a compensation which is a bit larger. It is, in our case, 79% of cobalt in this alloy. So now if we look to the size of the schema in this system, so we have a large bunch of simulation with different composition. This is the schema radius. And also we vary the DMI so that we can cover a large range of schema size. So we have schemas that are smaller than the domain wall width parameter, here this dotted line, or they can be larger. And what is interesting is that these curves are symmetric around the magnetic compensation point and minimum at the magnetic compensation point, because the magnetization promotes larger schemas due to the dipolar coupling. So this is why we have all this parabola shape. If from all these simulations, we calculate our three geometrical parameter N, D, and F, we can find that the expressions that I've shown before are working very well. We have scaling relationships when we plot versus R over delta, and all these points fall on universal curves. And we describe very well with our formula the real situation from the simulation. Sorry. My computer looks to be blocked. I'm sorry, I have a small technical problem.
No problem, take your time.
Yes, working. Okay. So now let's look to the dynamics and to the velocity. So this is the velocity, or what I call the mobility, is the velocity divided by the current density in the simulation versus the alloy composition. And we can see that whatever the Dialogin schema areas or whatever the size of the schemion, we have a peak in velocity at 79% of cobalt in this alloy, which corresponds to the angular momentum composition. So here on this scale, we have the angular momentum in the system. So when it is 0, we have a peak in velocity, and then the velocity decreases. On the side of the simulation, we also have larger velocities, because then the schema size is larger. And I've told you that we expect from the previous analytical consideration that larger schemas are more mobile. This is also what we can see if we look at a single cobalt composition. When we vary the Dialogin schema area interaction, the higher this interaction, the larger the schemas are, and then we have a larger velocity. So really we find that the larger schemas are more mobile. And you can see the dots are the simulation, the lines are the analytical calculation. There is a perfect agreement between the model and the simulation. Now, if we look to the deflection, we have around this angular momentum composition point a linear variation with the composition, which is expected because the deflection is proportional to the angular momentum. But for on the side of the simulation range, because the sizes are larger, then there is a reduction of the deflection because larger schemas are less deflected than smaller ones. Okay, again, sorry, I have difficulties to change my slides.
I think, can you please escape this sharing mode and then reshare once again?
Yes, this is what I will do. Okay.
Yeah, it should be okay. Yeah.
Yes, but now my PowerPoint has been closed. Oops, sorry. Okay. Do you see my slides?
Yeah, we can see.
Yeah, okay. So let's go to.
And we need Scormion-based computers badly.
Yeah, you're right. Okay, so now let's look what would happen because in an application or in most experiments, we work in magnetic tracks. It is easier to inject current in magnetic tracks. And we can use also this Thiel formalism with our effective equation to describe what happens in tracks. So in tracks, we have the gyrotropic deflection, the energy dissipation, the current-induced force, but we have also some repulsion from the edges of the magnetic track. So it will be this green arrow. And what happens is that in the steady state regime, because the skimmel is confined in the track, there is an exact compensation between this gyrotropic deflection and the edge repulsion. So these two forces are cancelling, and then the Thiel equation, the effective one, becomes simply the dissipation plus the current-induced force. So the solution of this equation is extremely simple. It is now exactly the ratio between the current-induced force and the dissipation, and it is proportional to this quantity. What is interesting is that in this velocity, we do not see the angular momentum. So as a consequence, we do not expect a velocity maximum at the angular momentum compensation. There is a strong motivation for antiferromagnets to provide more faster textures, which is actually the case for domain walls, but we do not expect it to be the case in tracks for skimmels. And now if we look to our simulation, so these open dots are the simulation in a free environment where there is a maximum in velocity at the angular momentum compensation. This should be 0 actually. And in a track, there is no particular feature. We just see a kind of parabola shape, which accounts for the skimmel size variation with the concentration of cobalt, which changes the magnetization of the system, but there is no peak. And we do not expect skimmels to be faster in tracks as compared to in antiferromagnet as compared to ferromagnets. So now let's look to another aspect, which is very specific to antiferromagnetic situation, is the possibility of a transient regime. So the initial state consider two skimmels that are perfectly aligned because they are antiferromagnetically coupled. And we need to arrive to a dynamical steady state where the skimmels are slightly separated to cancel the gyrotropic force. This is what was described in the previous equation. So to reach a steady state, we expect a transition regime with some characteristic time, which we would like to calculate. And in that case, there is a crucial role of the coupling force that we need now to express exactly. So let's go to this interaction force. We have two skimmels that are coupled, so in red and blue, and they are separated by a quantity which is delta R. So if we write the coupling energy, so M1 and M2 are the skimmel profile in the two lattices, and
Professor
because
Rohat, you have 5 more minutes.
Okay, thank you. This will be sufficient. If now we look to separation that are small as compared to the radius of the skimmels, we can approximate the second skimmel with this approximation, just a development. And then we find that the antiferromagnetic energy is related to the square of the skimmel separation and some factor. This is the dimensionless factor that we also found for the dissipation. So we know it. And then we have the force that derives from this energy. We just have to derive it. And this looks like a spring force. So it is linear with the separation. Here we have the plot of the force for different skimmel radius. For larger separation, instead of this consideration, we just have to look to the geometrical overlap between the two skimmel cores. So this purple area, and then we have this antiferromagnetic energy and this force. What is striking to note is that this force monotonically decreases in strength when we increase the skimmel separation. So actually, so this is these dotted lines, and we can see that the maximum coupling force that is possible in this system is actually this 4RJAF, and it is maximum at this separation, whether for large skimmel or small skimmels. So now if we look to the 2 Thiel equation model, now with 2 different velocities for the 2 skimmels, so maybe it's more convenient to have the mean skimmel pair velocity and the separation dynamics, the derivative of delta R. we can rearrange these two equations to find the new effective TIL equation. So here it is for a synthetic antiferromagnet. So we are exactly at the angular momentum compensation. So this is why in the effective equation, we have no gyro vector, but we have a new term, which is this term, proportional to the acceleration of the Schiemann pair. So this corresponds to the Schiemann mass, inversely proportional to the antiferromagnetically coupling. So it's a new term. So now we have a mass for the antiferromagnetic Schiemann, and we also have a transient time, which is a ratio between the Schiemann mass and the dissipation. In the steady state, it is the same result as before. The velocity is a ratio between the total current induced force and dissipation. And we have the separation, which is related to this force. We see that the velocity and separation are conjugated variables in the sense of mechanics, so they are completely related. And the antiferromagnetic energy plays the role of a kinetic energy. It is equal to 1/2 the mass times the velocity to the square. So if we put some numbers in synthetic antiferromagnet, the antiferromagnetic coupling is about 1 millijoule per square meter. So we expect a transient time of about 1 nanosecond. For a ferrimagnet or even for an antiferromagnet, the coupling, the antiferromagnetic coupling will be much larger, up to 1 joule per square meter. And then the response time is going to be very short, and we can say negligible, of the order of the picosecond. So now if we look to the simulation, we have the Schiemann velocity versus the time. You can see the transient regime for different strengths of the antiferromagnetic coupling. So the transient time increases when we decrease the coupling. This is the separation. So you can see that the separation increases with time and saturates in the steady state regime. And if the antiferromagnetic coupling is not strong enough, there is a separation between the two Schiemann. This is this black curve, and then the two Schiemanns are completely decoupled. Their velocity decreases, and they just live their life independently. And we can find nicely the relationship between the transient time and the antiferromagnetic coupling, and it is inversely proportional. And for the maximum velocity that we have noted in this system, we find that the maximum velocity is proportional to the antiferromagnetic coupling. So here for different Schiemann radius, so we expect this formula. And we can see also that from this formula, either from this part of the function, either for d, which increases with the Schiemann radius, the larger the Schiemanns, the larger is the maximum possible velocity in this situation. I would like to say that similarly for the transient time, this mostly concerns synthetic antiferromagnets. In ferrimagnets or antiferromagnets, the coupling strength is so large that we will not be bothered by the maximum velocity. Okay, so this is my conclusion. I've shown you a formalism to describe antiferromagnetic Schiemanns. And I think the most novelty of what I've shown you today is that we have some inertia Schiemanns. Antiferromagnetic Schiemanns have a mass, and as a consequence, they have a finite response time and a maximum velocity. So thank you all of us for your attention.
Thank you, Professor.
Thank you.
For this fantastic talk. So the session is now open for discussion.
Okay, I have a question.
Yeah, but Shubhankar, you cannot always take the privilege of organizing the talk and ask the question fast. Just
I'm
wait.
sorry.
You will be the second. Is there anybody? So you are the first, Shubhankar. I'm sorry.
Yeah. No, I saw that there is nobody.
No, I am there.
Yes.
I'll be the second.
Okay. So Stan, very nice talk. Thank you. Some new work. So I actually got confused in the beginning. In one slide, you said that the gyro force does not depend on the size, but later on you showed that the deflection is depending on size, which we know. So I didn't get this. Could you kindly clarify on this?
Yeah, indeed, the gyrotropic force doesn't depend on the size because it is related to. Sorry, I'm going to. It is related to the topology. So it is related to the angular momentum the thickness of the layer, and N, which is just the topology. So it is not, its strength doesn't depend on the size, but the deflection is not only related to the gyrotropic force, but it is the balance between the gyrotropic force and the energy dissipation in this system. And the energy dissipation, alpha D, is proportional to this D geometrical parameter. And this parameter, it varies with size. And for large schemons, it is linear with the size. So it is because the dissipation increases with the schemon size that the gyrotropic deflection decreases when you increase the size of the schemons, not due to the variation of the gyrotropic force.
Okay, one quick question, Suvankar. So I will ask this transient time. Sorry, I was a bit distracted with some phone calls. Could you kindly tell again the transient time, what we mean by that? And how is it affecting, let's say, in a rest track memory application?
Okay, we show that the schemons have, so in the TIL equation, we have a new term which involves the acceleration. So it means that when you switch on the current in the system, there will be some time for the schemon to accelerate up to the steady state regime. So if you want to do a racetrack memory application, it means that it will limit the speed, the possible speed of your application. So we can say that for a synthetic antiferromagnet, the speed limit of the application will be kind of limited to 1 to 10 gigahertz, not faster, because we have to let some time for the schemon to accelerate. The larger the antiferromagnetic coupling, the faster you can go. So if you can find some new materials to have a larger antiferromagnetic coupling, then you will be able to be faster. So for example, on the experimental point of view in our group, as a spacer for RKKY coupling, we don't use ruthenium, which is the traditional material for synthetic antiferromagnets, but iridium. With iridium, we have 1 order of magnitude larger antiferromagnetic coupling than for ruthenium. So with this iridium spacer, we should be able to be faster.
Okay, thank you.
Yeah, I just have a quick, not a question, just a query. So when you say that this maximum velocity is linear with the interaction strength, so do you assume that it has to be Jasinski-Moria, or it can be also the super exchange? The origin is not important, or it's important?
No, the origin is not important. In this formalism, it can describe any situation. It could be a SAF with RKKY interaction. It can be a ferrimagnets where the interaction is mediated by more direct exchange through the conduction electrons. It could describe also a real antiferromagnet. No, whatever. So just the limit, we comment the antiferromagnetic coupling here is given in joule per square meter because we describe the problem as in 2D. So if we have a bulk interaction, like in a ferrimagnet or an antiferromagnet, we just have to, the coupling interaction will be in joule per cubic meter. So you just have to integrate over the thickness of the sample, and then you've got your strength. So this is why, here I've said that for ferrimagnets, the antiferromagnetic coupling is about 1 joule per square meter. I have just integrated what is found from the literature on a typical thickness of, I don't remember, it was a few nanometer, and then you've got the coupling in the dimension that I use in my model. Okay, thank you. I think we don't have any more question, and thank you very much for this fantastic talk. Shubhankar, if you want, we can now have this moment.
Yeah, thank you so much, Stanislas. Please stop sharing so that we can share our screen, presenting the digital memento. Yeah, thank you.
Yeah, so thank you very much. So this says that the Symposium on Magnetism and Spintronics, SMS 2021, National Institute of Science Education and Research, NISER, Bhubaneswar of India, takes this immense pleasure in presenting this plaque to Professor Rohat. Thank you very much once again on behalf of the organizing committee. Thank you.
Thank you.
Thank you, Stan.
Thank you.
Yeah, so the third talk of this session, and this is the last talk of the session as well, is by Professor Puter. She is a staff scientist at Jülich Center for Neutron Science, Germany. Her research interest lies in the field of magnetism and surface physics that includes the transition metal oxide, nitrates, as well as metal thin films and heterostructure. Today, she is going to talk about thin films fabrication for users, possibilities, and perspectives. So, Professor Puter, it's now all yours. So, you know this, I will give you an alarm 5 minutes before, so after 20 minutes, okay?
Great.
Yeah. Thank you.
So I hope you see my slides. Can you give me some feedback?
Yeah,
yes, it's all fine.
Yeah, okay, because I'm not used to Zoom. That's why my problem. Okay, thank you very much for the kind introduction. What you see here on my first slide is the FRM2, the old atomic, and on the left and on the right, you see the new lab buildings, and the right one belongs to JCNS. And we just moved in this year, just for the people who know this area. And to be more precise, well, I belong to the Forschungszentrum Jülich, which is in the west of Germany. But the Forschungszentrum has an outstation, the Jülich Center for Neutron Science at Heinz-Meyer-Leibniz. It's Heinz-Meyer-Leibniz Zentrum, and we are located here near Munich. So today, actually, that was the first day when we had snow. So what my talk is about. Well, first I want to present you the MBE system, because this is the core of the thin film lab. I will introduce the transfer chamber, which connects the sample preparation to the neutron instruments. I will give some examples for thin film fabrication, and I will answer the question how to get samples as a user. So, I also want to thank Subanka Bedanta for inviting me to give this talk and for the collaboration. So these flowers are for you. So you might ask, why is there a thin film laboratory at JCNS? Well, this is a special service for neutron users, so that we provide also thin film samples. And how this is done, I will show in the end. So, and we also provide this UHV suitcase for transfer of samples which are sensitive to ambient air and measurements at the neutron instrument Maria. So you see here a sketch of the MBE setup, and this is a sketch of the main part of Maria, and there are about 200 meters in between, and this has to be covered. And this transport chamber looks like this, that you have a cube with windows which are suitable for neutron reflectometry. We have a wobble stick which also works like a sample holder, and we have here a UHV valve which then is attached to the MBE setup. So a measurement would look like this: that you first fabricate the thin film sample, then you transfer the sample into the sample transfer chamber. Then you carry everything. So this is about 10 kilos. You can easily carry this to Maria. And so this is the JCNS reflectometer. Then you measure the polarized neutron reflectometry at room temperature, and then you can transfer it back. And here's a picture on the right-hand side where you can see the transfer chamber lying in the magnet for measurement, ready for measurement. So the MBE setup looks like this. You've already seen this sketch. So we have 6 effusion cells. We have 2 E-guns with each 4 crucibles. And so that means you can put quite a lot of material inside, different materials inside this main chamber. So here's a list of elements which have already been used. But also this is this depends on the requirements, on the wishes of the user, what kind of samples we take or what elements are taken. So, and you introduce the sample in the load log, and then you can also, in the buffer line, you can also have low energy electron diffraction, and we have an OJ system. So this is kind of a standard system, but the specialty is that it's near to the neutron instrument. So, and what is also very, very easy and helpful is that we can write some kind of scripts. It's called recipes. For example, open a shutter, wait for some time, and then close the shutter. And this makes sample fabrication very, very reproducibly. So I want to show you now 4 examples of samples which have been produced with this setup and with my help. So first one is the PhD, part of the PhD thesis of Patrick Schöffmann. And where we wanted to fabricate a strontium cobaltate, and well, as you have 2 different elements which are in different effusion cells where you can set the growth rates individually, it's not that easy that you can have the correct stoichiometry. And for this system, we found a method how to improve the stoichiometry. So, for example, here we have cobalt strontium 1.3, and you see here on the left, you see the read pattern. So you see there's a lowering, and you have here the streaks from the thin film. And but you see additional spots, like here in A, you see some small spots. And we can correlate them with the AFM picture to these large islands on the surface. And we have some more spots which are correlated to this small spot. We have some larger spots which are now correlated in the real space to these small islands on the surface. So we have these two distinct spot patterns, and the question is now, what happens if we decrease the cobalt-strontium ratio? So this is now the ratio of 1.1, and you see in the read pattern that these large spots referring to these small islands have already gone, but these smaller spots referring to these large islands are still there. So. And well, if you compare these the samples in XRD, here we have the same sample in black, and then the red sample. This is a sample with the correct stoichiometry. You see, there's no difference, especially before. If you have a cobalt excess, we would expect some cobalt oxide islands. We have some cobalt oxide islands, and but they are not seen in the standard XRD measurement. So that means with read, we can say we are more sensitive than standard XRD measurements. Of course, you can tune this, but this is not what you normally do in your experiments. So we see that read is very sensitive to this stoichiometry, and if we now finally reach the correct stoichiometry, and all these samples have been cross-checked with Rutherford backscattering spectroscopy, you see that all these spots, these small spots, have disappeared, and we have a very, very nice read pattern. And you see as well that the AFM picture doesn't show any large islands anymore. So that means read enables the adjustment of growth parameters for stoichiometric growth. That means, for example, if you measure, if you want to have this 1-by-1 stoichiometry and you want to reach this, you first grow a sample on something which is, like strontium titanate or LAO. and then check the growth, and then you grow the sample what you really want to have. And well, if you ask what's about below this, if you have strontium excess, then the growth is amorphous. So this you see immediately with wheat as well. So the next example, what I want to show you is that we have produced iron niobium multilayers on a niobium buffer. And the idea is that you want to have we want to study this the proximity effect of this large superconductor to this heterostructure. So as substrate, we take arc-hard sapphire, and we grow at 800 degrees an epitaxial niobium layer on it, 50 nanometers. And then we grow at room temperature this niobium iron multilayer with, we have grown several samples with different iron layer thickness. So, but this growth is, unfortunately, it's amorphous. So to characterize the sample more, we did some XRD, and you can see it here that the niobium goes in one direction. You see the peak here, and it's a nice ferromagnetic system. And you also see here, if you observe the magnetization versus temperature, that there's the effect of the Meissner effect appearing at about 8.2 Kelvin. So finally, polarized neutron reflectometry was measured at different samples of different iron thickness. You see here the polarized neutron reflectometry measurement, and the outcome of this measurement is that you have the densities, the nuclear densities, which are here in black, and the magnetic densities, the magnetic moment, which is here in red. And you see these nice oscillations, and this is of the niobium layer. And what you can see is that there's a clear distinction, especially for the magnetism. If you have a layer thickness of iron of 4 nanometers, but below we have some intermixing, so that the magnetization is never zero. And yeah, so this is our result. We have a depth modulated iron niobium alloy for lower than 4 nanometers iron thickness, which is a weak ferromagnet with Curie temperature of about 100 K. And the proximity of the thick niobium layer leads to an intermediate phase between the normal and the superconducting phase. Well, originally we wanted to study something different, but we found no indications for antiferromagnetic coupling in contrast to these publications. But anyway, well, we learned a lot about the system. So the next is something completely different. This is iron nitride on LAO, which was grown in collaboration with a group in India of Mukul Gupta. And here we have produced iron nitride on LAO. Here you see the read pattern, which is very nice. And this was also studied by XRD. And the question in this case was, well, how does the growth method what's the influence of the growth method on this system, especially what about the magnetic moment of this iron nitride and the crystalline structure? And from the XRD, you see for all, you see this, there's a shoulder here. And so this is more or less the same for DC sputtering. This is the orange line. Then for MBE growth, or the last one is high power impulse sputtering. So with even higher energies than for DC sputtering. And you see all samples are ferromagnetic. This is seen here. The lowest magnetic moment is for DC sputtering. Then we have MBE growth. and we have the high PIMS, the high power impulse sputtering. So and then if you have a look on the structure, this is done with X-ray reflectometry. You see the roughness is here versus the method, and you see high PIMS has the lowest surface roughness. And if you go deeper in detail, then you see as well, this is the depth profile resulting from this measurement, that the intermixing layer, this is here with the LAO, is the lowest for high PIMS. That means for this special sample, it's not MBE, which is the best, which leads to the best samples, but it's this high PIMS. And this is the case because there's lower intermixing with the LAO, lower diffusion of the of the lanthanum. So, and the last example I want to give you is hydrogen detection in thin films by a neutron waveguide. So this sample looks a little bit the same as the other one with niobium. So we have a small layer of 3 nanometers cobalt inside symmetric niobium layers, in this case 25 nanometers, and it's covered with platinum. So, and what is done now is that the sample is exposed to hydrogen, and then the question is, what's the hydrogen uptake? How does it? How does the concentration of the hydrogen increase with time? And this you can resolve because especially the cobalt layer, or all of these layers, they change with the hydrogen uptake, and so the vector of momentum transfer, which is shown here, is modified, and you see it. Here's the concentration, and here's the shift of this vector of momentum transfer, and you can identify this increase of the hydrogen uptake by observing this change of the vector of momentum transfer. So how does this function? So what you measure is you measure the non-split flip channel. This is here in red, and what is more important, you measure the spin flip channel. This is here in blue, and you see here a resonance, and this is the resonance wave vector what is measured. And then if there's an uptake of hydrogen, which is shown here in this picture in the middle, so we start with the red curve, and then after some time you see the decrease of the wave vector, and this can be recalculated here. It's done here. So you have this wave vector versus time, and you also can derive the concentration in atomic percent within the sample. So what we have is an in situ study of the hydrogen absorption kinetics in niobium thin films at the constant, in this case, at the constant pressure of 0.2 millibars. And yeah, then of course, you have to discuss for this method advantages and limits. In principle, this works for various materials, this method. There's no need of fitting the neutron reflectometry curve, and this is really, it's more easy. Everybody who's done PNR fitting knows this. It is a fast measurement. You have the possibility to study in situ dynamics, and the limit of the detection is down to 2% of hydrogen. And this you can also see here. So this is a slightly different sample with thicker niobium, but you see here that the sample, the virgin sample and the 2% sample, they still overlap, but then you see the shift of this. So you cannot make a clear distinction, but then afterwards at higher percentage, you can make a distinction. And only a small Q range is necessary. So, and the limits are that it works quantitatively only in the small concentration range. That means below 30%. You have, well, for this method, you need a neutron source, and it's only a thin film technique. So these are my examples. And then you might ask, how does the thin film laboratory work? How can I get access to this? And this is now done, shown here. So you are the user, you have a scientific idea, and then you ask me as an instrument scientist, is the sample feasible? So, and there are some questions which have to be solved. So what about the complexity of sample fabrication? So if there's, and the next one is growth investigation required. For example, if you have samples which are very complicated and where you really can make a master's thesis about of getting the right sample, this is too much for this kind of proposals. Then you have to solve answer the question handling of the deposition materials. So if they are very toxic, it's a problem. And if the vapor pressure is rather high, but sorry, it's rather low. But apart from this, well, we can discuss everything, and then finally you end up with a proposal submission, and then there's two possibilities. You can either produce the samples.
So Puta, you have last 5 minutes.
Yeah. Okay. Yeah. Thank you. Yeah, we have a collaborative access, and the other possibility is remote access, and then finally you get your sample. So, and well, I said you have to write a proposal, and this you can do at mlz.garching.de. There's always the combination that you have a Newton measurement, you apply for a Newton measurement and MBE sample fabrication. And there's another possibility. This is this proposal is within the nanoscience foundries and fine analysis. There you even get some financial funding, and you can also combine with other methods which are offered within this project. So I'd like to summarize. I gave you an overview about the possibilities in the thin film laboratory at JCNS in Garching. I've shown the fabrication of different materials like strontium cobaltate, superconductors, iron nitride, and I've shown a method to detect hydrogen. I've shown you the transfer chamber, and I hope that we can start a collaboration soon. Thank you.
Thank you very much. This is a very nice and informative talk. So the session is now open for discussions. Yeah, you may ask the question directly. Yeah, Subhankar, you may start, please, if you have.
No, I think Souvik has a question. Souvik,
yeah, please, Souvik, please.
Yeah, very nice talk. I had two related questions. I was curious about your vacuum suitcase. I was wondering, why would you need it, in the sense that if you have very air sensitive material, could one not just cap the sample and do the neutron reflectometry? Like, have you seen very big differences that led you to build this vacuum suit?
With respect to these samples which I've shown you, they are all have all been measured without the suitcase. But the idea is, well, actually there are also already some proposals, for example, to measure some monolayers of iron on certain substrates. And if you have just one monolayer or two atomic layers of material, and if you want to carry this to the MBE, to the neutron reflectometer, you're lost. This oxidizes immediately. And for this case, we have done this, we have produced this. Actually, well, there is a proposal about this, and well, the reactor has not yet started again, and I hope it will start next year, and then we will measure within the transfer chamber.
I mean, the question was, can you not cap the sample? Like, can you not put a very thin layer of, let's say, silicon or aluminum oxide? And
sorry, no.
There is big differences in neutron reflectometry data fitting or something. That was the main.
Well, if you want to measure just, for example, sorry, I did not get a cap. If you there's many studies about capping of magnetic layers with some other material. You change the you may change the magnetic moment, you may change the anisotropy, you may change the easy axis, whatever. So it's completely, you can do this, but then you have a different system.
Okay, sure. And the related, just have you tried to do neutron diffraction on a very thick, thin film ever? Like, have you, is it even possible? Like, can we expect some neutron diffraction results for maybe if you can grow very thick the film? Have you ever tried, or maybe?
I personally haven't done this, but I know that this has been done, and you can get also results from this. There is tomorrow there will be Ixi Su, and maybe you ask him about this because he's the expert on this.
Okay. All right, thank you.
Thank you.
May I ask a question?
Yeah, please.
Yeah. How is this niobium film grow? Is the layer by layer growth?
You mean the buffer layer?
Yeah.
I never checked really if we have oscillations, intensity oscillations. I should do this, but I have not done. But you see, it's grown epitextually, yeah.
Oh, okay, very good. So it's grow by MBE, right?
Yes, it's all what I've shown here is grown with this. I don't know if you should still see my slides.
Yeah.
So it's done with this MBE setup.
Okay, good. Thank you.
You're welcome.
Yeah. Shubhankar, you wanted to ask something.
No, I'm fine.
Yeah, there is a question from Jayanarayan Mukherjee. You may ask the question directly if you wish, or I can read it out. Okay, so this is a technical question. How many times these proposals are open in a year?
This is well, as they are these two possibilities, and for this NFFA thing, there's the next deadline is the 1st of December, and this is I think it's 3 or 4 times per year, and for the other this is 2 times per year, as far as I remember. But they change due to this corona. Everything is changing. So. The easiest way is to go to these 2 websites and have a look there. Or if you have further questions, please contact me. So you see here my email address. Just contact me.
Yeah, thank you. Thank you very much. This is a very important thing. Yeah, so if there is no question, let's thank the speaker and then you can present the memento. Thank you so much for this nice talk. Yeah, can you please share the screen, Shubhankar, for this memento? Yeah. Yeah. So this is the virtual memento for you. It's from the organizing committee of National Institute of Science Research, Science Education and Research, NISER, Bhubaneswar, India, for this conference called Symposium on Magnetism and Spintronics, SMS 2021. Thank you very much once again.
Thank you so much, Sabine. We also like to present a small memento before I announce something to the previous chairman of the poster session, Professor Chandrasekhar Murapaka. So Abhishek, if you could show the memento for Chandra. Yeah, so thanks Chandra for chairing the poster session 1 today. It went very well. So Symposium on Magnetism and Spintronics, NISER Bhubaneswar takes immense pleasure in presenting this plaque to Professor Chandra Murapaka for chairing the poster session 5. Thank you so much, Chandra.
Thank you, Shubhankar. Thank you so much.
Thank you. And we like to also show the memento for the current chairman of the current session, Professor Shubhankar Chakrabarty. You did a fantastic job. We have really like 20 minutes of break for the next session. So
yeah, that is what you told me to do, right?
Yes, thank you, because we really need breaks. And in the meantime, when they share the screen, in the meantime, I like to announce the three speakers: Professor Andrzej Majewski, Dr. Stanislas Rohat, and Dr. Sabine Putter. I request you three to join the room number 2 in the frame platform, because we have like nearly 20 minutes as a small break till the next session starts. So I think there will be probably some virtual interactions there. So I request you to go there, and that will be very kind of you. So, okay, here we have the memento for Subhankar Chakrabarti. So Symposium on Magnetism, Spintronics, NICER, Bhubaneswar, India. Takes immense pleasure in presenting this plaque to Professor Subhankar Chakrabarti in appreciation for chairing the session 6. Thank you so much, Subhankar.
Thank you, Subhankar.
Thank you all the speakers, and we will break now. And whoever wants, you can go to the virtual platform frame, room number 2. So Professor Andrzej Majewski, you go to zone 2. Professor Stanislas Rohat, you go to zone 3. And Professor Sabine Putter, you go to zone 4 of room 2. The links have been given in the email today. And our volunteers are there in case you face an issue. It's a little bit like video game. You have to play around, and we meet there. So we will resume our next session exactly at 7 o'clock. The speakers will be
8 o'clock.
Sorry, at 8 o'clock. I'm
Right,
sorry.
right.
Where the chairman will be Professor Subham Majumdar. He's already there. The speakers are Professor Antonio Azevedo. He is also there. And Professor Dipankar Das Sharma, he will be joining shortly. He's actually in California, and he would be like waking up just shortly. And then Professor Pranam Muduli. So very exciting talks also ahead. And thank you all for these very nice talks so far. And we will resume again at 8 o'clock. Let's meet in the virtual platform. Thank you, Subhankar.
Yes,
See you
yes.
later.
Thank you. Thank you.
You can
Bye.
continue the Zoom link, because it's the same link for the
Right.
next session also.
Right, right. Bye.
Thanks. So, hello, Sunda.
Hello, how are you? Yeah.
How are you?
That's fine.
Thank
So
you so
can you hear me?
Yes, I can hear you.
Okay, fine. So
just maybe we wait a minute because some people probably are leaving from the virtual platform.
Okay, so, no problem. Yeah, I'm waiting. Yeah.
Just a minute. Thank you so much, first of all, for taking time, because I know you are really busy with family.
No, it's okay. It's fine. Yeah. Yeah.
And I think I saw that.
Antonio has already joined.
Yes. Hello, Antonio.
Hello, Antonio. Can you hear us?
Yes, that's great. How are you guys?
Yeah, fine. Thank you.
Great.
So what's the time? What is your
11:30?
11:30. Okay.
Yeah. It's great time to us.
Okay,
yes, it's not too bad. Actually, it's 8.5 hours and it's not bad.
It's
I
great.
planned that
Wow.
way that you can finish your talk and go for lunch.
Yes.
That's
Okay, I think we begin now. So I formally welcome you all to the last session of today. I think it has been wonderful set of lectures from this afternoon. Really, thank you so much to all the speakers. And we have 3 more exciting talks in this session. And the session will be chaired by Professor Shubham Majumdar, who is a senior professor at Indian Association for Cultivation of Science at Kolkata. And he is very famous for his work on multiferroids, calorics, and so on. Many interesting physics he does. And I'm really grateful to him that he has little bit family health emergency, but still from that he managed time to join in this conference. I'm really grateful to you, Professor Majumdar. And now I will leave it to you, as you have realized that the talks will be 25 minutes. So kindly give a alarm to the speakers at 20 minutes so that we have a few minutes for the discussions. Okay. So now it's all yours. So kindly coordinate the session. Thank you so much.
Okay. Thank you. Thank you very much. And welcome you all to this is our today's last session, I think. And can you, okay, I think some problem with this.
Have you received the CV?
Yeah, I have received the CV.
Okay. Yeah.
Thank you. Yeah. Okay. This first talk will be delivered by Professor Antonio Azevedo. Professor Azevedo is a full professor from Federal University of Pernambuco. Okay, I hope my pronunciation is right. He's full professor since 2014, and he has done his PhD from UFPE, Recife, in the topic on nonlinear dynamics in spin waves. And he was a research associate at Data Storage System Center at Carnegie Mellon University, Pittsburgh, and working with Mark Kreider in magnetoptical recording media and processes. He's also a fellow of National Council for Scientific and Technological Development. And very importantly, he is an editor of our magnetism journal, JEEE. So his major research interest is nanomagnetism and spintronics. And without spending more time, I request Professor Azevedo to kindly present it. Your talk will be 25 minutes, and at 20 minutes, I will give you an alarm, and you have a 5 minutes question answer section. Professor Azevedo, please.
Thank you, guys. Thank you, Subhanka, for the invitation. Hello, everyone. I'll try to keep my time. So I'm going to talk about interface-driven spintronics phenomena. I'll try to follow this outline, as I'm supposing that there are many students in the room. So I will try to make an introduction. And
I'm sorry, Antonio, to to interrupt
Yes.
you. Would you kindly go in the presentation mode?
It's not in there?
No.
Oh, what should I do?
If you just click the presentation mode, it should go.
Presentation mode. That's great.
Yes, now we have. Thank you.
I'm sorry. So I'll try to follow this outline, and I'll give you some an introduction and motivation and spin to charge current conversion. I'll talk about some spin pump interpretation that it's a very known issue, but it has some misunderstanding in the interpretation of the measurement. So later I will give you example of application that we have carried out, we have performed, and later I will talk about 3 preliminary results that we are measuring right now. Case of bismuth and orbital Hall effect and topological Hall effect, and later I come with the conclusion. So Recife is here. It's far away from you guys. It's a city full of rivers. It's quite hot. Probably it's like your city also. And that's it. So just let me show you previous slide, few slides about the ferromagnet normal metal bilayer, which can be interpreted as a playground for investigation of the spintronic phenomenon. The ferromagnet layer can be a metal, can be a metal, can be an insulator. The normal metal can be different materials, even magnet materials such as permalloy or antiferromagnet materials. The magnetization can be perpendicular or in plane. And in the ferromagnet layer, you can excite ferromagnetic resonance, spin waves, and so on. You can investigate its switching, transport, anomalous Hall effect, anisotropic magnetoresistance, and so on. If you flow a current to the normal metal layer, you create a spin current perpendicular to the interface, and can be injected the ferromagnet material. If the magnetization is put to process, it can inject a spin current into the normal metal layer by the spin pump effect, and you can create a charge current perpendicular. Also, you may have at the interface the Hash-by-Edelstein effect if you have interface with high-speed optic coupling. So it's a very simple system to investigate all this phenomena. You may also apply a thermal gradient perpendicular to the interface, so you can transfer the spin current by what called the spin Zibek effect, and it creates a charge current perpendicular. It's important to mention that the spin Zibek effect, the injection of the spin current by spin Zibek effect and the spin pumping are quite similar, but they have fundamental difference. In the spin Zibek effect, you have an incoherent injection of the spins. In the spin pump effect, you have a coherent injection speed. This makes a huge difference sometimes. So you may also have an interplay between the spin current and the spin waves, and this is good to investigate the spin current phenomenology using spin dynamics. So let me remind you the spin, just few mechanisms of the spin current generation. One is in the local geometry, in which inject a current to a ferromagnet, produce ferromagnet layer, and it propagates through this normal metal, and eventually it reaches the second ferromagnet layer, and the voltage can give information about the state of the second ferromagnet magnetization, layer of magnetization. The other mechanism is called the spin Hall effect, which was proposed in 1971, and it was discovered in 1999, and it was discovered experimentally in 2004. So in this case, you have a charge current, and due to this scattering, it separates the spin in perpendicular direction. So a charge current generates a spin current. The other mechanism is spin pumping, in which you put the magnetization to process, it injects a spin accumulation into the nearby media, and due to this inverse spin Hall effect, you can generate a charge current perpendicular. It's a very convenient mechanism. For instance, if you have yttrium iron garnet, which is a very convenient material to investigate the ferromagnetic resonance, you may generate a very nice inverse spin Hall if current into the, for instance, this is platinum. In this case, we have 0.1 micro amperes of current generated by this effect. So the other effect is very important here is the spin-opt interaction. The spin-opt interaction is a very investigated phenomenon in solid state. For instance, when you are in the solid state material, the spin-opt interaction is proportional to the potential, the electric potential, which in solids depends on the symmetry of the material. So if you have inversion asymmetries, like for instance, an interface like this one, you may have a huge Hashba field. The Hashba field seen by the electron in his reference frame is given by this equation here, which is not so visible, but it's okay. So the Hashba Hamiltonian, this is the interaction between the Hashba field and the magnetic moment. So if you solve the Hamiltonian problem, so you can see that the dispersion relation of electron splits into spin up and down. So if you take a look at this three-dimensional spin density of the states, you can see that, for instance, here you have a spin down and spin up, spin down and spin out. They are separated, they are split due to this Hashba effect. But there is a very nice paper which was published in 1990 by Edelstein, in which he prevents that an electric current may induce a spin magnetization. For instance, what is called the direct Rashba-Edelstein effect, if you inject a charge current in an interface, you may generate a spin current, a spin accumulation. So this is right when we inject a spin current, the Fermi surface shifts in opposite direction to the current, and it creates a overpopulated population of spin parallel to the y direction. The inverse effect is also possible. If you inject a spin current, it generates a charge current. This is called Rashba-Edelstein effect, which is an interface phenomenon. It's very, it can be very strong in some interfaces. So let me talk about the spin pump interpretation. The spin pump interpretation can be very difficult if you use ferromagnetic metals due to the two reasons. One is the galvanomagnetic effect. So the Lorentzian line shape disappears, and also the ferromagnetic metal can generate it by a self-induced spin charge conversion. It can generate a voltage that sometimes, most of the time, it's confused, and the people say that they are measuring the spin pumping effect, but it's not spin pumping effect. So in order to get rid of this spurious effect, you have to use ferromagnetic insulators. For instance, this is a very nice spin pumping curve obtained in yttrium iron garnet, which is an insulator, 100 nanometer thick, and platinum 2 nanometer thick. So very nice Lorentzian chip. So a signal generated by inverse spin Hall effect must obey this equation. If it doesn't obey to this equation, the origin is something else. So now let me go to, let's see how long I have in time. Okay. Let me move to some results. And I will give you results on spin pumping, spin current to charge current conversion in some two-dimensional materials. One is the graphene, lithium iron garnet graphene bilayer. So graphene is the most perfect two-dimensional material. And to grow in single layer of graphene on top of YEG, on top of lithium iron garnet, we followed this procedure here. First, we grow single layer of graphene on copper by using MOCVD technique, and later we deposit the PMMA layer on single layer of graphene. We remove the copper by using this acid, and later we put in the bath of DI water to remove all the scratches. And this is step in which we have to use the lithium iron garnet to fix the graphene layer on top of YEG. It needs some tricks. So later we put in the acetone bath and remove the PMMA, and we get this nice graphene layer on top of YEG. For instance, this is a STM measurement of a single layer of graphene on top of GGG we got here. Actually, the YEG has to be very smooth. It has to be very good quality material. So this is the Hammond investigation showing the YEG GGG here on the bottom, and here graphene on silica, for instance, it appears the two peaks characteristics of the graphene, and also graphene on YEG, it appears these two peaks, which is a confirmation that we really have YEG on top of it, graphene on top of YEG. So then we measured the transport property of the single layer of graphene. We know that graphene has no magnetic property, but we measured by using lock-in technique, we measured a very nice signal from the magnetoresistance. We calculated this signal from a magnetoresistance, and it works fine. Later, we did measurement of the spin pumping voltage, and we also detected that graphene can convert spin current into charge current by this Hashby-Adderstone effect, inverse Hashby-Adderstone effect. We calculated the figure of merit, which is 10 to minus 3 nanometer. And we also deposited permalloy. Actually, we deposited graphene on top of silicon oxide and deposited permalloy on top of silicon of single layer of graphene. And also we make some measurement of the spin pumping. In this case, for instance, the line width is not a Lorentzian line shape, so you have to take care to separate both effects. And this is a good indication that graphene can be used for investigation in Spintronics phenomena. Also, we have investigated the disulfide molybdenum, which is a material, is a semiconductor material with direct gap. In this case, we fabricated two electrodes of gold. This is the scale bar here is 20 micrometer, and by exfoliation, we put MOCO2 in this gap here, and we make measurement of transport property, which is a good ohmic contact. These are the ferromagnetic resonance of the YEG film before put the material on top and just after putting the material. This is the spin pumping effect or the spin pumping measurement. So disulfide of molybdenum can be used as a good material for conversion of the spin current to charge current. Also, we concluded that this effect is due to hash by Ederson effect. And this was published in the APL 2 years ago. Now let me talk about another system that we have investigated, which is the topological insulator Hormoloi bilayer. In this case, we got the topological insulator materials from the Jagadish Mudera's group at MIT, which is 6 quintuple layers of this material here. And here in Recife, we deposited an island of Hormoloi on top of this material, and we investigated the spin pumping effect in this material. Also, we investigated the spin-Zibek effect. Also, when we apply thermal gradient perpendicular to the plane, these are the spin-Zibek effect measurements. And so also we investigated that in this case, the Hash-Bell-Delsin effect is inverse. Hash-Bell-Delsin effect is responsible for the conversion of the spin current to charge current. And we published this few years ago. Also, this year we published a paper in which we deposited Bi2 Se3 on top of yttrium iron garnet to investigate the signal of the spin pump investigation. So we detected that the polarization of the current generated in Bi2 Se3 is opposite to the signal of platinum, and is the same signal as tantalum. For example, here is I'm showing you. And we also investigated Hormoloi, and it works fine. So also we investigated, in spite to be granular, the material is the charge conversion probably is due to the surface states of the topological insulator. Now I would like to show you 3 issues that I have enough time. Yes, 3 different issues that we are working now. We are interested now. Actually, these are very preliminary results. One, we were motivated by this paper published by Charles Chien, in which he actually is a perspective paper published in APL materials, in which he concluded that bismuth is transparent to spin current. There are many papers published in literature showing that bismuth is a very nice paper, is a very nice material to convert spin current to charge current. But my conclusion also is that those papers need to be rewritten. So here I'm showing you the titanium is the largest Z material before the unstable. Like bismuth, I'm sorry, bismuth has the largest diamagnetism, also has a huge spin-off cap. And so bismuth should be a great candidate to convert spin current to charge current, but this is not true. Also, bismuth has the largest Seebeck coefficient. So be careful if you are using bismuth to investigate the spin-Seebeck effect. Here are measurements in which we measure the spin pumping voltage in bismuth, yttrium iron garnet bismuth. As you can see here, the signals are not explained by this equation here. We would expect, thank you. We would expect that at 0, the voltage should be positive, and at 108 it should be negative. Both voltages have the same signal. So this is a clear indication that this is due to the thermal effect, because bismuth has a very large Seebeck coefficient. And the thermal effect comes from the heating of the egg layer at the ferromagnetic resonance. This is a very old paper that I published many years ago, in which I have investigated the profile of the radio frequency magnetization in a YAG film. Is, as you can see, the uniform mode is concentrated here, and it hits a little bit. If it hits a little bit, 0.1 Kelvin, for instance, it can generate 7 microvolts of voltage. So if you intend to publish, to work with bismuth, take care of all these things. I'd like now, in the few minutes, talk about these two other issues that I'm working on. One is the orbital Hall effect, which is very hot issue. We are investigating ferromagnetic insulator, platinum, and different materials on top of it. We are using Spintronics effect, the spin Hall effect, and also transport properties. And so, as the results are too preliminary, I'm not going to show you here the results, but the results are very exciting. I hope I can show you the next slide. So the other thing is the topological Hall effect. Topological Hall effect needs special samples. For instance, if you use pure egg on top, platinum on top of pure egg, you get this nice spin pump results. But if you have a egg doped with praseodymium, it becomes very, very soft, as you can see here. In this case, you do not obtain the same result as obtained by pure spin pump, by pure egg. Why this happen? I'm supposing that due to the easy plane of egg praseodymium, it creates some texture, magnetic texture, that deviate the current generated by the spin pump in only one direction. This is just a supposition. I don't have it. I'm not sure about this. So topological Hall effect, you need to have very nice samples, and this is an issue that needs to go deep into. I hope the next time I can talk about this. So just a conclusion. As Pauli said, interfaces were invented by the devil, but I would say that interfaces were left to be exploded. And I have just shown that the spin charge current conversion can be a very fundamental phenomenon to investigate physics at interfaces. And I just mentioned to you guys 3 phenomena that we are investigating at this moment. The role played by bismuth, orbital Hall effect I didn't show you, but I'm investigating the topological Hall effect, which are issues that I hope at the next time I can talk to you the results. So I would like to thank my students, to doctorate student master, and I also would like to thank the financial agents that give support to my investigation. Thank you. I think that's just finished in time.
Thank you very much for very nice talk. And actually, this is would be very good for the students. Actually, the introduction part, I think that will be very helpful for students. Even I didn't know many things. So now the session is open for questions, and you can directly ask the question, or you can put it in the chat box. So whichever you like.
Okay, can I ask a question? If there is
there is a question from Avishek.
Okay, please take his question.
Yeah. How did you rule out the possibility of ISHE in yttrium garnet molybdenum S2 flames?
Actually, we have to investigate. Actually, we have to investigate the line width increasing, and we have to investigate it. And the line width increasing, if it happens, is due to the spin Hall effect. But in this case, we have just few layers of MOS2, and the lambda, the spin diffusion length calculated if you use conventional spin Hall effect, inverse spin Hall effect, it's very short. It's much smaller than the thickness of the sample. So in this case, the only explanation for the spin charge to charge current conversion is due to this the inverse Hash-Bell effect. So it's just a calculation. Okay, if you calculate the spin diffusion length. So in this case, the spin diffusion length is related to the increase of the ferromagnetic resonance line width. So the lambda is very, very short. So it's incompatible with the thickness of the MOS2.
Yeah, I mean, just a comment. Abhishek is doing his PhD in our group, working on MOS2 thin films prepared by sputtering, so large area production. So Antonio, you are taking exfoliated films, which are probably very like a few monolayers or even a monolayer limit. But for us, it is like thick film, several nanometers, several monolayers, you can say. And we see a strong indication of ISHE. Still, we have to analyze and publish, but probably he's asking that. Of course, maybe thickness plays a role. When you go to the monolayer limit, maybe the Rasbach coupling is playing more. I have one quick question related to the bismuth-selenide. When you grow the bismuth-selenide, I believe on top of the egg. So was it polycrystalline or it had the quintuple structure?
It's polycrystalline. Actually, it's here. This, as you can see here, it's like a these particles. This,
okay.
As you can see here, several groups have grown Di2SE3 by using sputtering, obtaining the same phenomena. So in this case, the interface is between the grains, which we are supposing that the topological Hall effect is occurring at the interface of the grains.
Okay, I mean, probably you may be aware that
May I ask a question?
Yeah, just to finish. So we are also working on bismuth-selenide prepared by electron evaporation. And last year we published a paper where we showed that it has very large inverse Rasbach-Edelstein length. I will send you that paper, Antonio.
Ah, okay. Thank you.
Yeah, thank you so much.
Antonio, may I ask a question?
Yeah. Of course.
Yeah. For the bismuth measurement that you're showing that is due to the Seebeck effect is dominant, is that right?
You mean here?
Yes.
No, this is a spin pumping.
Yeah, you show it's a spin pumping, but your conclusion is since it's independent with this angular there's no big no significant.
You mean bismuth selenide?
No, bismuth.
Bismuth. Okay, I'm sorry. This one here.
Yeah, this one. So for this observation, you showed this is mainly due to the Seebeck effect, is right?
That's right. That's right.
Yeah. May I ask that? Did you use
here? I'm showing you. Here I'm showing you. Here I'm showing you the voltage measured between these two electrodes as a function of the radio frequency power.
Okay.
It should be 0 at 9 degrees when the angle is 90 degrees, and the voltage should invert here.
Yeah.
So if it cannot be explained by this equation, it's something else.
Okay. Okay. Good. Yeah, because we are working on this as well. Yeah.
Really?
For the signal, it's indeed very small. Yeah.
Great. We can. Please send me an email. We can talk about this.
Oh, yeah, good. Okay, thank you.
Okay. Thank you, Hachi.
Okay, I have a question, small question, just query. So in this, regarding this transparency of spin current to this bismuth, silver, or bismuth, I think copper, yeah, this paper.
This one?
Yeah, this one. So is it a non-local measurement or a local measurement? I mean, can you rule it out by making a non-local measurement?
Actually, you have to be careful to remove the thermal effect from the bismuth. In this case, Chien used a spin-Zibek effect, and he was very careful to isolate the bismuth from the ferromagnet layer, from the measurements.
Okay.
Actually, he used an oxide layer, in which you can flow a spin current through.
Okay. Okay, fine.
This is a very nice review.
Yeah, exactly. So I don't find any other question. Is there any other question? Okay. If not, I think we thank the speaker, and I ask Professor Azevedo to please, and we have a pleasant duty to do. Okay. This
old photo.
Okay, the Symposium Magnetism Spintronics, and I read this spec. This National Institute of Science, Education and Research, which is called NISER, Bhubaneswar, India, takes immense pleasure in presenting the plaque to Professor Antonio Azevedo, Federal University of Pernambuco, Brazil, in appreciation for being a valuable speaker to give a lecture on interface-driven Spintronics devices. Thank you very much, Professor.
Thank you so much, Antonio. Very nice.
Thank you, guys.
Thank you.
Nice to see you.
Nice. So, Shubhankar, this DD is in, or?
Yes, I'm in.
There you go. Okay.
So good morning.
This is Shubhankar.
Good morning.
And I have to introduce you. Okay.
In the meantime, I'll share my screen.
Okay,
can you hear me clearly?
Yeah, we can hear you clearly. Very clear.
But I'll leave my video off simply because the bandwidth is very small where I'm talking from. And I tried once to switch on the video and it's logging me out of Zoom. So it's better that I leave the video off. Okay.
Okay. So no problem. Okay. So our next speaker is Professor Dipankar Das Sharma, and we more commonly know him as DD Sharma. So, and he'll be talking about dynamically disordered magnetic state in sub-K regime in strongly interacting system. And Professor DD Sharma, he's a professor of Indian Institute of Science, Bangalore, and he's one of the most prominent condensed matter physicists in India. And his main research interest is spectroscopic studies of strongly correlated electron system, and it can go from oxides to any other transition metal oxide, sulfides, selenites, and so on. And he uses many tools, and he also does some theoretical calculations as well. And he uses photoemission spectroscopy, inverse photoemission spectroscopy, X-ray absorption, Auger electron spectroscopy, scanning telenin spectroscopy, and so on. And it is it is indeed nice to mention that he has more than 480 scientific publications and with an H index of 80. So this is a Google Scholar source, and he's presently in the editorial board of several scientific journals, which include Advanced in Condensed Matter Sciences Journal Electron Spectroscopy, and related phenomena, solid-state communications, Journal of Physical Chemistry, Advances in Physical Chemistry, and so on. And he is recipient of various awards. I'm not mentioning all of them. That will take a long time. So he's a fellow of all the academies of India, and he's also a fellow of American Physical Society APS from 2007, and he's the recipient of Shanti Sharup Bhatnagar Prize, which is the highest prize for the scientist in India. And without spending more time, let us go to Didi and listen his talk. Didi, please.
Thank you, Shubham, for a wonderful and embarrassingly long introduction. Thank you for your kind words. And let me start by thanking Shubhankar and his team for organizing this fantastic conference. I'm sorry that I cannot be present personally, and I'm at a remote corner, far away from you with a 13.5-hour time difference. And as my video is not working. So I apologize to the participants for that, because the video seems to log me out every time I'm trying to switch on the video. Already the title of the talk has been given out by Shubham. What I'm going to talk about is a dynamically cooperative paramagnetic state. And I'll try to point out why it is interesting or intriguing at some sense to find such a state even in the sub-Kelvin regime in a strongly interacting system. When I talk about strong interaction, because Shubham pointed out that much of my life, scientific life, I've been spending trying to understand strongly interacting systems, but those in the context of strong electronic interaction. But here, the strong interaction that I'm referring to is actually strong magnetic interaction. And I'll point out to you as I go along and show you what I have in mind. I'm not being able to find out the laser pointer, but can you see the cursor that I'm moving on the screen? Is the cursor visible?
Yes,
Shubham?
yes.
Okay, wonderful, fantastic. This is, of course, my affiliation. I'll not spend time on that, but let me point out the funding. Funding at various forms have been supported by different agencies rather generously over many decades, and in particular by Science and Engineering Research Board in terms of my JCBOS fellowship, and Nanomission have funded us very generously over the years, Department of Science and Technology. More recently, for about 3 years, we had this private funding, Jamshedji Tata Trust, that was critical for many of our studies. And now very recently, CSIR, the Bhatnagar Fellowship, is supporting our research. So I'm very happy to acknowledge the contributions that make it possible for us to study various scientific topics, of which I'll be talking about one that we're rather interested in recent times, and we're spending a lot of time. So I'm going to talk about a specific system where you have had early success in trying to understand rather unusual ground state, magnetic ground state of a material. Let me get on to the topic. Now it was changing, now it is not changing, so maybe I escape, nothing is changing. Sorry, it just froze. I assume you can still hear me. I'll stop sharing and come back once more.
We can hear you.
You can hear me, fine. It had stopped sharing for some reason, stopped allowing me to change the screen. Maybe I can change. Participant can now see your screen, but it's not allowing me to change. Why that is happening, I do not know, but let me try.
Should we share our screen and play your PPT?
Just let me make one more attempt.
Yeah, okay.
If that would work. That also didn't work. Maybe then you. Okay, one last attempt. If it doesn't work this time, then Shubhankar, use share the screen and I will go along. Okay, Shubhankar, can you go ahead? I'll stop sharing the screen and you project it locally, because though it first changed, but now it has stopped changing the screen.
Please just give us a minute.
Yeah, sure, absolutely.
And
I anticipated this problem, and that's why I sent you the
it's
file.
unfortunate.
While you're trying, let me I don't know if there's anything that I can do. Speaker view. Share screen once more, last attempt. No, it doesn't work.
Just a second.
Oh, it does. It's working now.
Okay.
Oh, it's you or me?
No, it's you.
Ah. It got scared. Shubhankar, it got scared when you threatened to show it. So let me continue, okay?
Yeah, please.
So basically, as Shubham pointed out, that we have been working on strongly interacting electronic system, mainly in transition metal oxides, and they provide a fantastic playground for controlling different degrees of freedom. The different degrees of freedom that are available to us in the context of electronic and magnetic properties are, of course, shown over here: the spin, charge, orbital, lattice, and topological degrees of freedom. This strong interaction, what it does is to take these different degrees of freedom and couple them together. So they're not independent quantity, they talk to each other. And this coupling allows you to have excitations, for example, light excitations, which would normally couple to the charge and orbital degrees of freedom. But with light excitation, you can get a response in the spin degree of freedom, simply because charge and orbital and spin are coupled together. So depending on what energy input you give, in what form, there are different forms you can do: electrical, light, optical, mechanical, thermal, or magnetic excitations. And you can get responses and properties which could be magnetism, electricity, light, mechanics, and heat out of it. And this has given rise to many, many different kinds of concepts of electronics. Remember, electronics is a very simple one where electrical input couples to the charge input, and that gives you an output that is also in the electrical sector. But this coupling of different degrees of freedom allows you to give an input in one sector, get an output in another sector, and there are different kinds of electronics that is being talked about, and much of this conference is related to the Spintronics aspect. But there are other kind of electronics that one can construct out of this strong coupling, like magnetic electrics, topological electronics, quantum computing, motronics, etc. And in this large scenario phase space of various materials, one can try to rationalize in terms of a few parameters, trying to understand in broad terms how the system evolves. This is one axis, and the reference is given below, where we understand fairly well now that strongly interacting electronic systems, where this axis that changes the Coulomb interaction, the interaction between the electrons, where we know that when the Coulomb interaction, T is the hopping parameter, it's just a normalization factor, a scale, energy scale of the system, that if the Coulomb interaction increases, you can start with a simple metal or a band insulator, and then that metal, if it is a metal that you started with, for large values of U, would become a Mott insulator. We understand this scenario rather well. There's another axis, which is the spin-orbit coupling strength, lambda, again expressed in the terms of the same energy scale. We know that you can start with a simple metal or band insulator, and it can become a topological insulator driven by the spin-orbit coupling. But interplay of spin-orbit coupling and Coulomb interactions together can give rise to a very wide variety of very interesting ground state various kind of materials. For example, the action insulator, Y semi-metal, topological Mott insulator, and quadrupolar insulator. It's basically, this is spin-orbit coupled Mott insulator phase, where both U and SOC are important. And in that, there is the spin liquid phase, and this spin liquid phase is the one that I'm going to talk about today. So this is the part of the phase diagram that we are going to focus on. And we have been searching for spin liquid systems for a long time. Let me tell you very briefly what the spin liquid is all about. We know that when there are magnetic moments on a lattice, these magnetic moments interact with each other, and that interaction can be ferromagnetic or antiferromagnetic in most of the cases. Depending on if it is a ferromagnetic interaction, then the ground state would be a ferromagnetic alignment of the magnetic moments. At some temperature, there'll be a transition from a disordered paramagnetic state to an ordered ferromagnetic state. The interaction very often in oxides, particularly in insulators, are antiferromagnetic, as shown by this blue and the red nearest neighbors. They have opposite spin alignments. That is what favors the energy lowering, and that gives rise to an ordered antiferromagnetic state below a certain ordering temperature. This is what we expect. But imagine you have a lattice which is not square lattice as shown over here and is a triangular lattice. On a triangular lattice, you know, sorry, you can anticipate that if I have the nearest neighbors connected in such a way that there's an antiferromagnetic interaction between them. Now, what would happen? Now, imagine that this is a blue up moment, this is a red down moment. Now, the question is, this one doesn't know whether it will be up or down, because as you can see, if it is up blue moment, then there's an antiferromagnetic coupling satisfied here. So the energy is lowered with respect to this interaction, but with respect to this interaction, which wants it to be antiferromagnetic, it's a ferromagnetic arrangement. And one may say, okay, then put it as down, then this antiferromagnetic interaction is satisfied, but this one is not, becomes ferromagnetic. And you can see that whether you put up or down, in the two energies of the two configurations are identical. So there's a degeneracy in the system which does not prefer up or down, and they have the same energy. And that is called the frustration. So the frustration is coming from the fact that the ordering is not being able to set in because the energy of the two ordered state that you can anticipate are equal. And so there is nothing that's breaking that degeneracy. So the system gets frustrated and cannot order. But in fact, if it is a classical spin, which can point in every which direction, actually this triangular lattice, I can make a triangle. This is just a triangular cluster. But if I make a triangular lattice like here, it actually orders. It orders in a particular way, which is called the 120 degrees order, with 3 spin sublattices. You can see that there's a red sublattice where all the spins are moments are pointing the same way. There's a blue sublattice that are pointing all the same way, and green sublattice that is pointing the same way. And the relationship between the red, blue, and green are a 120 degrees rotation. Classically, this will be the ordered lowest energy state, and the system does order. There's a reason why a system likes to order at low enough temperature. If you go to low enough temperature, classically, there is no contribution from the entropic contribution is decreasing. So the tendency to disordering is decreasing. So it tries to find an ordered state to lower its energy. But if the system is quantum, and then the spin cannot point in every which way, then in fact, P.W. Anderson in a classic paper showed that a very unusual magnetic ground state forms, where it is a linear superposition of all possible kind of pairwise antiferromagnetically coupled state. For example, this one shows a particular segment of the lattice that these two are antiferromagnetically coupled, these two are antiferromagnetically coupled, these two are antiferromagnetically coupled. And like that, nearest neighbor antiferromagnetic coupled state combined with, and every possible such configurations combined with also farther neighbor antiferromagnetic states coupled with even farther neighbors, etc. This kind of a linear superposition gives rise to the lowest configuration, a ground state of such a quantum mechanical system on a triangular lattice. And this, as you can see, doesn't have any obvious ordering, but it's a very well-defined state, magnetic state. And this state is called a quantum spin liquid state. And recipes for quantum spin liquid state in general is that it has to be a quantum spin state. And that's why people look for in the spin half systems, because that is as quantum as you can get in the spin systems. One looks for large spin orbit coupling. So people have been looking for in the 5D, 4F, and 4D systems primarily, less in the 3D systems. And of course, frustration is absolutely necessary, because if there is no frustration, then the ordered state, which is either ferromagnetic or antiferromagnetic, will take over at a lower temperature, and you'll get a simple ordered state. And one of the very popular frustrated lattice is the Kagome lattice that I'll not be talking about much. The system I'm going to talk about will not have, it's a copper 2+ system, it's equal to half system. So it is a quantum spin system, but it has a very small spin orbit coupling, so it does not satisfy this part. And it is not on a Kagome lattice either. In fact, it will be on a triangular lattice that I'll show you. So the fact that I'm violating these two essential normal wisdom where people look for quantum spin liquids. So what is the recipe that is actually giving me this unusual magnetic ground state that we seem to be finding is actually, we believe, disorder. Now, we know disorder in a magnetic system normally gives rise to a spin glass-like system, because you have frustration and you have disorder and you have all kinds of magnetic interactions, and that tends to give rise to the system in a spin glass state, as we know from magnetic studies of many, many decades. But what I'm going to show you that in this particular system, disorder seems to promote a rather unusual ground state, which has some resemblance with what I have talked about in the title, that it will be a dynamically cooperating paramagnetic state down to very, very low temperatures. So we came to this compound, Y2CuTiO6, in search of quantum spin liquids, but I'll tell you the whole story now. There's a history to this particular compound in our group. In fact, Devraj Chaudhary, who is a faculty member at IIT Kharagpur now, for his thesis work, was looking at this compound and had published a couple of papers, but he was looking at more the dielectric properties, which are very, very interesting of this. But we'll not talk about the dielectric properties. Devraj had already noticed something unusual, that the coppers did not seem to order within the studies that we had done at that time. But the specific work that I'm going to talk about is a collaborative work between our group and IIT Bombay, Professor Mahajan's group, and driven by the two brilliant students, Akmal Hussain and Kundu, from the two places, and aided by many other people like Sumiran Pujari, Professor Sumiran Pujari from IIT Bombay, Pranav Kirti, who's now working with Stuart Parkin's group at Hale. We have ICTS from ICTS in Bangalore, Shubha Bhattacharya, SN Bose National Center, Priya Mahadevan, and various experiments that we did, muon spin rotation at RAL and PSI. We have Peter and Joe Christoph, Michael Benitz from MPI CPS, and from Uppsala, we have Joshi and Roland Matthew, who have contributed to this work. And I'm very happy to acknowledge their contributions. This particular sample, there's a typical X-ray diffraction pattern that you see, that you can refine it. I'm not going to spend much time on it, except for pointing out that it has this P63CM crystal structure with these lattice parameters. What that amounts to for what is relevant for our study is that this is the crystal structure that it has, where these are the yttrium ions, these large gray spheres. These blue spheres are where copper and titanium sits. And you have these and the oxygens that connect up this network. The symmetry around this is a bipyramid with a triangular base. And I'm going to show it to you in a moment. And also what is relevant is this oxygen-oxygen distance and the separation between this copper and that copper. You can see that this copper titanium layer is far separated from that copper titanium layer. And let me show it to you in a more expanded version here. So you have the copper titanium layer here and the copper titanium layer here. They're separated by 5.74 angstrom. That's a very large distance for magnetic interactions. And that magnetic interaction has to take place through these oxygens. So basically you can have this copper hop to oxygen, that hops to yttrium, hops to this oxygen, and then hops to this copper. And that will be the pathway for the interaction. And that these oxygen-oxygen separation is also quite large. So basically what one is saying that the interaction between the layers would be weak. So it's essentially two-dimensional, and one can estimate what the magnetic interactions are. And we did estimate the nearest neighbor within the plane. The interaction strength is in the order of about 34 Kelvin and antiferromagnetic. And between the planes, the interaction is about 1 Kelvin and antiferromagnetic. And these estimates lead to an estimate of the Curie-Weiss temperature for this material of about 104 Kelvin. The experimental value, as I'll show you in a moment, is 134 Kelvin, saying that these estimates are reasonable estimates. So for a moment, if I forget about this third dimension, which is of course very important for many reasons, but take this layer out and look at its structure, this layer, it's then you can see that it's a perfectly triangular lattice. These blue squares where the copper titanium lives are all arranged in a beautiful triangular lattice. These oxygens that couple them are in between, shown by red. So you have a triangular lattice, which I've shown leads to frustration with copper and titanium. But the point is, every blue site is not occupied by copper. 50% of the sites are randomly occupied by copper, and remaining are occupied by non-magnetic titanium 4+ ions. And that is the disorder that you are talking about. So think of a perfectly triangular magnetic lattice and think that 50% of the sites are randomly replaced by non-magnetic ions. And that is what we are looking at in this particular system. In general, in this case, if I forget about the disorder promoting a spin glass-like state, one could argue that actually the frustration would be decreased. Why? Because imagine that you had copper in all of them, magnetic ions in all of them. That's a frustrated triangular system. Now, one of them is randomly replaced, so this is a non-magnetic one. Then there is no frustration because these two can be antiferromagnetically coupled, and since this is a non-magnetic ion, there should be absolutely no problem, and the system should be able to order locally. So in general, the disorder here, it's not a trivial way one can think about it, and it can increase the ordering tendency, it can decrease the ordering tendency via the spin glass-like formation. So there's a lot of competition that comes in because of the disorder. And let's see what actually happens. And like remaining 5 to 10 minutes, I'm going to finish off and I'll tell you what the real situation is experimentally. Experimentally, this is a susceptibility in blue, and this is the inverse susceptibility. You can see that inverse susceptibility shows a clear Curie-wise behavior in the high temperature, and that high temperature, if you extrapolate, you have a Curie-wise temperature is 134 Kelvin. The relevance of that is to say that the magnetic interaction between the copper-copper sites are in the order of 134 Kelvin. So one would expect a magnetic ordering in this system unless something very unusual is happening in the order of 134 Kelvin. And our theoretical estimate also of the magnetic interaction is in that order, as I have pointed out already. But this susceptibility, either this blue one or the red one, doesn't show any ordering down to 2 Kelvin that we have measured in this particular case. So though the magnetic interaction scale is 134 Kelvin, down to 2 Kelvin, which is much, much lower than the magnetic interaction energy, the system still doesn't order, which tells you that it's a very unusual state, that though there is a very strong magnetic interaction, it does not order down to 2 Kelvin. This leads me to the question of it must be because of frustration that the ordering temperature is getting suppressed. And experimentally, people tend to quantify this frustration as a parameter. How do you do that? You have a temperature axis shown over here. Imagine that in this temperature axis, the Curie-wise temperature is sitting here. And suppose because of frustration, normally one would expect the ordering to take place if there's no frustration in the vicinity of this temperature, but it doesn't happen. If there's frustration, it can lower that temperature. And its extent of lowering is a good measure of saying how frustrated the system is. And you can immediately see that I can then take a ratio of this one to that one and call it the frustration parameter. More lowered TC is larger is F, the frustration parameter, allows me to estimate what a frustration parameter. Frustration parameter 10 is large, 100 is larger, 1000 is even larger. Normally, people talk about the system is frustrated when you have an order of magnitude suppression, which means F is in the order of 10. In this system, already we know, since that TC is below 2 Kelvin, because down to 2 Kelvin it does not order, and theta is in the order of 134, it's already, you can see, is very strongly frustrated. It's about 70, the frustration parameter, much larger than the 10, much larger than an order of magnitude separation, right? Nearly 2 orders of magnitude separation. But you can try to go to even lower temperature and trying to see where the ordering takes place. Before doing that, here what I'm showing you is susceptibility at 3 different frequencies. And these 3 different frequencies are right on top of each other, the data points. That there is no frequency dependency, despite the fact that there's 2 orders of magnitude change in the frequency, saying there's no spin glass-like behavior, because otherwise we would see the irreversibility is showing up and dependency on the frequency of the measurement. That doesn't happen, so there is no glass formation either. So we cannot talk about that the ordering is not setting in because the system is getting into a glassy state. That is not true. And as I said, the frustration parameter is greater than 67. We measured to lower temperature. You can see that here the measurement is down to 0.5 Kelvin. ZFC and FC data are right on top of each other, telling you that there's no irreversibility. That means there's neither any ordering nor any glassy state formation. And now that the temperature of the ordering is pushed below 0.5 Kelvin, that tells us that because there is no ordering down to that temperature, we have the frustration parameter going from 2 Kelvin to 0.5 Kelvin essentially lowers the upper limit of estimate by a factor of 4. And so you have a frustration parameter that's now 268 or larger. So it seems to be an extremely frustrated system for reasons that is not yet clear. And trying to understand that behavior even to lower temperature, near ground state behavior, we looked at the muon spin rotation data. Here is the muon polarization as a function of temperature, time, and we can see that at zero field, how the depolarization happens as a function of time at different temperatures. And the depolarization rate can be extracted by fitting, which is the solid lines that also I'll show you in a moment. But what it shows is that if the system would order at any temperature, we know that here is a picture from somebody else's data in another compound that orders in the same structure, actually yttrium manganate. When the system orders, you will see that this kind of oscillatory behavior, which doesn't show up here at all. And that means that even down to 0.05 Kelvin, we don't have any ordering, which means that the frustration parameter is close to 3000, which is one of the spectacularly high frustration parameters. So the system does not order down to 50 millikelvin, though it has a magnetic interaction temperature which is more than 100 Kelvin. So that's really the spectacular aspect of it. And we can extract the depolarization rate, which is given as an inverse of microsecond. You can see at the height, and that is extracted from this fitting that I said, exponential fit, and it behaves this way. At the high temperature limit, we see the expected slowing down of spin dynamics. So that at high temperature, you have a paramagnetic system, the spins are fluctuating rapidly. As you lower the temperature, they're fluctuating more slowly. That's the expected behavior. But as you reach the low temperature, there is a saturation. Now it becomes decoupled from the thermal bath. And even though I'm lowering the temperature by more than an order of magnitude, the fluctuations has become limited, and the fluctuations are intrinsic, and they're not only more thermally controlled. Because if it was thermally controlled, then as I lower the temperature, I would expect it to go that way, as in the high temperature it was happening. But it shows that now it is a dynamically fluctuating state that it has reached, and down to the 50 millikelvin, it retains that particular state. So it's a strongly coupled cooperative fluctuation that is thermally decoupled and continues to fluctuate right down to the lowest temperature. So that is what we seem to be finding. And then we look at what is the nature of this state. We look at the specific heat. There's a specific heat where the lattice contribution has been subtracted. You can see that the magnetic contribution is essentially zero when you're at 20 Kelvin. And if I integrate the specific heat, of course, I can then figure out what is the entropy released as we are going from low temperature 50 millikelvin to about 20 Kelvin. And we expect that to become 100% if all the entropy is released between this temperature and that temperature. But you see that actually it is only 15% that is released, which would imply, of course, by this time, the complete entropy of the magnetic system must be realized. That means that at this temperature, 50 millikelvin, I still have 85% of the entropy trapped in the system. So there's a huge amount of entropy that remains unquenched down to, in this particular case, not 50, sorry, 350 millikelvin. So it's a very, very highly disordered, cooperative, fluctuating, strongly coupled blob of magnetic state that you are realizing at this very low temperature. So what is the nature of it? They do not order, they do not seem to freeze. That, again, by analyzing the specific heat, and let me go through a bit more quickly for the sake of time, that this is the magnetic entropy that we are plotting in log-log plot. And we see this behavior of the magnetic entropy at the lowest temperature, which looks like T to the power 1.4. And in fact, all the magnetic specific heat contribution to the specific heat scales together as a function of T over H, as shown here. If you have this expression looks a little strange, but actually this is what is expected from random singlet ground state. And the exponent here, 0.7, is exactly what is expected. So it looks like that what it is we're being able to reach in a triangular lattice via disorder, of a strongly coupled triangular lattice via disorder, is a random singlet ground state. Not only that the specific heat has this scaling behavior, it turns out that even magnetization is a function of H and temperature. For different temperatures, these are for different temperatures, 2 Kelvin, 5 Kelvin, 10 Kelvin. They all map onto an universally scaled feature when you plot it over H over T and have this particular configuration. And if I now take this scaling and the specific heat scaling together, right, you'll see that this mt to the power minus alpha, and here the specific heat is H to the power gamma. This alpha plus gamma turns out to be equal to 1, which is actually what is predicted for a random singlet state. So what it seems really that we are being able to reach a random singlet state. We have realized random singlet state, mind you, is actually theoretically known to exist on one-dimensional systems. Here is a two-dimensional system which also has a weak coupling at third dimension, and the coupling strength is about 1 Kelvin. So we are probing a temperature scale that's lower than the coupling between the layers. And via the disorder, we seem to reach a magnetic state that is very similar to what is expected from the random singlet state. And with that, let me summarize by pointing out that low dimensionality, and I have said 2 minus in the sense because, if you have a two-dimensional system and you've disordered it to 50%, you have a dimensionality that is not quite two-dimensional because you're breaking the dimensionality. Aided by the disorder in the system, because you're putting in non-magnetic ions in the system, it seems to lead to a dynamically cooperative paramagnetic state down to 50 millikelvin in this particular system. With that, let me thank you for your attention. Thank you very much.
Thank Professor Didi Sharma for this wonderful talk, actually, and also the wonderful introduction. And this session is now open for question and discussion, and anybody can ask question or write in chat box. So Didi, this is not a metallic sample, no?
No, this is highly insulating, highly insulating.
Highly insulating. So there is no chance. I mean, this is all super exchange.
Yeah,
so,
yeah.
Okay. So
it's all super exchange dominated. That's right.
And so,
yeah. Just one question.
Yeah, please.
So, is it possible somehow to estimate the freezing temperature for the spin liquid state? And if so, then how much it is for this one?
See, specifically one says that there is no freezing in the spin liquid state. That's why you would call it a spin liquid, because if it freezes, we'll call it the glass state, right? So the point is that we are putting an upper limit down to 50 Kelvin. We are seeing that it does not freeze. So at a even lower temperature, it may freeze, but down to this 50 millikelvin, we know that the system is not freezing, and it's in this dynamically cooperative paramagnetic state where freezing hasn't taken place. It's dynamic, but there's a cooperative, because you saw the lambda saturate. So basically, it's not anymore. The dynamics of this spin system is not controlled thermally. So there's a lot of dynamics which will not remain if it is a frozen state.
Yeah, so then can we confidently say that even if we go to 0 Kelvin, it will still not freeze?
One can say with reasonable confidence that it will, but we do not know at what temperature. And the funny part of it is that why does it survive down to such low temperature? You know, when the magnetic interactions are so strong, and one would have expected it to freeze at a much higher temperature because of frustration and disorder, but it doesn't seem to. So down to 50 millikelvin, it doesn't. There's a hand raised by Dr. Soom.
Yeah, please. Thank you so much.
Hello.
Any question? Any more question?
Yeah, there's a...
Yes.
Please, please.
Yeah, really beautiful talk. Thank you so much, Professor Sama. Yes, really enjoyed to hear your talk. Yeah, my question is, okay, trying to come back to a little bit about this chemistry, okay? Because you have copper, titanium at the same site. Copper is 2 plus. What is the valence state of titanium? Because titanium 3 plus can be also very quantum too. Is 3D B1.
Absolutely,
okay?
Absolutely. You're absolutely right. And this is a question that you have addressed carefully because it would be important. It turns out the titanium is in 4 plus state, almost certainly, to the extent one can see by experiments like X-ray absorption. If you do at the titanium 2p edge, which has very characteristic fingerprints of whether it's titanium 3 plus or titanium 4 plus, it looks like all titanium 4 plus. Or if you look at the X-ray photoelectron spectroscopy, it looks like all titanium 4 plus. And the other point is that if it would be titanium 3 plus, for example, because you'll have a titanium 3D state occupied, which will have a distinct valence band spectral feature close to the Fermi energy. Even if I, like yttrium titanate, because I think you are a chemist, so I can talk to you about very quickly about yttrium titanate also, which is a titanium 3 plus state, which is a D1 system, and we know exactly, and it's a highly insulating system. So this is an insulating system. So it's a D1 system if yttrium titanium 3 plus would be there, and that would have a nice clean signal very close to the Fermi energy with a gap because it's an insulator. That also is not there. So all the indications are that it's almost purely titanium 4 plus.
Okay. Yeah, this I'm totally convinced by your data. This is no doubt about your. Second question is, I mean, okay, because as you said, this is a pretty anti-intuitive, okay? Because the disorder, as you mentioned, usually leading to spin freezing at ground state. But I mean, here you somehow helped this quantum fluctuation. But my question is there any theoretical proposals has been put forward to explain this, okay, to interpret this? For instance, you probably should also know very well in the paracolo community, we have also a lot of this disordering factor, okay? For instance, for lung chromas, rare earth, because this is subject is prone to the local distortion. But in principle, in turn, you could use that distorting to create a very dynamic state, okay, which is not frozen as a ground state. The trick is, of course, but of course, this is a transition metal. I'm just really extremely curious because it's so interesting. Okay, so some theoretician must be so excited to come in to think about a kind of theoretical framework to interpret this.
True. I mean, I know that, in fact, we are investing a lot of effort in collaboration with a couple of very good theoretical friends We do discuss some possibilities, but not any rigorous theories in this paper that we published in PRL year and a half, 2 years ago. But we've been studying it a lot more since then. And in particular, two of my colleagues, Professor Kedar Damle from TIFR and Professor Shubhra Bhattacharya J from ICTS in Bangalore, they're looking at it, and we're trying to understand that, because, okay, I sort of hint at it at some level, that if we have a two-dimensional system, of course, and if I don't have any anisotropy, then Marmin-Wagner helps me in keeping the system disordered, right? That would be a trivial statement that if you have a purely two-dimensional system with no anisotropy, then the system cannot order because of Marmin-Wagner theory. But that's the reason I pointed out that it's not a purely two-dimensional system. We have a third-dimensional coupling strength, which is 1 Kelvin, and I'm probing down to 50 millikelvin. Yeah, and I'm probing down to 50 millikelvin. Again, several orders of magnitude lower, and it still retains this very unusual state. And that's why it's still intriguing. So to answer directly your question, no, we don't have an understanding of it, but we are trying. And I would be very interested.
Okay, perhaps it's just, for instance, for the pure two-dimensional triangular Heisenberg model, okay, it's not ordered if you have only nearest neighbor exchange J1.
Yeah.
But as soon as you add J2, this is second nearest neighbor.
I know.
At certain strengths, you start to order, have this, exactly. You mentioned 120-degree phase.
Yes.
My question is, if you consider J2 also in, if the J2 somehow in competition with your JC, okay, perpendicular exchange, then you frustrate this, let's say, a smaller perturbation of exchange. Maybe the system really becomes so random you cannot order. But I do not know. Okay, has any theoreticians considered this?
We have evaluated the JNNN as the next nearest neighbor.
Yes,
it's finite. It's actually okay. The problem of Y2 CuTiO6 is a problematic one because it's a disordered system, and you cannot order 50% on a triangular lattice.
Okay.
So the estimate needs to be done on a superlattice on one realization of the disorder. Right. So it's a little more complicated, but let me simplify it by mapping it onto another system, which is very well studied, yttrium manganite, which has the same structure. So I have a 100% triangular lattice, so I can estimate what the next nearest neighbor interaction is, and we have done that. And I can give you the numbers also. The nearest neighbor is in the order of 30 to 40 Kelvin interaction. The next nearest neighbor interaction is actually quite strong. It's about 1/4 or 1/5 of that. It's not very small. It's in the order of 1 to 10 Kelvin. Okay, and whereas the perpendicular direction, the out of plane interaction strength is about a Kelvin or a little lower. So it's all in that ballpark. So the next nearest neighbor interaction is sizable for the kind of temperature scale that you're talking about.
Okay, fine.
Yeah, thank you. Thank you very much. It's really an honor to hear your exciting talk. Thank you so much.
Very kind of you to say that. Thank you ever so much.
Thank you, Professor Didi Sharma. And I have a nice job to do. And Shubhankar, can you share? Yeah. So this is the play for you.
Thank you very much.
So I read it. Symposium on Magnetism and Spintronics, SMS 2021, National Institute of Science, Education and Research, Mysore, Bhubaneswar, India. Takes immense pleasure in presenting the play to Professor Dipankar Das Sharma, Indian Institute of Science, India, in appreciation for being a valuable speaker to give a lecture on dynamically disordered magnetic state at sub-Kelvin regime in a strongly interacting system. Thank you very much.
Thank you very much. Thanks a lot. All the best to you guys.
Sure.
Thank you.
So I think we can go to our last speaker of this session, and he's online. Professor Mudali, are you on? Yeah.
Yes, yes.
Okay.
You can hear me?
Yeah, I can hear you. And so Professor Pranava K. Mudali. He's from.
I'm done. I'm done.
So he's from IIT Delhi, and he joined in IIT Delhi in 2012 as an assistant professor, and he received his PhD degree in physics from Humboldt University, Berlin, Germany in 2005, and he did postdoctoral research works in the University of North Carolina, USA, the Royal Institute of Technology, Sweden, and the University of Gothenburg, Sweden. He's a member of IEEE. Yeah, is there a problem? Can you hear me? Yeah.
Okay, okay, thank you so much.
Yeah. And his current research interest includes spintronics and nanomagnetism. And I mean, he's interested in spin Hall effect, spin pumping, skyrmion, spintronics, and different areas of spintronics, spin torque, induced magnetization dynamics, etc. And I request Professor Mudali to start his presentation. Professor Mudali.
Okay. Thank you very much, Professor Muzumdar, for the introduction. And also thank the organizer for giving this opportunity to talk about our work. I would be talking about skyrmions today. And also I thank all the audiences who are here for waiting for this talk. So because it is a little bit late from Indian time point of view, but probably not that late for European time and so on. Okay, so I'm going to talk about our work on recent work on ultrafast nucleation of single and multiple antiferromagnetic skyrmions. And let me start the talk. And I know that there are some students in the audience. So let me start with one of this picture, which was simulated in micromagnetics. This is a domain wall. You take a thin film, you introduce exchange energy and anisotropy, and you see this blue and red region here, which is basically the blue is represents one domain and the red is another domain. If you zoom in here, for example, if you look closely, this is how it looks like. This is one domain where the magnetization is of the are aligned in one direction. Here is aligned in other direction, and this is the domain one. Now what I do is I introduce something called DMI, which I will explain in a moment. And then suddenly you see that you see some small circular particles. And now the circular particle has kind of rainbow looking. So they unlike here, there are only two colors. Here, actually, these circular particles are multicolor, indicating that they have, if you actually zoom in closely, then you will see they are actually some kind of particles. You can call it particles. I will explain why they can be called particles. So basically, you have some spins which are oriented in certain way, and they are all very similar spin structure. So, and those are called so-called skyrmions. And so obviously, as you can see from this simple analysis, that you need this DMI to get these skyrmions, and the skyrmions are presently attracting a lot of interest in the Spintronics community for various applications, including racetrack memory and neuromorphic computing and many other applications. So the main ingredient for this is DMI. What is this DMI? So this may not be known to some of you, so I would try to explain very briefly what it is. So you know that the DMI basically stands for Yeltsinski-Moria interaction. And I start with first the Heisenberg interaction, which is actually the interaction that is responsible for ferromagnetism. So we have two spins, and then there is a Heisenberg interaction between them. Then depending on the sign of J, you can have it. The spins will be parallel, and that is what leads to ferromagnetism. But in certain cases, you can have a different kind of interaction which is known as DMI interaction or Yalanskiy-Moria interaction. And this interaction, the Hamiltonian looks like this, where you have a cross product of the two spins, and there is a tensor here, Dij. Since it's a cross product, now the minimum energy of this will actually require the two spins to be orthogonal to each other. So it favors the perpendicular orientation of the spins, Si and Sj. And this D here is actually a vector. As I said, it's a tensor. It depends on the local environment around the magnetic atom. And it's usually, this interaction is actually an indirect interaction, and it requires a crystal inversion, lacking of the inversion symmetry. So as an example, from an application point of view, this symmetry is actually lacking. If you take a heterostructure, for example, a ferromagnet and a heavy metal, then there is a lack of symmetry at the interface, and at that point, you can have something called interfacial DMI, IDMI, and that has been found to be quite significant, and this is the one which is attracting a lot of interest recently. So how do you know that the system has this kind of DMI interaction? So one way to know this is actually is possible to make some brilliant light scattering measurements. Here I am showing one of our previous work where we had managed to measure some DMI interaction, interfacial DMI interaction, in a very simple system consisting of formalin and graphene. And this work was done in collaboration with Professor Anjan Burman, where this BLS measurements were done. And we could show that there is a rather unusual interfacial DMI, which is driven by the defects at the interface, and that is present in this system. So, now coming back to that DMI interaction again. So if you have enough of this DMI interaction, there is a competition between the exchange interaction and the DMI interaction, which can lead to formation of these skyrmions that I was showing before also. So this is what is that skyrmion is. So let us look at the skyrmion in a little bit more detail. There actually happen to be two kinds of skyrmion, depending on how the spins are rotating. So the first one is called block skyrmion, and in which the skyrmion structure looks like this. So as you can see, the red represents spin down, and the blue color here represents here spin up. So the core is pointing down, and as you go towards the periphery, it is slowly moving, pointing up. But the way how it moves, that is what determines whether it is block skyrmion or nil skyrmion. For a block skyrmion, the motion will be like this, so which means the spin will rotate perpendicular to the radial. So this is the radial direction. So the spins are rotating perpendicular to that radial directions, and this is called the so-called block skyrmion. And if it is, however, rotating along the radial direction, then we call it as a nil skyrmion. So and that's what this is the line profile, which clearly shows that how the motion is happening. The interesting point about this skyrmion is that if you take the different orientation of the spins within this object, you can map out a sphere. So you will have, as shown in this animation, you take this individual spins, and you can actually completely feel of the spheres with the directions of the different spins from this structure. Now, so there is something called this topological charge. Maybe you already know about this from the previous talk. This topological charge basically describes how is this orientation are in the inside this skyrmion structure, and mathematically it is usually expressed by this equation here. And since it actually describes this complete sphere, so if you calculate this quantity, it will actually come out to be some integer, and so it has an integral number, and this is a requirement for the skyrmion. It has to be integer, either plus or minus 1. And we say that it is a topologically protected. So that means what it means is that if you want to break this skyrmion, you need more energy. So there is an energy involved in breaking this skyrmion. So basically, this will act like one particle, and as if you have a one ball that is there in the system. So this is what is the, and obviously it is stabilized by, it requires different kind of energy exchange, Zeeman, anisotropy, Doppler, and DMI. And I will show you one example of our work where we consider a nano disk, and then we vary this K and D, where D is the DMI constant and the K is the perpendicular anisotropy constant. And for a certain range of these two parameters, you get this Fermion, this rainbow structure here. You can look at here. So whereas you can of course get a lot of other structures, but these Fermion structures are stabilized for a particular choice of parameters. Okay, now so these Fermions were first observed in the bulk MNSI, and this was in 2011. This was where the first work was reported, and this was, however, observed at very low temperature. And now we are in 2021. Now there has been a lot of reports, and there has been many reports where this Fermion has been observed in simpler system involving this interface, as you can find from this review article, where it has shown several images of Fermions from different metal systems. And these are actually, many of these are actually observed at room temperature now. So this can be routinely observed in the room temperature nowadays. And in fact, one of our work from India is probably very early work, and also only work, as far as I know, where we could show evidence of this Fermions using magnetic force microscopy, and then we could also reproduce the results using simulation in this Hochschild alloys CF cobalt to aluminum iron. I just want to highlight this, but I'm not going to discuss about this in detail. So now these Fermions are actually useful for application, I told you, and one of these application is that you want to use it for memory application, so-called restrict memory. I'm not going to discuss that now because you might be knowing about this. But basically what you need for that application is that you need to move this Fermion. And this is a very early study by Albert Fort group in 2013, where they showed that if you take a Fermion, this is a numerical study, and you apply a current, so you can exert a torque on this Fermion, and you can move them, and you can see that they're moving nicely in this track. But soon after, it was realized that this is now an experimental result from 2017. You can see that these Fermions are actually, if you move, actually this is the Fermion, and as you pass the current, and this is you are seeing at different time, this Fermion is actually moving towards the edge, and it will actually finally at this end it will actually collapse. So it is not really moving in the straight line. It is actually, there is a transverse component velocity that is being added, and this is what is found in experiment. So and this is known as so-called Fermion Hall effect, because the motion of this Fermion is going transverse and 90 degree to the direction of the charge current. So this was first observation of the direct observation of this Fermion Hall effect. And why this arises is the following. Actually, as I told you, this Fermion can have a topological charge of q is equal to plus or minus 1. And normally the motion of this Fermions is basically discussed in terms of this so-called Cayley equations, which looks like this. And it includes the spin torque. And if you consider the CPP geometry, that means current perpendicular to the plane of the your system. And then you can solve this equation, and you see there are two components of velocity that is here. One is the Vx, which is the motion along the x-axis, that is along the direction of the current. But also there is this y component of velocity, which is now proportional to g, and this g contains q. So obviously, depending on the sign of q, this value Vy will be positive and negative. And also it will depend on the current direction. If Jx is, it is also directly proportional to x. So there is a y component, and it also changes sign with x and y. I mean the changing sign of the charge current. So this was experimental. This was simulated as well as experimentally confirmed in this Nature Physics paper where they simulated fast that the skyrmion is moving this way, not along the X, but along the Y, and the direction is actually reverses if you change the charge current direction. And that was also confirmed experimentally. The red arrows for positive current, whereas the blue arrow is for negative current, and so the motion is opposite to each other. So this nicely basically explains this phenomena. But this also possesses a challenge because of the skyrmion Hall effect. You are not able to move the skyrmions in a nanotrack. That means this is not really going to be. This is going to be a challenge to use this skyrmion motion for any racetrack memory applications. So of course we have to solve this. That is one of the purpose of this talk. But also you can use this skyrmion Hall effect actually to your advantage. And one of our work actually we did that. And we took a nano disk and we stabilized the skyrmion numerically, and then we introduced spin polarized current. And because of this, the magnetostatic field, we could stabilize an auto oscillation, and we call it a skyrmion oscillator, and that was stabilized in this. The more information can be found in this paper. And this oscillation was actually found to be resulting from two kinds of motion. When you actually just look at the nano disk and you did a little micromagnetic simulation to find out what are the eigen modes of the system, and we saw that there are two kind of motions that is possible. One is that the skyrmion can actually just rotate, so that is the gyration motion with the frequency range and this like this. Also, there is something called breathing motion, where the radius of the skyrmion is basically changing. So that is that occurs at a little bit higher frequency. And so these are the two eigen modes that we can excite by temperature, as we saw in this paper. But in the previous work that I mentioned, there we could synchronize the two motion and get auto oscillations of the skyrmion, and which can be useful for example, microwave communication and so on. But the problem is now for memory application, this is how we're not going to be useful. So we have to overcome this problem of the skyrmion Hall effect. And in order to overcome the skyrmion Hall effect, there has been certain proposals already. And one of the proposal was published in this paper by Zhang in this Nature Communication paper in 2016. This is also a numerical simulation paper where they propose what is known as antiferromagnetic skyrmion. And this antiferromagnetic skyrmion is shown here. This is basically the same as a skyrmion, but now what you do, you take a skyrmion and you, for each spin, you have now two spins. One is spin up, another is spin down. So like in this case, green and yellow. So for every spin, you have a one pointing off, another pointing down. Then you can form a structure. Now it is as if you have two skyrmion. One is pointing, the core of which is pointing up. The other skyrmion core is pointing down. And they have opposite Q. Q is +1 for one, and the other is Q -1. So the net Q is 0. And so this is what you can look at in more detail here. This figure, if you look at the line profile, this looks very similar to the Neil skyrmion I showed you before. Now only thing is that you have, instead of one spin, you have a pair of spin, one going opposite to the other. And so once you can create this AFM skyrmions, they have shown in this paper that if you have a really small nano contact, then you can inject a current, spin polarized current, and then after a while you will create a skyrmion which looks like this, AFM skyrmion. It is you can create by spin polarized current. But however, one thing I would like to point out is they were using a out of plane spin polarized current. That means current was going along the Z direction, but also polarized. The spin current has a polarization which was also out of plane. So this was the work they had done. And they showed that if you have this kind of AFM skyrmion, because Q is 0, as you can see that the Y component will be now 0. This was also shown in their simulation that if you pass the current, it moves very nicely in the straight line. And in contrast, there is this lower one is showing for a simulation for FM skyrmion, where it is going towards the edge and is collapsing here. So the AFM skyrmion will obviously remove this, will have no skyrmion Hall effect, so it can move in the straight line, and also it can move faster than the, because of that it can also move faster, of course. So this is so far has been a theoretical idea, and so we are inspired by this theoretical idea, and we try to do simulation in this direction. So we use mu max, and we use the parameters which were basically same as that from the paper. And then first thing we did was we tried to see where what parameters are needed for the stabilization of the AFM skyrmion, and we found that there is a really narrow range. As you can see, this orange region is where actually you can get the AFM skyrmion. And there are other structures you can stabilize in different regions, but we are interested in AFM skyrmion. So we took that sets of parameter, and then we try to take a nano contact, and then we inject a spin current here in this manner here. And what you see is that we are actually injecting a pulse current. So we do not inject a continuous current, but there is a pulse current. So we inject the current and then we switch off the current. So this is the nano contact area, which is taken to be 70 nanometer, and the current was injected in this region. And as you can see in this movie now, as you inject the current, and after a certain time, you will see that it actually, you see this kind of orange ring that is being formed. And this red indicates that this pulse is now switched off. So even after the current is off, the skyrmion is still evolving, and eventually it stabilizes to some like this. And this is what after about 20 picoseconds, it has a diameter about 32 nanometer in this case. And if you look at now, the question is, why do we see this orange circle? Is it really FM skyrmion, or why it is orange in color and all that? So investigate that in detail. And there is a reason why the color is orange. It's because of the color scale that we are using. So if you look at in simulation, there is one good thing is that you can look at this individual lattices separately. So if you look at sub lattice A and B, then you see that this is one skyrmion basically up and the other skyrmion down. And you can see that if you look at this topological charge, initially it was 0, but when you inject the current, after a while, the topological charge of the sublattice A is positive, and that of +1, and that of B sublattice B becomes negative -1, so that you have a net topological charge is 0. So this actually conclusively proved that okay, we have actually formed a AFM skyrmion. The reason why it looks orange is because only at this, because there are 2 spins at each point. So the color, it is a very difficult thing to see in a color contrast. That is why we only see basically the edge of the object, and that's why it looks somehow orange. Okay, now, so this is how the AFM skyrmion is nucleated. Now we can look at, yeah, we can also, before that, I can just, sorry, I can, I'm sorry. We can see, we can also define this nucleation time here, and you can see that this only takes 10 picoseconds, around about 10 picoseconds to form this AFM skyrmion. That is why you call ultra fast nucleation, because it takes it is really fast process. Now we studied this in a little bit more detail. So we look at, this is the total energy of the system, which consists of different exchange energy, DMI, anisotropy, and so on. And what we did is we look at the total energy minus W0, or W0 is the energy before we inject the spin current. And so we look at this delta W and look at as a function of time as you inject the current. So this is for different pulse width, for example. So if your pulse is like 4.5 picoseconds, so initially the energy will increase because you are injecting a pulse current, injecting a current to the system. And then after a while, the energy drops and it goes back to 0. So this happens also same for 5 picoseconds, and also the Q is 0 at that point. So, but if you go to a little bit higher current, higher threshold, you apply the current a little bit longer with a pulse width of 5.5 picosecond. You see that it doesn't go to 0, but it actually has a certain finite value, and this is where the AFM skyrmion is actually stabilized. So that you can also see, you may also see this from this movie which was running. After about 10 picoseconds, you have this AFM skyrmion that is stabilized. So this is, I can see this is not a ground state, it is a metastable state because the energy is not, it is above the ground state. So it is a metastable state. But important point here is that there is a threshold pulse width. So you need to apply a certain threshold current above which only this nucleation will happen. And in this case, it is that 5.5 seconds. So here at 5 seconds, the 5 picosecond, nothing was happening. But if you apply 5.5 picosecond pulse width, then you can see that after a while you will form this AFM skyrmion. So there is a threshold of pulse width also that is involved. Of course, it also depends on the amount of current. In this graph, we have fixed the current. So we can study this in more detail as a function of threshold current and pulse width. And that we did in the next slide. And now we did it for two cases. In our case, actually, we are using in-plane spin polarized current. So the current is vertical, but this polarization, spin polarization is in plane.
You're running out of time. You're running out of time. Okay, just.
Oh, okay. I will try to finish.
Yeah.
So in the case of there are two cases. So we compare these two cases. This was the case that was used by the other paper. We see that the nucleation time in our case is significantly lower than out of plane case. And also there is a linear dependence of the threshold current density and the threshold pulse width, from which we extract this number here, which we called threshold current, which is independent of pulse width. And this is, you can see that this is significantly lower for this in-plane case. We also look at the energy consumption, and this energy consumption is proportional to the square of current into the pulse width, and that is also found to be significantly lower for the in-plane case, and compared to the out-of-plane case. And we also look at the question is now why it is so. Why is the in-plane case better than the out-of-plane case? So we examined that in detail, and we found that when you are applying the in-plane current, it actually takes a really small time. If you look at the motion of the spins while we apply the current, the trajectory is rather simple, whereas when you apply out-of-plane spin current, the trajectory of the magnetization is rather complex, and that is shown here. So this is the initial state of the spin, the core. If you look at the core, it was up, and it has to go down for the skyrmion to form, and the process is like this. Whereas in this out-of-plane cases follows a spiral path, and that is why the nucleation time is much longer here. So we also look at another thing, that if you switch on the pulse and you keep it for a very long time, so what happens is that initially you are forming one skyrmion. Because you are using an in-plane polarized current, there is a little bit of spin torque which can actually push the skyrmion outside of the contact, and we can actually form then two AFM skyrmion if you apply a little longer. And if you apply more, then you can also form three AFM skyrmion. Although there is a merging of the skyrmion that is happening, which sometimes destroy the skyrmion, but we can actually controllably form three AFM skyrmion by applying longer pulses, and this is very much reproducible. We can also, so I think in the interest of time, I will skip this movie. This shows with this process basically, but we also look at the temperature effect, because so far whatever I saw was at 0 Kelvin. So if you introduce the temperature, obviously things will get randomized, but we saw that we can still stabilize AFM skyrmion even at finite temperature. And if you look at the nucleation time, actually it goes down as you increase the temperature. So it is actually beneficial. So threshold pulse width, the threshold pulse width needed for nucleation is found to decrease for a fixed current. So this is going to be beneficial for application. So that means this ultra-fast nucleation process is robust and it is not affected by the finite temperature. So that's all I want to discuss. So this is the conclusion that I have. We demonstrate ultra-fast nucleation of FM skyrmion, and we show that this is energy efficient if you use in-plane spin polarized current, and it is robust with respect to temperature. In addition, you can also create multiple FM skyrmion by this method. So thank you for your attention.
Thank you, Professor Mugadi, for this nice presentation and on skyrmion. And this is a very, this contemporary topic, and so there is a lot of people are working on it, and it may be useful for future Spintronics and other purposes. And now I think I have already I have a question here from Esita Pandey. What is the origin of DMI in graphene NIFE system?
Okay, so we had. We think it is actually driven by the defect at the interface between graphene and permalloy. So it is an interfacial. It is, of course, origin is from the interface, but also it is partly driven by the defect, because we could. What we did in the experiment was we changed the argon pressure during the growth of permalloy, and that we found to introduce some defects into graphene, and that was found to increase the DMI. Based on that, we can say that it is extrinsic origin, in that sense, a defect-driven DMI. But people have also observed a DMI in this system where it is supposedly not driven by defects.
So, any other question?
I have a quick question.
Yeah, Shubhankar, please.
So what we have been told by others that the OOMF, that's also the platform for MUMAX, that it is not ready yet for antiferromagnetic skyrmions, because for that you really need atomistic simulation. So is it like the MUMAX has now implemented the exchange length, or how did you know?
No, actually, there is a little bit of contradiction in the literature about whether how to implement antiferromagnetic system in the MUMAX. Some people have done in a different manner. We did basically, we consider this exchange interaction to be negative. So that is a simple way to consider, and that is how we have done it. But there are other groups where they take each spin, they have two. Each cell of the micromagnetic simulation has two spins, one pointing up, another pointing down, and there is a coupled LLG equation that they solve. So that is a much more complex approach, and some people believe in that approach. But we have taken this approach where J is just negative. That's it.
Okay, I don't know, Stanislas, you want to comment on this?
Yeah. Hi, Suvanka. I completely agree with your comment. I think that negative exchange is not appropriate, and that MUMAX, like OOMF, is adapted for ferromagnetic description, and we are running atomic scale calculation that show, and the complexity of antiferromagnets is much more complex than ferromagnets. It's not my approach, and yeah, I prefer atomic scale simulation for that. Or like we do for ferromagnets, we use two spins per lattice, but then you don't describe the antiferromagnetic order parameter. So that's good for amorphous ferromagnets, not for antiferromagnets. The complexity of antiferromagnets can only be described by atomic scale calculation up to now. That's my point of view, at least.
Yeah, anyway, thank you. I think we are done. So Abhishek, you can share your screen with the memento. It's almost 10.
It's almost 10 now. So I thank the speaker once again, and I have a present job to do. This is the memento, and this is a virtual presentation to you, and I read it out. So, Symposium on Magnetism and Spintronics, SMS 2021, National Institute of Science, Education and Research, Nizer, Bhubaneswar, India. Take immense pleasure in presenting the plaque to Professor Pranaba K. Muduli, IIT Delhi, India, in appreciation for being a valuable speaker to give a lecture on the ultrafast nucleation of single and multiple antiferromagnetics stimulants.
Yeah, thank you so much. Very nice talk.
Thank you very much.
So I also like to thank Professor Shubham Majumdar for his excellent chairing of the session. All the lectures were really nice. Abhishek, could you please play the memento for the chairman? And it's my real pleasure to present this memento to Professor Shubham Majumdar. So, Symposium on Magnetism and Spintronics, Mysore, Bhubaneswar, takes immense pleasure in presenting this plaque to Professor Shubham Majumdar from ISCS India in appreciation for chairing the session. Thank you so much, Professor Majumdar, for your kind efforts to be present in the conference. I'd like to thank all the speakers of this session of today, and it was really nice, excellent set of talks. So we are very much looking forward to tomorrow. We also had really excellent set of posters, but I believe today while browsing we had some difficulty. So we have requested the today's presenters to be also present tomorrow, mostly if they are available. And tomorrow we have another poster session, so we can again interact. And tomorrow we have again interesting set of talks. We start 2 o'clock Indian time, that's 9:30 a.m. Central European time. So with this, I wish you all a good night or nice day wherever you are, and see you tomorrow. Thank you so much. Take care. Bye bye.
Thank you.
Bye.
So we end for today.